Welcome to Docker and Kubernetes for beginners. My name is Vladimir Živković and I'll be your instructor throughout this course. If you ever wanted to learn Docker and Kubernetes but didn't know where to start, you're in the right place. This course is designed specifically for beginners, which means you don't need any previous experience with containers or container orchestration. We'll start with the fundamentals, build a strong foundation, and then gradually move toward practical, real-world examples. Every lesson is explained step by step, making even complex topics easy to understand. My goal is not only to teach you the commands, but also to help you understand why Docker and Kubernetes work the way they do. Once you understand the concept, you will be able to apply them confidently in your own projects. Before we get started, I'd like to mention that this course is condensed and updated version of one of my previous courses, Docker, Kubernetes, and Azure Container Services. But before we wrap up this first lesson, I'd like to ask you for a small favor in the beginning of this course. If you enjoyed this course and found it helpful, please consider supporting my work by subscribing to If you're watching this course or any of my courses of free time, let me just introduce myself. So this section is about me. As you already know, before we begin, let me briefly introduce myself. My name is Vladimir Živković, as you already know, and I am Microsoft Certified Trainer, Cloud Consultant, Solution Architect Expert, and online instructor with many years of experience working with cloud technologies, infrastructure, networking, identity management, and modern IT solutions, and of course AI consultant. Throughout my career, I have earned multiple industry recognized certification, including Microsoft Certified Trainer, MCT, Microsoft Certified Azure Administrator Associate, Azure Solution Architect Expert, Azure Networking Engineer Associate, AI Business Professional or AB 730 and 731, which is AI Transformation Leader. And finally, AWS Certified Solution Architect Professional, and I have a few more certification, but this is the most important one. Of course, over the years I have helped thousands of students building their cloud and infrastructure skills through online courses and hands-on training. My teaching philosophy is simple: explain complex concepts in a clear and practical way, focusing on the real-world scenarios rather than memorizing commands. Of course, I teach and it was able to find. You're now not able to find my courses in Udemy platform because I pulled off my courses, and most of these courses I will publish on this YouTube channel, or part of this course, of course. In this course specifically, I will guide you step by step through Docker and Kubernetes, helping you build a solid foundations. And finally, the third lesson before we start is I want to explain what are we going to learn in this course. In this course, we will build your Docker, Kubernetes and Kubernetes knowledge step by step, starting from the very beginning. We will begin by installing Windows Subsystem for Linux or WSL and Docker Desktop, making sure your environment is properly configured before moving on the hands-on labs. From there, you will learn how to create and manage Docker images, run and manage containers, work with Docker volumes and networks, build your own Docker files, use Docker Compose to deploy multi-container applications, understand the fundamentals of Kubernetes, create and manage pods, deployments, replica sets, and services, work extensively with YAML files to define and deploy Kubernetes resources, deploy applications to a Kubernetes cluster, and explore many additional concepts and practical demonstrations along the way. Of course, I have only basic lessons here, but this will be enough, and this hands-on will be enough for you to understand and how to begin to work with your Docker and Kubernetes, of course. Then, throughout this course, we'll focus on understanding not only how things work, but also why they're designed that way, helping you build a solid foundation for future DevOps and cloud technologies. Of course, just like in any of these free or my previous Udemy courses, first there is a simple PowerPoint presentation, of course, and then we will get practical work. As an added bonus, the download section includes all of the files that I use throughout the course, including source files, configuration files, YAML manifest, scripts, and a complete PowerPoint presentation that I use during the lessons. This allows you to follow along with every demonstration and practice everything at your own pace. By the end of this course, you will have the confidence to build, run, and manage containerized application using Docker and Kubernetes, while also being well prepared to continue learning more advanced DevOps technologies. Of course, as I already mentioned, this is a condensed version of this course, and the cloud part I am not included in this course. Of course, in the first version of this course, there was more than 10 hours of Azure Kubernetes service. Then we have the complete guide how to work with ACA and ACI. So the first lesson or the next lesson, and we are officially starting with this course, is what is a container. Once again, buckle up, we are starting. But before we start with our course, we need to learn some basic lessons about containers. So in this lecture, I will talk about what is a container. Containers are executable units of software that package application code along with its libraries and dependencies. They allow code to run in any computing environment, whether it be desktop, traditional IT, or cloud infrastructures. Containers take advantage of a form of operating system, or OS, virtualization in which features of the OS kernel, for example Linux namespaces and C groups, Windows silos, and job objects, can be used to isolate processes and control the amount of CPU, memory, and disk for those processes and access. More portable and resource efficient than virtual machines, containers have become the de facto compute units of modern cloud-native applications. Additionally, containers are critical to the underlying IT infrastructure that powers hybrid multi-cloud settings, the combination of on-premises, private cloud, public cloud, and more than one cloud service from more than one cloud vendor. The primary advantage of containers, especially as compared to a VM, is that they provide a level of abstraction that makes them lightweight and portable. So let's learn what their primary benefits include. They are lightweight. Containers share the machine OS kernel, eliminating the need for a full OS instance per application and making container files small and easy on resources. A container's smaller size, especially compared to a VM, means it can spin up quickly and better support cloud-native applications that scale horizontally. They are portable and platform-independent. Containers carry all their dependencies with them, meaning that software can be written once and then run without needing to be reconfigured across computing environments, for example, laptops, cloud, and on-premises. They are supportive of modern development and architecture due to a combination of their deployment portability and consistency across platforms, and their small size. Containers are an ideal fit for modern development and application patterns, such as DevOps, serverless, and microservices that are built by using regular core deployments in small increments. Also, the fourth thing, their containers are improved utilization. Like VMs, containers enable developers and operators to improve CPU and memory utilization of physical machines. Containers go even further because they enable microservices architecture so that application components can be deployed and scaled more granularly. This is an attractive alternative to scaling up an entire monolithic application because a single component is struggling with its load. Also, containers are faster time to market. Containers rely less on system resources, making them faster to manage and deploy than VMs. This feature helps save money and time on application deployment and optimizes time to market. Containers depend on containerization, the packaging of software code with just an operating system and its relevant environments, variables, configuration files, libraries, and software dependencies. The result is a container image that runs on a container platform. A container image represents binary data that encapsulate an application and all its software dependencies. Containerization allows the application to be written once and run everywhere, providing portability, speeding the development process, preventing cloud vendor lock-in, and more. Let's talk about virtual machine. What is a virtual machine? A virtual machine, or VM, is a compute resource that uses software instead of physical computer to run programs and deploy apps. One or more virtual guest machines run on a physical host machine. Each virtual machine runs its own operating system and functions separately from other VMs, even when they are all running on the same host. This means that, for example, a virtual macOS virtual machine can run on a physical PC. Virtual machine technology is used for many cases across on-premises and cloud environments. More recently, public cloud services are using virtual machines to provide virtual application resources to multiple users at once for even more cost-efficient and flexible compute. So, the logical question, what are virtual machines used for? Virtual machine or VMs allow a business to run an operating system that behaves like a completely separate computer in an app window on a desktop. VMs may be deployed to accommodate different levels of processing power needs, to run software that requires a different operating system, or to test applications in a safe, sandboxed environment. Virtual machines have historically been used for server virtualizations, which enables IT teams to consolidate their computing resources and improve efficiency. Additionally, virtual machines can perform specific tasks considered too risky to carry out in a host environment, such as assessing virus-infected data or testing operating systems. Since the virtual machine is separated from the rest of the system, the software inside the virtual machine cannot tamper with the host computer. How does virtual machine works? The virtual machine runs as a process in the application window, similar to any other application, on the operating system of the physical machine. Key files that make up a virtual machine include a log file, NVRAM setting file, virtual disk file, and configuration file. Let's talk about advantages of virtual machine. Virtual machines are easy to manage and maintain, and they offer several advantages over physical machine. We can run multiple operating system environment on a single physical computer, saving physical space, time, and management cost. Virtual machines support a legacy application, reducing the cost of migrating to a new operating system. For example, a Linux virtual machine running a distribution of Linux as the guest operating system can exist on a host server that is running a non-Linux operating system such as Windows. VMs can also provide integrated disaster recovery and application provisioning options. There are five types of virtualization. All components of a traditional data center or IT infrastructure can be virtualized today, with various specific types of virtualizations. The first one is hardware virtualization. When virtualizing hardware, virtual versions of computer and operating system are created and consolidated into a single primary physical server. A hypervisor communicates directly with a physical server disk, space, and CPU to manage the VMs. Hardware virtualization, which is also known as server virtualizations, allow hardware resources to be utilized more efficiently and for one machine to simultaneously run different operating systems. Software virtualization creates a computer system complete with hardware that allows one or more guest operating system to run on a physical host machine. For example, Android operating system can run on a host machine that is natively using a Microsoft Windows OS, utilizing the same hardware as the host machine does. Additionally, application can be virtualized and delivered from a server to an end-user device, such as a laptop or a smartphone. This allows employees to access centrally hosted applications when working remotely. The third one is storage virtualization. Storage can be virtualized by consolidating multiple physical storage devices to appear as a single storage device. Benefits include increased performance and speed, load balancing, and reduced cost. Storage virtualization also helps with disaster recovery planning, as virtual storage data can be duplicated and quickly transferred to another location, reducing downtime. The fourth one is network virtualization. Multiple subnetworks can be created on the same physical network by combining equipment into a single software-based virtual network resource. Network virtualization also divides available bandwidth into multiple independent channels, each of which can be assigned to servers and devices in real time. Advantages include increased reliability, network speed, security, and better monitoring of data usage. Network virtualization can be a good choice for companies with a high volume of users who need access at all times. And the last one is desktop virtualization. This common type of virtualization separates the desktop environment from the physical device and stores the desktop on a remote server, allowing users to access their desktop from anywhere or on any device. In addition to easy accessibility, benefits of a virtual desktop include better data security, cost saving on software licenses and updates, and ease of management. With the help of virtualization, with the help with Oracle VirtualBox Manager, I can run Linux virtual machine on my Windows laptop. As you can see, I have these virtual machines already spun up. One is a server and one is a Ubuntu Linux. If I check this VM1, which is powered off right now, I can click on Start to start my virtual machine, and we are powering VM up, and after some time my Linux Ubuntu VM will boot up, will power up, and I can simply log into my VM and continue to test or develop some application on some other thing. As you can see, this is complete virtualized virtual machine on my Windows Linux VM on my Windows VM. I can run my terminal and I can do whatever I want. For example, let's try to update my machine. I need to add my password, and we are updating my Linux VM, my virtualized VM, and then I can even run, I can even run whatever I want. And I can even listen to the music, run certain programs, run Wireshark for example, and that's it. Just like normal VM. You can even update or install anything you want. You can surf, for example, for those who don't know what is VM or virtual machine, I can, for example, read some news. Let's go to NFL.com if you like American football or NFL, and you can simply run whatever you want. This was just a simple reminder, and for those who don't know how can you run virtualized VM on Linux VM on Windows VM on my Windows laptop, this is how can you do it. Thank you for watching, and in the next chapter we will talk about difference between the container and virtual machine. Like virtual machine, container technology such as Kubernetes is similar in the sense of running isolated applications on a single platform. While virtual machines virtualize the hardware layer to create a computer, containers package up just a single app along with its dependencies. Virtual machines are often managed by a hypervisor, whereas container systems provide shared operating systems, services from the underlying host, and isolate the application using virtual memory hardware. A key benefit of containers is that they have less overhead compared to virtual machines. Containers include only the binaries libraries and other required dependencies, and the application. Containers that are on the same host share the same operating system kernel, making containers much smaller than VMs. As a result, containers boot faster, maximize server resources, and make delivering applications easier. Containers had become popular for use cases such as web applications, DevOps testing, microservices, and maximizing the number of apps that can be deployed per server. VMs are larger and slower to boot than containers. They are logically isolated from one another with their own operating system kernel and offer the benefits of a completely separate operating system. Virtual machines are best for running multiple applications together, monolithic applications, isolation between apps, and for legacy apps running on older operating systems. Containers and virtual machines may also be used together. The third topic that is also important from this course is application. So in this chapter I will talk what is an application. You may have heard people talking about using a program, an application, or an app, but what exactly does that mean? Simply put, an app is a type of software that allows you to perform specific tasks. Applications for desktop or laptop computers are sometimes called desktop applications, while those for mobile devices are called mobile apps. When you open an application, it runs inside the operating system until you close it. Most of the time, you will have more than one application open at the same time, which is known as multitasking. App is a common term for an application, especially for simple applications that can be downloaded inexpensively or even for free. Many apps are also available for mobile devices and even some TVs. There are countless desktop applications, and they fall into several categories. Some are full-featured, like Microsoft Word, while others may only do one or more things, like a clock or a calendar app. There are a few types of application that you might use. For example, word processor. A word processor allows you to write a letter, designing a flyer, and create many other types of documents. The most well-known word processor is Microsoft Word. Web browser. A web browser is the tool you use to access the internet. Most computers come with a web browser pre-installed, but you can also download a different one if you prefer. Examples of browsers include Mozilla Firefox, Google Chrome, or Safari. Also, there is various media players. If you want to listen to MP3s or watch movies you need to use a media player. Windows Media Player or iTunes are popular media players. Also, there are many types of games that you can play on your computer. They range from card games like Solitaire to action games like Hello or something else. Many action games require a lot of computing power, so they may not work unless you have a newer computer. Desktop and laptop computers aren't the only devices that can run applications. You can also download apps for mobile devices like smartphones and tablets. There is also an application for mobile apps, like Gmail. You can use the Gmail app to easily view and send emails from your mobile device. It's available for Android and iOS devices. Instagram, you can use Instagram to quickly share photos with your friends and family. It's also available for Android and iOS. Every computer and mobile device will come with some application already built in, such as web browser and media player. However, you can also purchase and install new apps to add more functionality. Let's talk about the benefits of containerization. Every day, developers or administrators find a new way to put containerization to work to solve their challenges. Containerizations can produce unique benefits for your applications. Here are some of the most common reasons when administrators, developers, or architects decide to containerize an app. First is portability. No discussion of containerization is complete without at least one mention to the motto write once, write anywhere. Because a container bundles dependencies, you can take your application just about anywhere without rebuilding it for each new environment. The abstraction provided by containerization ensures that your container works the same way no matter where you deploy it. That means you can take your app to the cloud, run it on a VM, or go directly to bare metal. As long as the host operating system supports your containerization tools, such as Docker, you are ready to deploy it with minimal hassle. Efficiency. Containerization is one of the most efficient methods of virtualization available to developers, administrators, or architects. Containers improve efficiency in two ways. They use all available resources and they minimize overhead. When properly configured, containers allow a host to take advantage of virtually all available resources. Isolated containers can perform their operations without interfering with other containers, allowing a single host to perform many functions. Containers also remove the need for virtualized operating system, hypervisors, and other bottlenecks the virtualization techniques introduce. Unlike VMs, which rely on the virtual kernel, containers use the host operating system kernel, and this drastically reduces overhead and minimizes resource use. The third one is agility. Containerization is a crucial tool for streamlining DevOps workloads. Create containers rapidly, deploy them to any environment, and then use them to solve multiple diverse DevOps challenges. When a task presents itself, you can quickly develop a container to handle the job. Then you can automatically shut it down until you need it again, a process called orchestration. Technologies like Kubernetes automate the process of coordinating, managing, scaling, and removing containers. You can think of Kubernetes as the conductor of your container orchestra. With the help of Kubernetes coordinated containers, developers, administrators, or architects can rapidly respond to problems and spin up novel solutions without worrying about lengthy and complicated deployment. It's faster delivery. How long does it take to upgrade to go from concept to implementation? Generally, the bigger an application, the longer it takes to get any improvements implemented. Containerization solves this issue by compartmentalizing your application. You can divide even most enormous beast of an application into discrete parts using microservices. Microservices takes apart much larger application by segmenting pieces into containers. This division makes it easier for developers to implement changes and deploy new code. You can change isolated areas of the application without affecting the whole. Continuous integration, or CI, is a natural partner for containerization. CI automates the process of merging, testing, and building new code. Many modern CI/CD pipelines output a container image as their final step. Improved security. The isolation introduced by containerization also provides an additional layer of security. Because containers are isolated from one another, your applications are running in their own self-contained environment. That means that even if the security of the one container is compromised, other containers on the same host remain secure. Containers are also isolated from the host operating system and can only minimally interact with computing resources. This is inherently more secure the way to deploy the application. Faster app startup. Compared to other methods of virtualization, containers are quite lightweight. One of the many benefits of being lightweight is rapid startup times. Because a container doesn't rely on a hypervisor or virtualized operating system to access computing resources, startup times are virtually instantaneous. The only limiting factor is the application itself. With no substantial overhead to wait for, the only startup delay is from your code. Rapid startup is a great reason for frequent updates and improvements. Flexibility. Containerization allows developers the versatility to operate their code in either virtualized or bare metal environment. Whatever the demand of deployment, containerization can rise to meet them. Should there be a sudden need to retool your environment from metal to virtual or vice versa, your containerized applications are already prepared to make the switch. containerized apps using microservices becomes so flexible that you can host certain elements on bare metal and deploy other to virtual cloud environments. You can also deploy it to hybrid cloud environments that utilize a mixture of bare metal, on-premise and various cloud providers. With the portability of containers, you can select the most effective way of hosting the different services in your app. Thinking with containers allows developers, administrators or architects to reconceptualize their available resources. That might mean squeezing an extra drop of processing from a machine at maximum capacity, or it could mean finding that what before seemed like a resource limitation was simply an opportunity to innovate. And the last one is easier management. Kubernetes offers a variety of tools that simplify container management, like rollbacks and upgrades, as part of the platform. It also handles installation. There are self-healing features you can use to attempt to recover failed containers, terminate containers that fail health checks, and constantly monitor your container's health and status. Kubernetes also automates resource management. You can allocate each container a set amount of CPU and RAM to handle its task. Ultimately, managing containers with the help of a tool such as Kubernetes is leaps and bounds easier than traditional application management methods. I'm sure you heard of Docker in the previous chapters, so it's time to get to know what Docker is. Docker is a set of platform as a service or PaaS products that use OS-level virtualization to deliver software in packages called containers. The service has both free and premium levels. The software that hosts containers is called Docker Engine. It was first released in 2013 and developed by Docker Incorporated. Docker is a tool that used to automate the placement of application in lightweight containers so that application can run efficiently in a variety of isolated environments. Containers are isolated from each other and bring together their own software, libraries, and configuration files. They can communicate with each other through well-defined channels because all containers share the same services of a single operating system core. They use fewer resources than virtual machines. Docker can package an application and its dependencies into a virtual container that can run on any Linux, Windows, or macOS computer. This allows the application to run in a variety of locations, such as on-premises, public, like decentralized computing, distributed computing, and cloud computing, or private cloud. When running on Linux, Docker uses Linux kernel, resource isolation features such as C groups and kernel namespaces, and a union-capable files such as overlay.fs to allow containers to run within a single Linux instance, avoiding the overhead of running and maintaining virtual machine. Docker on macOS uses a Linux virtual machine to run containers. Because Docker containers are lightweight, a single server on virtual machine can run several containers at the same time. A 2018 analysis found that a typical Docker use case involved running 8 containers per host, and that a quarter of the organization analyzed running 18 or more per host. It can be installed on a single board computer, such as the Raspberry Pi. Linux kernel support for namespaces generally isolate the app view of the operating environment, including process, trees, networks, user ID, and mounted file system, while kernel C groups provide resource limitation for memory and CPU. Docker implements a high-level API to provide lightweight containers that run processes in isolation. The Docker registry is a repository for Docker images. Docker clients connect to registries to download or pull images for use or upload push images that they have created themselves. Registers can be public or private. The main public registry is the Docker Hub. Docker Hub is the default registry where Docker searches for images. Docker registries also allow you to create event-based notification. Also, if you already know what Azure is, Azure Container Registry allows you to create, store, and manage containers, images, and artifacts in a private registry for all types of container deployments. You can use Azure Containers registries while existing pipelines to develop and deploy containers. You can use Azure Container Registry task to create container images in Azure on demand or automate builds that run source code updates, base container images, update, or timers. In this chapter and the next chapter, we will learn how to install Docker on our Windows machine. But first, let's see what we need to do. If we want to work with Docker and containers on our Windows machine, the first thing we have to do is to install Docker Desktop. When we install Docker Desktop, we will also install the necessary Docker runtime and all the necessary tools. Also, if we want to run Windows containers, we must have at least Windows 10 or 11, Professional or Enterprise Edition. The second thing we need is WSL or Windows Subsystem for Linux. In this installation, allow us to work with the Linux containers. During this course, I will exclusively talk about installation on a Windows machine. So, in the next chapter, we will see how to set up Docker on our Windows machine. Now it's time to install Docker Desktop, so we will go to the official website of Docker or Docker website and click on download. As you can see, we are now at www.docker.com and we have this download Docker Desktop option for macOS, Windows and Linux. I will choose my download for Windows AMD 64. I will download this file and then we need to, if you didn't know, you can open Google and search for WSL or Windows Subsystem for Linux. This is that page on learn.microsoft.com. But first we need to install our WSL. Let's first check. Our Docker Desktop is downloaded, so I will first go to my start menu and in the search I will search PowerShell and run it as an administrator. Then I will go back to our WSL and simply copy this command WSL -- install. Then I will simply copy that command and paste it into PowerShell window that we previously started as an administrator. What this command will do, it will install the Ubuntu repository on our Windows machine. But first, we are enabling virtual machine platform feature, and after that, our Ubuntu repository will be installed on our VM. So let's wait for our virtual machine platform to install. If you already have installed this option, it will simply go and install your Ubuntu repository. So I will now pause my video and continue when this virtual machine platform is installed. Simply open Windows PowerShell, copy WSL -- install, and your Ubuntu repository will be installed on your machine. Then after this installation of Windows platform is finished, I will again run my PowerShell as an administrator and then I will again copy this command, and it is now downloading our Ubuntu image. And now it's installing our Ubuntu. And our distribution is successfully installed, and it can be launched via wsl-exe/d ubuntu. We don't need our PowerShell anymore, so if I go to our Windows Start and search for Ubuntu, I now have this Ubuntu app, and then, because this is the first time we are run this Ubuntu, it's provisioning the new WSL instance Ubuntu, and this as you can see, take a minute. You can create a default Unix user account, and you have to give your name here. I will leave this as my name, and when I hit enter, then it will ask me to add my password or to create my password, but for now I will just wait for a few minutes, and then I will add my password. After that, we will run our Docker desktop, and we will install our Docker desktop. And here it is. I have option to add my new password. I will add my password. I need to retype my password, and our password updated successfully, and as you can see, we are now running our WSL or Windows Subsystem for Linux on our Windows machine. If I, for example, open my Explorer, you can see that we have a little Linux icon here, and that's it. Then, as I already said, we need to install our Docker desktop by clicking on the icon that we previously downloaded. I will click on yes, and you just need to click on OK, and our Docker desktop is being installed. After that, we will need to restart our computer, and we are ready to run our first container if we want. While Docker desktop is installing, when you start in the morning and to work with your containers, the first thing you need to do is to run your Ubuntu or WSL Windows Subsystem for Linux, and then you can run Docker desktop. When you finished working with your containers, first exit from your Docker desktop, and then you can exit from your WSL. This is the recommended way, so just to keep any trouble, just do it that way. So we're waiting for our Docker desktop to be installed. And then I will stop my recording. That we can successfully restart our machine. After restart, I will go to my Windows Start menu, type Ubuntu in the search. This will run my Ubuntu repository, and then I can run my Docker desktop icon, and I will accept this. I can add my email, then I can authorize. You can set what is this role, and I'm officially logged in to my Docker desktop, as you can see. Then you can go to settings and choose your general settings, and okay, let's go to our Docker home. This is for my personal use. You can see that you can go from here right to Docker desktop, Docker admin console, Docker hub, and so on. This is my personal. You can view your Docker Scout. It's now enabled, and if you can see, we have this. We don't have any container here. We have images. We don't have any images. I have one hub repository. There is something called volumes, builds, and so on. This is how can you install and run Docker and Windows Subsystem for Linux on your Windows machine. In the next chapter, we will learn what is an image first, and in the upcoming chapters we will see how can we run our first container in Docker. Container images are unchanging static files that hold executable code and operate in isolation on IT infrastructure. A container image assembles all the components needed to create a container on an operating system, and it comprises different image layers stacked on the top of each other. Containers images are immutable and share the same functions as templates. Container images are stored within a container image registry or container registry that serves as a type of a file system. Container registries are data repositories or multiple repositories that warehouses container images for storage and or access. One notable advantage of container registry is how smoothly they connect to container orchestration system platforms like Kubernetes and Docker. In addition, container registries can be used in a DevOps capacity during container-based application development, enabling optimized workflow integration. A container image is an assembled accumulation of layers that include the following: base image, libraries, binaries, dependencies, and configuration files. In new images built from scratch, it all starts with the bottom layer, the base image. The base image is where the most container-based development workflows begin. Many base images comprise basic or minimal Linux distribution like Debian, Ubuntu, or Red Hat Enterprise Linux, Rocky Linux, or Alpine. Base images are where the container's file system are stored. The process of creating base images, known as building, enable developers to construct and standardize environment which support custom container images. Container images are stored in container registries where images can either be uploaded to that registry, pushing, or downloaded into different system or pooling. Container registries use object storage to manifest metadata about container images. This offers a means for successfully transferring such metadata, but it's limited. For example, in the case of data involves multiple images, there are limits on the possible number of available listing tags. Dependency containers offer another storage method. These containers enable the management, registration, and resolution of dependencies within an application. Dependencies describe situations where one object or process must occur before another object can function as order. Consider the pressing need for online security. The authentication of individuals granted access to repositories is essential. Authentication uses a series of permissions specific to that container registry. Permission define who's authorized to use computer resources from a container registry. There is something called container runtimes that we already mentioned here. The concept of runtimes is vitally important. Container runtimes are software that lets containers operate within a host system. Container runtimes use a series of steps to carry out the creation of your environment, as guided by a container image that holds the app and its dependencies. Container images are a key component of container registry use. Fast deployment. Container images are intended and designed to hold everything required to run a container. Once container images have been created, all that's needed to run containers in the proper prompting from the computer system. This makes container image perfectly suited for quick implementation. Business priorities often change overnight. By having containers images created ahead of time, an organization can forecast all of its potential container needs, then later select the container best suited for that time and purpose. Container images give organization the ability to pivot as conditions dictate. Container image security is upheld through access control enforced by container registries. These include authentication protocols to ensure that non-authorized persona are denied access to container images. Images encryption is routinely used now to encode images and protect them from vulnerabilities. In this chapter, I will show you how can you install Visual Studio Code. But let's first learn what is VSC. Visual Studio Code, commonly referred to as VS Code, is an integrated development environment developed by Microsoft for Windows, Linux, macOS, and web browsers. Features include support for debugging, syntax highlighting, intelligent code completion, snippets, code refactoring, and embedded version control with Git. Users can change the DEM, keyboard shortcuts, preferences, and install extensions to add that functionality. Visual Studio Code is proprietary software released under the Microsoft software license, but based on the MIT license program named Visual Studio Code Open Source, also known as Code OSS, also created by Microsoft and available through GitHub. In the 2024 Stack Overflow Developer Survey, out of 58,121 responses, 73.6% of responders reported using Visual Studio Code, more than twice the percentage of respondents who reported using its nearest alternative, Visual Studio Code. Let's see how can we download and install VSC. Installation of Visual Studio Code is pretty simple. First, you need to go to code.visualstudio.com/download. You can choose from 3 options for Windows, Linux, and macOS. You can choose from system installer or user installer. I will choose my Windows 10. Then I will download this program. It's something more than 100 megabytes. When our download is finished, after that I will simply double click on this icon, accept the agreement, click on next, choose to create a desktop icon, click on next, and then I will click on install. I will not finish this installation, but you can do it if you click on install, because I have already installed my Visual Studio Code on my machine. And then I will just cancel this. If I run my Visual Studio Code, I have this some Terraform. Let's pretend that is not here. This is our Visual Studio Code, and then you can install extensions. For example, in this case, you need to install Docker extension. You will simply find Docker and install this Docker or dev containers, and that's it. Simply click on Docker and click on install. I already installed this, so I will not do it, but you can do it. Once that you install your extension, you will have this little icon here as Docker, as you can see, and this is Docker icon. So this is how can you install Visual Studio Code and install Docker extension. In the next chapters, I will show you how can you use Visual Studio Code and how can we build containers right from our Visual Studio Code. Thank you for watching. The next term we need to learn is what is a Docker Hub. Docker Hub is a repository service, and it is a cloud-based service where people push their Docker container images and also pull the Docker container images from the Docker Hub anytime or anywhere via the internet. It provides features such as you can push your image as private or public. Mainly, DevOps teams uses the Docker Hub. It is an open source tool and freely available for all operating systems. It is like storage where we can store images and pull the images when it is required. When a person wants to push or pull images from the Docker Hub, they must have a basic knowledge of Docker. So let's discuss the requirements of Docker tool. Docker is a tool nowadays enterprises adopting rapidly day by day. When a developer team wants to share the project with all dependencies for testing, then developer can push their code on a Docker Hub with all dependencies. Firstly, create the image and push the image on Docker Hub. After that, the testing team will pull the same image from the Docker Hub, eliminating the need for any type of file, software, or plugins for running the image because the developer team shares the image with all dependencies. Main use of Docker Hub. Efficient image management. Docker Hub simplifies the storage, management and sharing of Docker images, making it easy to organize and access container images from anywhere. Enhance security. It runs security checks on images and provides detailed reports on potential vulnerabilities, ensuring safer deployments. Automation capabilities. With features like webhooks, Docker Hub can automate continuous deployment and testing processes, streamlining your CI/CD pipeline. Integration and collaboration. Docker Hub integrates seamlessly with popular tools like GitHub and Jenkins and allows managing permissions for users and teams, facilitating efficient collaboration. Docker Hub offers a variety of web services designed to help developers manage, collaborate, and deploy container images effectively. This feature makes Docker Hub a useful platform for developers to store, manage, and collaborate in containerized applications throughout the development and deployment process. Here's a look at what it provides. Image repositories. Docker Hub primarily serves as a registry where you can store and access container images. you have the option to create both public and private repositories, browse official images, and upload your custom images. Automated builds. Docker Hub can link directly to code repositories like GitHub or Bitbucket to build images automatically. When you update your code, Docker Hub can build new images to keep everything in sync, making continuous deployment easier. Webhook integration on Docker Hub allows you to trigger specific action, such as deploying an image or sending notification whenever an image is updated. This can be useful for automating steps in CI/CD pipelines. Image scanning. Docker Hub offers security scanning for Pro and Teams accounts, which checks images for known vulnerabilities. This provides insight into any security risk within your images. Team collaboration. Docker Hub includes tools for managing users, teams, and permission within the organization, making it easier for teams to share and control access to Docker images. Official and verified published images. Docker Hub hosts trusted images from software vendors and the community. These verified and official images are reliable starting points for building applications. Activity monitoring. Each repository on Docker Hub includes an activity log. It records when images are pushed, pulled, or updated, helping you keep track on who accessed or modified your images. Also, you need to make a difference between GitHub and Docker Hub. So, in this table, you can see that primary purpose for GitHub is to code repository and version control. In Docker Hub, primary purpose is for Docker image repository and management. Content. In GitHub, you can store your source code or documentation. On Docker Hub, Docker container images. Integration. GitHub works with CI/CD tools like Jenkins, Travis CI. Docker Hub integrates with CI/CD tools and Docker itself. GitHub visibility have, just like Docker Hub, public and private repositories. And for security, GitHub use code scanning availability alerts. In Docker Hub, you have image security scans and vulnerability reports. So this is what Docker Hub is. Now it's time to know what is Dockerfile. The operating system or OS libraries and dependencies required to run the application source code, which is not reliant on the underlying operating system, included in the Dockerfile, which is a standardized executable component. Programmers may design, distribute, launch, run, upgrade, and manage containers using the open source platform Docker. Enterprise Edition and Community Edition of Docker are both available. The Enterprise Edition is for business and IT teams working on mission-critical production applications, while the Community Edition is suitable for small teams just learning Docker. The Dockerfile uses DSL or domain-specific language and contains instructions for generating a Docker image. Dockerfile will define the process to quickly produce an image. While creating your application, you should create a Dockerfile in order, since the Docker daemon runs all of the instructions from top to bottom. There are various Dockerfile commands or instructions. For example, from represents the base image OS, which is the command that is executed first before any other commands. Copy. The copy command is used to copy the file or folders to the image while building the image. Add. While creating the image, we can download files from distant HTTP or HTTPS destinations using the add command. Run. Scripts and commands are run with the run instruction. The execution of run commands or instruction will take place while you create an image on top of the prior layers or image. CMD or command. The main purpose of the CMD command is to start the process inside the container, and it can be overridden. Entry point. A container that will function as an executable is configured by entry point. When you start the Docker container, a command or script called entry point is executed. It can be overridden. The only difference between CMD and entry point is CMD can be overridden and entry point can't. The following are the stages of the creation of Docker from Docker file. First, you need to create a file name Docker file. Then you have to add some instructions in Docker file, build Docker file to create an image, and then run image to create a container. There is some benefits of Docker file: consistency and reproducibility. Docker file ensure that environment setups and dependencies are consistently facilitated across different setups, minimizing the host environment dependent issues. Version control. Docker files can be used for versioning along with your source code, and it helps in tracking the changes and rollbacks. And automation. It provides the automation with the process of building, configuring, and deploying the applications, with reducing the manual intervention and errors. These 6 commands are most frequently used, so if you want to learn more about commands in Docker file, you can find these commands on official Docker page. In the next chapters, we will use Docker file and some of these commands. How to run container in detach mode. But first, let's see what is detach mode. Detach mode lets you start the container and let it run in the background while you continue working on other tasks in your terminal. To run a container in detach mode, you need to use the D flag with the docker run command. For example, if you run the following command, like docker run /d nginx, the following command starts an instance of nginx web server in detach mode. That is something like docker run /d nginx, and you need to hit the enter. I will now hit my enter, but first I will need to add the sudo command, and let's run docker nginx. I will now add a password, and it is unable to find the local nginx latest locally, so it will pull from library, from Docker Hub library, nginx, and as you can see, we are completely downloaded this image, and this long string, as you can see here, is that you can see in the terminal, is our container ID. If we want to verify if the container is running, we can use the docker ps command. Let me try sudo again, docker ps, and which will list all the running containers. As you can see, we have our container ID, this is our image, this is our command, created, status, port, and names. I will have to give you one note that we can use the docker attach command to switch a container running in the detach mode in the background to a container running in the attach mode in the foreground. The command is primarily used to attach your local terminal session to a running container console, allowing you to see the output of the container process. If you, for example, run simple docker run container nginx command, it can happen that the container simply stop and won't have an output line in Ubuntu. What we can do is go to Docker desktop setting WSL integration, and if it not enable Ubuntu, and click on the apply and start. So if you, for example, run, as I already said, sudo docker run nginx, you can see that we have our process which is do not finished. What we can do is to go to our Docker desktop. As you can see, we have 2 containers that we created. This one is the first with -d, which run is detach mode, and this is our new one. What we need to do is to go to our Docker desktop, then I will go to settings, this little cog here, then I will go to VLS integration. Let's find where is VLS integration. Here it is in the resources. Let's click on VLS integration, and then you need to enable integration with addition distro. I will now toggle this on, and then we need to click on apply and restart to make this function enable. Then if we simply go to our container, as you can see, we are, or if you open a new command prompt, let's open a new command prompt, and here you can run we need to open a new Ubuntu, and if you run something like docker stop and the name of our container, the name of our first container is, let's go back to our containers, is Gallant Hamilton. Let me just see, and then run this command. You can see that we will see that in the first window that have been stuck we will have an exit command, but this will be an exit command here. But as you can see, if you go back to our desktop, you can see that our Gallant Hamilton is stopped. So this is how can you enable VSL integration or enable Ubuntu, and then you can click on apply and restart. And how can you create a container? If you go to images, you can see that we have our Nginx image, and we have two containers that we created, and our container is stopped. Simply docker stop and the name of our container that we created here. As you can see, this is the name of our container that we created. I will now stop. I will now leave this and type clear, just to clear and finish this demo. In Docker, all the applications in the container runs on particular ports when you run a container. If you want to access the particular application with the help of a port number, you need to map the port number of the container with the port number of the Docker host. The ports in Docker are essentials for enable communications between the Docker containers and the outside of the world via the internet. It helps in defining the endpoints through which services can be hosted within the containers and can be accessed by external entities. Docker uses port mapping to map the ports that are exposed within a container to ports on the host system. It allows the services that are running within the containers to be accessed externally via the host IP addresses or port number combination. So why we use port mapping? The network services of a container are made accessible to the host or external network through port mapping in Docker. Docker containers can only communicate with other containers on the same Docker network and run by default in isolation from the host and external networks. By publishing a container's network service to the host or external network through port mapping, you can make it reachable from other network devices. When running a container or Docker container, you can map a port on the container to a port on the host or external network using the flag P or publish options. If you use the command that we already use to publish nginx for instance, it will be published the port 80 from the container to port 8080, for example, on the host or external network. Let's see how can we add a container port number. Let's see how can we run a totally new command. For example, I will run sudo docker run, then D for detach, and the first time I will use -p, which is referring to port number, then I will add 80, this is the port, and 80 again, and let's see, for example, nginx. As you can see, we are getting the ID of our new container. So if we look in our Docker desktop, we can see that we are created a new container. So let's go to our Docker desktop, and we can see that we have interesting alien. This is our new container. This is our container ID. This is our image. As you can see, we have this nginx image here, and then we have this port number that we specified. Our container is running, and if we go back, this is our container ID, and if we go back, if you go to our browser, and for example, let's type here, and if we type localhost, you can see that we're getting a confirmation that we can locally start our nginx container, and we are getting this welcome message. Also, if I go back to my Ubuntu, I will, for example, run this sudo docker stop command, and if you want, you can add the first 3 letters or numbers of your container. So for me this is 004, and if I click on enter, I can stop my container. If we check in our Docker desktop, you can see that our container is in stopped state. If you go back to our browser and again type this, it will not be able to run this nginx. Let's try again, and if you can see, we are now in the incognito mode. Our local host is not being able to run. Also, if you want, you can run your containers directly from here. Simply click on start and your container will run from here. Also, you can click on stop and you can stop your container right from your Docker desktop. If I go back to my Ubuntu or WSL, let's see another command. For example, for stop and restart the container, you can use sudo docker stop and the name of the container. Let's write container name, and then of course I will get an error response because we didn't specify the container name. I just want to show you the basic commands. If you want to run the container, you can run with sudo docker run and container name. of course. If you want to if you need a help, you can run docker run -- help. Then, while running the container, you can again use the command below, docker run /p, and you can add a host port and the container port, and then add an image and tag. There is an option to update the container. If you wish to update the port mapping of a container, named by container to map, for example, port 8080 on the host to port 80 on the container using the command, for instance, you can map the container port to the host port by updating the container. For that, you will need to run sudo. Sudo is nothing but the super user in Ubuntu or Linux command. It will give you administrative rights. Then you will need to run sudo docker, then container, then update -- publish /add 80, for example 80. Just to remind you, the first 80 is the host port, the second one is container port, and your container name. And then you will run, as you can see, you will run your container. Then, if you want to use the Docker API, you can alter a running container port mapping using the Docker API, sending a post request with the new port mapping configuration in the request body to the container ID update to endpoint. Then you can publish Docker ports via /p, and the following commands map the host port to specific ports like TCP or UDP. You can try this. Let me first type clear. You can type this on your system. You can use Apache HTTP Docker image, for example, and then you will need to run docker. Let's first run sudo docker run /d /d is for detach, p is for port. Let's run, for example, 8080. This is our host port, and then we are adding our container port /tcp and image, for example. You can add your Apache, for example, or HTTP, and in that case you will run in TCP mode. If you want to run in UDP mode, simply just change this TCP to UDP, and you will need to add image name. Also, this D is to run the Docker container server in the detach mode. There is also an option to publish any range of ports to container, so you can run this by sudo docker run /d /p. Then you can, for example, add something like 8000, then /8004, and then you can add semicolon 4000 to 4004, for example, and then you need to specify the image. You can publish any range of ports to your container. Then another great solution is to publish random ports. Do not specify any port in the publish tag. This will publish some randomly chosen ports to all of the exposed ports of the Docker container application. Always remember, /P is in capital letter for this random allocation. So for this random ports, you can run this command sudo docker run /d /P and image name, and that's it. this is how can you publish random ports. I hope this was helpful. This was a little more advanced for now, but in the next chapter we will see go and see a quick look at Docker images, for example. But for now, this is how can you work with Docker images, with Docker with port mapping. I hope this was helpful, and for now just remember that /p is flag for adding a port. Thank you for watching. Docker image is an executable package of software that includes everything needed to run an application. This image informs how a container should instantiate, determining which software components will run and how. Docker container is a virtual environment that bundles application code with all dependencies required to run the application. The application runs quickly and reliably from one computing environment to another. So, what is a Docker image? Docker images are built using the Docker file, which consists of a set of instructions that are required to containerize an application. The Docker image includes the following to run a piece of software: application code, runtime, libraries, and environmental tools. A Docker image is a platform-independent image that can be built in the Windows environment, and it can be pushed to the Docker Hub and pulled by others with different OS environments like Linux. Docker image is very light in weight, so it can be portable to different platforms very easily. Let's talk about components of Docker image. The following are the terminologies and components related to Docker image. First is layers. This is immutable file system layers stacked to form a complete image. Then we have base image, the foundational layer, often a minimal OS or runtime environment. Docker file, a text file containing instructions to build a Docker file. Image ID is a unique identifier for each Docker image, and tags is a labels used to manage and version Docker images. Docker image build is a command that is used for building an image for Docker file. Docker image history, it is used for knowing the history of the Docker image. Docker image inspect, it is used for displaying the detailed information on one or more images. Docker image prune is used for removing unused images that are not associated with any containers. Docker image save, this command helps in saving the Docker image into a tar archive file. And Docker image tag, it helps in creating a tag to the target image that refers to the source image. So, Docker image is the Docker container source code. Docker file is a prerequisite to Docker image. Docker images can be shared between users with the help of the Docker registry, and to make changes in the Docker image we need to make changes in Docker file. Docker container is the instance of the Docker image. Docker image is a prerequisite to Docker container, and Docker containers can be shared between the users. We can directly interact with the container and make the changes required. The some structure of the Docker image is the layers of software that make up a Docker image, make it easier to configure the dependencies needed to execute the container. So, as I already said, base image will be starting point for the majority of Docker files, and it can be made from scratch. Parent image is the image that our image is based on. We can refer to the parent image in the Docker file using from command, and each declaration after that affects the parent image. Layers, Docker images have numerous layers. To create a sequence for intermediary images, each layer is created on top of the one before it. And Docker registry refer to this page on the Docker registry for further information. So, this was just a quick look at Docker images. Now it's time to see how can we create our first container. So we will run command from previous chapters, and see how it's easy to set up container on your local machine. But first, let's get a simple docker ps command. So in my Ubuntu, I will run docker ps, and as you can see, if we can see with this command if we have some running container on our system. If we want to see all container in our system, then we need to run a new command. Simple, type docker ps-a, and all containers will be shown in our terminal. As you can see, we have this container ID, image, command when it was created, status, ports, and names. This is default names of our container. And all of these containers are shown in our terminal. One way to stop the container is the docker stop command. And we need to add the first character of our container. For example, if I want to stop my container, I will run docker stop, and for example, first for container ID, which is 004 for my first container, for interesting alien. And then this container will be stopped. If I have more than one container that have the same ID, this 004, then I will add the fourth character in the command, which is C. Restarting the container is done with the docker start command and the first character of the container. So if I type docker start and this 004 characters from our interesting alien, this container will continue to run. But first, let's create our new container. It's very simple. I will run our command, which is docker run d for detach, p is for port, then we need to add our port name and the name of our container that we want to be created. This is nginx container, and as you can see, we are creating our container from simple image, nginx image. Now that we have a container created, we can try all the commands that I mentioned in this chapter. Let's try our docker start. So I will, for example, try first docker ps. You can see that we have this new elastic facial container created 20 seconds ago, and status is up and running. Then if I go and run docker ps-a, you will see all container in our system. First one is running and other three are not running. Then let's try to stop this running container, docker with command docker stop, and I will run these first three characters from our container ID, which is A46. And let's hit on enter. And after some time, our container is in stop state, so we can check this. If we type docker ps-a, as you can see, status is exited for our elastic facial container. And then if we want to start this container again, because it is in stop state, it is not necessary to type the port number that we type when we created this image or container from this image, because it is clear on which it is running, and it is only necessary to run the start command. So let's try docker start A46, and let's hit on enter. And if we check again our docker ps-a, as you can see, it's our first container is up and running. So in the following way, we can remove the container, but first we need to stop our container. Let's first go to our Docker desktop. As you can see, this is our Elastic Fistel container and it's running. It started 34 seconds ago. Also, you can stop this container if you click this stop button. Also, you can run one of these existing container if you click on this play button. But first, let's go to our terminal and let's stop this container. I will run docker stop and the name of our container, first three characters, A46. Let's hit on enter. Our container is stopped. Let's try and see that with docker ps-a status is exited 9 seconds ago, and then we can remove this container with simple command docker rm, which stands for remove, and then our container name or first three characters A46, and let's hit on enter. And if I try to run docker ps-a, you can see that we don't have this Elastic Fistel container. And then if I go to our Docker desktop, there is only 3 containers that we created 11 days ago. So this is just a simple exercise, and just wanted to show you how can you create your first Docker container and how can you run these commands to see your container, to see all container in your terminal, how to stop container, how do you start container, and how to stop and then remove your container. Thank you for watching. Knowing how to SSH into a container is as essential to using for debugging and operating containers on your local operating system or remote setup. To connect to a container using plain Docker commands, you can use docker exec or docker attach. Docker exec is a lot more popular because you can run a new command that allows you to spawn a new shell. You can check processes, file, and operate like in your local environment. Docker attach is more restricted because it attaches your terminal standard input, output, and error to the main process of a running container. Also, as I already mentioned, you can use SSH command, but you need to know your container IP address. Let's, for example, go to our terminal. Let's run our terminal. Let me clear this. And I will run simple command to create our Nginx container. Let's run docker run -d -p and Nginx, and this will create our new container. And then we can run, for example, docker pc. You can see that we have our container, and then I will run docker attach. Let's run docker, the last 3 characters of our container, so it's 5b a. If I hit on enter, you can see that our container is a hung state, so there is nothing what we do much here, but we can open a new Ubuntu terminal from our start menu. So let's go and do that. Let's run another Ubuntu terminal, and then we can run docker ps command for start. So you can see that we have our new container that we created earlier is running, and first we need to stop this container with docker stop and the first three characters of our container. So I will run docker stop 5BA and hit on enter, and as you can see, let's run docker pc, so we don't have any container that are currently running. After that, as you can see, our container will be in stop state. And then we can run another command with a new image, but this time I want to create an Ubuntu container, or Ubuntu if you want. So I will run new command, docker run. We already know that, but this time I will simply run Ubuntu, and let's hit on enter. It's unable to find our image locally, so this is pulling from Ubuntu library, and you can see it's creating our container, and after that we have another container. Let's check with docker ps command. We don't see anything, but if I run docker ps-a, you can see that this our Ubuntu container is exited 22 seconds ago. Why? This is because we are not running any server. This is just a simple Ubuntu container with operating system. When you run nginx container, it will run because there is a process that need to be run. If we check our Docker desktop, if I go to images, you will see that now we have nginx image and Ubuntu image, or Ubuntu image. Let me go to containers. You can see that we have our 4 containers based on nginx image, and this last one is based on our Ubuntu image. Let me go to our terminal, and then we can run new command with some new flags. Let's try docker run, and then I will add d for detach and it, and then I will run Ubuntu again. Let's run this. As you can see, our container is now running. Let's check it again, docker ps, and you can see that we have our container which is running. Also, let me explain this it flag. This means that A adds as stdin stream, and T adds the terminal driver. AT combines A and T, which allows you to interact with this process. AT flag is used to run the container in the interactive mode and also attach a pseudo terminal. Now, if you run command docker attach and 3, let me find, if you on your keyboard run this page up, you will see all of your commands that you used in this session. So let me try to find my, I don't have it, so let's try command docker, and then we will try characters of our new container, which is C98. Let's hit on enter. You can see that we are now logged inside our container as a root user, and now you can run some commands if you want. And for example, if I run ls, you can list all your folders, or for example top. This will help you to see all processes in your container. Also, this command will help you to explore this container. Also, if I type exit, you can see that we are exited from our container. And let's try again docker ps-a. You will see that we have our container which is exited 6 seconds ago, and I can again run my command if I want to run this container, and this container will create a new container. So let me try again docker ps. You can see that we have new Ubuntu container, and then you can also run whatever you want with this container. Let's check our Docker desktop. You can see that we have various Ubuntu and Nginx container. This is all based on our images. So if I go back to our terminal, you can see how it's easy to work with this option. There is another option. If you go inside your container, you can use your SSH command. First, you need to get an IP address of your container. The SSH client requires the server IP address to establish the connection, and you can do this by this command to obtain the container's IP address. First, you need to run docker ps, and you can see we have this Nginx container. I previously stopped this Ubuntu, and now we have our Nginx running. Then you need to find the container's name or ID. We can use with docker ps command, and then you can run docker inspect command. This is our command, as you can see. I will copy this to our terminal, and then you need to change your this or simply add these 3 characters, container ID. It is 5BA, and then I will run enter. So this is our address of our container. Then if you want to see if this address is reachable, you can run ping. For example, ping c-c3, and then you can run the name of your container. After that, you can see it is reachable, and once that you know IP address of your container, simply type SSH, your username of this container, at this 172.17.0.2, your address, and the system prompts for user password to connect to the container shell, and you will be able to work with the same thing, just like with this docker attach command that I already told you and show you how can you run this command, how can you go inside your command. So with docker run -d-it ubuntu, you can go inside your container, and let's stick to that. Just wanted to show you that is another way, and this is the end of this chapter. In this chapter, I want to show you how can you host your first web application on Docker container. So for this option, we need to download web server. You can choose between various web servers. I choose Apache. So if you want to download Apache web server for our local Windows laptop, we need to go to official Apache site, which is httpd.apache.org download, and then we need to download this official Apache server. I will go to files for Microsoft Windows. Let me choose my Apache launch, and then I will download this Apache latest version for Windows 64. Let's click on download and download this Apache. Official Apache server. And then, as you can see, this is our zip file, Apache zip file. And then we need to unzip, of course, this file. We need to pick a place that we want to unzip this file, and it is necessary that this file, it is clear that this file have all necessary files for work with Apache server on our local machine. Let me first unzip this. I will unzip to my desktop. Let's wait until this file unzip this archive. In the meantime, I will put this Apache in my C drive. I will simply drag and drop this folder, just waiting for completion of this unzip. Here it is. This is our Apache file. Let's find appropriate place. I will simply copy this Apache file on my C drive. As you can see, if I go on our Apache file that we just unzip, we have all necessary file and license to work with this on our local machine. Let me expand this just to be more precise. And then, if you go into Apache folder, we need to go to conf folder, and then we need to edit this http.conf. Let me open with edit in Notepad, and as you can see, if I scroll down, you need to define this. You need to edit this server root, so you need to add exactly the same path where this folder with this Apache folder is. If you copy this Apache file on some other location, then you will need to replace this location. Simply replace this location and you will be able to work with Apache. Our Apache is on our C drive, Apache 24, so it's okay. I will leave this as it is. Just wanted to show you that it is possible to edit this configuration file. Then we need to open command prompt from our Windows menu. Let me go to my Windows menu. I will run this as an administrator, and then we need to run following command. Let me first go to our C drive, and then I will run cd Apache 24 to get inside our folder, and then we need to go to our bin folder. Let's go to our bin folder, and finally I will run http command, pd command, to allow access. Hit on enter. So we are allowing access in our Windows firewall. Simply click on yes. So Apache is able to work on our local machine. If we, for example, go to our browser and try to type localhost, you can see that it works. So we are officially install our Apache, so we can run with this Apache server And that's it. This is our welcoming message from Apache on our Windows machine. If we want to host our application, there is a simple application. Just wanted to show you. Let me first open this simple app. This is a simple .html application. I found this on the internet, online. You can find whenever .html application do you want, or you can simply write your own. This is simple hello world application, and I name it simple app. If I open this application in my, let me open new, I will open a new file, go to desktop, and I will open this simple file. You can see that I have my simple app here, and now I will go to file and simply save this app. Let's go to desktop and save this as simple app 1 on my desktop. Let's click on save, and after that, if I go to my desktop and simply run this application, you will see this is our app. If I click, you click the button hello world. Okay, this is our simple application. And then I want this app to host on this Apache web server. So what we need to do? First, if we want to host this application in our Apache, let's go to our Apache folder. Then I will go up, and then we need to go to our htdocs, and then I will simply, you can delete or replace this index. Let me delete this index, which is official file of this Apache server. And then if you go back to our browser again, you will see that we don't have this it works message because we don't have our index app. But I will now copy my index app of my sample application, sample app or simple app, and then if you go back to our browser and open this new private window, I will simply type localhost /simpleapp1.html, and if I hit enter, you can see that we have our application which are running on Apache web server, but it is hosted on the Apache web server, but this is local. Let's click on hit me, and that's it. So this is how can you run your local app, simple.html app on Apache server on Windows machine. Thank you for watching. Of course, there is another way to host your web application, your first web application on web server, on Apache web server, but this time let's try to host this on our Linux operating system. This is our web app, as you already know, simple web app, and this is my terminal, Ubuntu terminal, WSL Ubuntu terminal. Now I will try to run this application on Apache server. Let's first try to update this package index. I will run simple sudo apt update to update our system. We need to add the password address, and As you can see, it's downloading all necessary packages to update our system. After that, we will install our, let's run again sudo apt full upgrade. I will hit yes, and then all these packages will be installed on our system. You just need to be patient, and then we will run next command, and we will install our Apache on our server. So in the meantime, I will remind you that we have this simple app application. This is HTML application. You see in the previous chapter how it looks like. And then after that, I will run next command, which is sudo apt install 2. Let's install. Click on yes to confirm it. We are now installing Apache server on this Ubuntu machine on our WSL, and then we need to change the permission of this HTML folder. I will run sudo. Sudo is just a super user command which gives you administrator right. Then we need to run chmod 777, so we are giving full permission to this folder, and then /var/www /html so we are giving full permission to this folder, and then we need to go inside our folder. Let me type cd /var/www/html, and then if I go to ls, you can see that we have this, just for a little to remove it here, we have this index.html, which is default for this Apache server. So we need to remove this index.html file. I will run sudo rm index.html and hit on enter. If we go to ls now, you can see that we don't have any index.html file, and then we need to go to our application folder, and we need to copy all files to our /var/www/html. It is very easy. Let me first go to our, so if I do ls, and then we need to go to our Apache folder, or we can go simply to our C drive and go to our C, /users I need to reach to my simple app. This is the folder, and then I will simply type simple app dot html. No such directory. Let me find something. This is where is my app reside. I will now simply paste the path. Copy path. Let's go to our browser, and then I will go and copy this. I made a few corrections. Simple, I go to my C drive, create a new application folder, and copy this simple app.index.html to that folder. Then you need to run cd/mnt/c/application. I am in that folder, and then if we do an ls, this is our simple app.html. So let's make it even more simply. Then we need to copy all these files from this folder to our /var/www/html. So I will run next command. So the only thing we need to do is to copy this simple app file to our /var/www/html file, and I will do this with cp-r-star, which means all recursive or all files, and then let me go to this /var/www/html folder. Finally, if I type ls, you will see that we have successfully copied our file, and then we need to go to our browser. Let's go to our browser. I will open a new private window, and then let me run localhost /simple app1.html, and we have our app, which is running on our Ubuntu machine. Just to remind you, we installed our Apache web server and then copy this our application on our Linux Ubuntu. And there is one more thing that we need to do. We need to stop this Apache 2 server, and we will do it with next command. Let me just go again to our terminal, and then I will run sudo systemctl stop Apache 2, and this system will now stop. So this is how can you host your first web app on. In the previous chapter we saw how can we run with our Windows machine, and if you are more Linux guy, this is how can you run your first web application on your Apache web server. Thank you for watching, and I hope this was helpful. In this chapter I want my application to run as a container, and for what we need to create our own Docker images that will run on Apache. So we need to open our Visual Studio Code and go to our folder where is our simple app1.html application in our application folder or some other folder on your hard drive. And then we need to create a new file. Let's go here and create a new file, and this file we will call Docker file. So to have this Docker file available, you need to install your Docker extension, as I already told you. Then in this file we need to specify a set of instructions how, as you already know in some of the previous chapters, Docker images that are placed in official Docker hub have this Docker file with a set of instructions, and then thanks to this Docker file you can create a container. If we want to build our own image in Docker, we need to specify a set of instructions in this Docker file. First command which I want to add is command from. This command is, as you can see, tell us from where we want to pull our base image, which is, and what image, which is resident on our Docker hub. So I want my application to run on Apache server, so I will run httpd, and then we need to specify the next command, which is the copy command. All we need to do is just to add this command. So I will now add this copy command, as you can see. Then I will type dash, and we need to add location of our Apache. Let's use this official command /user/local/ /apache2 /hd docs, and that's it. This is our simple from httpd file which is on our Docker hub. I will copy this to my local httpd docs. Let's save this file, and then everything we need to do is to save this file, and with the help of this Docker file it will pull the image and copy all files in our container. Let me now add a new terminal. I will go here and choose my Ubuntu WSL. So as you can see, we have this our WSL command. We are mounted that and everything we need to do to run the first command. You can do it from our Visual Studio Code or just from your Ubuntu terminal. I will run our command with docker build t stands for tag, and the name of our sample app 1, and at the end I will put a dot. Dot means that everything we have in our Docker file in our current directory, and I will run enter. So as you can see, in this way we have just created our Docker image. This is how can you create an image. And if we want to create a container from this image, you can run simple command. We already know this command. This is our Docker. But first, let me go to my Docker desktop. If you go to image, you can see that we have sample app1 as the latest image. This is our image. As you can see, this is our application running on Apache server. And then if we go back to our Visual Studio Code, I will run simple command to create a container from this sample app image. I will run docker run d for detach, p stands for port. We need to add our port and the name of our image. This is sample app1. And finally, our container is created. Let's go to our Docker desktop. If you go to containers, you can see that we have our gifted Raman, and it's created, it's running, and it's created on before 9 seconds ago. This is our image, this is our sample app image, and that's it. Let me, and as you can see, I'm in my Ubuntu terminal. So if you want to see the layer of your image, simply simply run docker inspect httpd. You can see all images of your Apache image, or simply you can run docker inspect sample app1 if you want to see layers of your image. Also, you can check and see, for example, let's try first docker ps -a we have our containers, which first is running, and this is the list of all of containers that resides on my local VM. Then I can run docker inspect and the first 3 characters of my running container. As you can see, this is our running container, and you will get your container in JSON file with all necessary information, so you can play around and see everything that you want. Also, there is an option to check your Docker info. For example, if you run this command, you can see all information of this Docker version, like client, context, Docker agent, so you can inspect even more further. So this is server containers is 8, running 1, paused 0, stopped 7. You have 3 images. What is our server version, storage driver, and so on. What is network bridge, and that all information which you need to know to understand how this works. Also, the last command I want to show you in this chapter is docker history, and then I can add sample app1, and then you can see all the necessary order, in which order we created our image, and then you can see what is our image created by copy with our user local Apache 2 htdocs, and then which command we run, and all other informations. So this is some bonus information of our command, but in this chapter, just to remind you, we created our own image, and then we created our container from that image. Thank you for watching, and I hope this was helpful. When working with Docker, it's often useful to assign a specific name to your containers. This can help you easily identify and manage your containers, especially when you have multiple containers running on the same host. When working with Docker containers, it's important to establish and follow consistent naming conventions to make your environment more organized and easier to manage. There is a lot of benefits of consistent naming conventions, like easier identification. Consistent container names make it easier to identify and locate specific containers. Improve collaboration. When working in a team, consistent naming convention help everyone understand and interact with the container more efficiently. Automated process. Consistent naming convention can enable the use of automated scripts and tools for managing containers. Here are some best practices for naming your Docker container. You can use descriptive names. Choose names that describes the purpose or function of the container, such as web server or database container. Then use lowercase letters to make the names more readable and consistent. Separate words with hyphens. Use hyphens to separate words in the container name, such as my-app-container, and avoid spaces and special characters. Spaces and special characters can cause issue with some tools and scripts, so it's best to avoid them in container names. Also, you can use a consistent prefix or suffix. Consider using a consistent prefix or suffix to group related containers, such as app, dash or db. Dash or dash db. So every time we run the command to create a new container in our Ubuntu terminal, for example, let's run docker run dash d dash p, and then we add our port name, and let's, for example, try nginx. We get a unique ID and some random name for our container. In one of the previous chapters, we already saw that we can use the first three characters of the container or its name. So, if I go now to our Docker desktop, you can see that we have some random name for our container. In this case, it is Boring Liskov, sorry. It is run based on nginx image. This is container ID, and this is the port that we allocated to this container. It was created 35 seconds ago, and it's running. In order to make it easier to work with our containers, it is possible to give a unique name for our container when we try to create our container. So, first thing, I will now stop this container. I can simply let me click on this icon in our Docker desktop. So I will stop this nginx Boring Liskov container, and then we will go back to our Ubuntu desktop, and first command that I want to run is docker images, and I can, with this command, I can list all the images that we have created in our Docker desktop. So we have sample app 1, nginx and Ubuntu. Then if we want to run a new container, to create a new container with the specific name that I want to add, we can run some command. But first you must try docker ps just to see. I don't have any container that is running right now, so we need to run docker run and then the new flag dash dash name. I will add name for my container, sample app. Let me try cont, and then dash d dash p, I will allocate this port and the name of my image. This is sample app 1. And finally, let's hit on enter. And here it is. As you can see, we have this new ID of our container. And let's try again. Let's go to our Docker desktop. As you can see, this is the container that, and the name of this container that I added during the creation of our new container. This is container ID, sample app image. Here is base sample app image. Allocated port is, as you can see, CPU used and last started 35 seconds ago. And then if I, for example, run docker ps, you can see sample is my sample, created 49 seconds ago, allocated port and the name of my container. Also, you can stop this container and check with docker ps. But there it is. It's very easy to add a name for your container, and there is also another catch that I want to show you. So if you want to automatically delete the container after it is stopped, so let's stop our container, docker stop, and I will now add a name, sample app -cont. Our container is stopped, so let me try docker ps command. Docker ps command. As you can see, we don't have any running container in our system. But now let's try to again run this container. Let me try docker start and then sample app -cont. Let's now try docker ps, and as you can see, my container is running. And there is another option. If you want to automatically delete the container after it is stopped, you can use the command, for example, docker, and then add rm for delete, then name, you add name of your container, and then simply add p8080 and, for example, nginx. If you run this command after you stop this container, it will automatically delete it. So let me first delete this message. So I will run docker ps. We have one image that is running. I will now try docker stop sample app cont1. Let's try docker ps. So we don't have any container that actually run, and then I will try, for example, docker run remove name. Let's add app1, for example, then d-p 8080, and let's add our engine X container. So as you can see, if I now go to Docker PS, we have one container that is running, and now if I run, for example, docker stop and add the name of my container, let's try Docker PS. So as you can see, we don't have any container that we created. So this is how can you automatically delete the container after easy stop with this --rm flag. Thank you for watching, and I hope this was helpful. Learning to properly tag Docker images in a production environment is crucial. Meaningful and consistent image tags are not only help users to identify and select the appropriate image version for their needs, but also enhance clarity and streamline workflows within the team. A tag is essentially a label assigned to a Docker image to help identify it. It typically consists of two components: image name, also known as a repository name, this is the name of the image, and tag. This is an optional identifier commonly used to represent a specific version or variant of the image. If tag is not specified, Docker automatically assigns the latest tag to the image by default. For instance, you can consider the tag Ubuntu 24.0. In this case, Ubuntu is the name of the Docker image, and 24.04 is the tag representing a specific version of Ubuntu. By using this tag, we can pull or run this specific version of the Ubuntu Docker image. So why is it important to tag a Docker image? When you're working with the Docker images on your local machine for your personal project, you might not think too much about their tags, but in a real-world situation where you have a big development teams and tens of hundreds of Docker images floating around, it's crucial to have a consistent and meaningful tagging strategy in place. Here are some of the reasons and benefits of tagging Docker images. First one is version control. Tagging Docker images allow you to maintain the different version of the same application, making it easier to roll back to a previous version if needed. This can be especially useful in cases when a new release introduces a bug or breaks compatibility with other components. Traceability and accountability. Tags provide a way to track the origin and history of an image, which is important for understanding the evolution of the application. This can help you identify when a particular change was introduced or who is responsible for a specific update. It simplifies deployment and automation. A consistent tagging strategy makes it easier to automate deployment processes and manage the application lifecycle. For example, a continuous integration and continuous deployment CI/CD pipeline can automatically build, test, and deploy new versions of the application based on the tags assigned to the Docker images. And it's easier for troubleshooting. A well-defined tagging strategy can help quickly identify the correct version of an application when issues arise. This can significantly reduce the time and effort needed to diagnose and resolve a problem. Then, when you create an image, when we create our image, we didn't specify the tag command, but by default, Docker assigned the latest image to the image that is created to us. If we, for example, go to Docker Hub and try to search some of the images, for example, Nginx. Let's go to our Nginx. You can see supported and the latest tag that you have, that you want or that you can use. So if you go to any other images, we will see that each of these has the latest image, and most of them have several tags for one image. As you can see, this is supported tags and respective Docker file links 1.27.4, and you can see all the latest tags for our Nginx server. As you can see, you can check this for yourself, and this is the recent tags. This is official Nginx image in Docker Hub. And then you can use one of these tags for one image. Also, the command that can be used to tag our sample app, let's go to our, let me clear my screen, and then the command that can be used to tag the, for example, let's try docker images command. So as you can see, we have our sample app 1, which is the latest tag. Have the latest tag. If you want to change this tag that we used in the prior version, you can now add a new one, and that it can reflect the application version accordingly. So I will type docker tag and then the name of our sample app 1 latest, and then I can simply add a new name like sample app version 1 and then hit on enter. And then if I run our Docker images, you can see that we have another version of our Docker images. This sample app is simply called sample app version 1. So you can add version 2, version 3. Every time that you change something on that app and create this image, you can create a new tag. Also, if you go to our Docker desktop and go to our images, you can see that we have our image that we just created. And then, if you want to remove the, for example, latest tag for that image, you can run simple command docker rmi, which stands for remove image, and simple sample app 1 dot version 1. This is just a simple app. Or latest sample app 1 and remove this latest. And then if you hit on enter, this will remove our sample app 1 image with the latest tag, and we will have only sample app version 1. I won't run this command because I need this image so we can move with our course. So this is how can you tag an image and change this tag to a new version, and then you can remove this prior version if you want with docker rmi command. Thank you for watching. Container logs are records of events and output generated by Docker containers on runtime. Each captures stdout and stdr streams of a single container, offering valuable insight into the container's behavior, performance, and potential issues. By default, Docker logs are JSON files located in the /var/lib/docker/containers directory of the host systems. Each file can run if you run, for example, container ID with the ID of the relevant container -json.log. A Docker log feature following elements: message, warnings, and errors generated by the application inside your containers. container OS data such as kernel message and system errors, and CPU memory and disk usage metrics. Container lifecycle data including start-stop times, configuration details and errors. Information on network requests and responses such as IP addresses, port and connection status, unauthorized access attempts, security vulnerabilities and other security events. What is a logging driver? A logging driver is a tool for capturing, storing and processing Docker container logs. The most common logging drivers is JSON file. By default, you can write JSON logs in JSON format and store them locally on the host machine, and syslogs. Send logs to a syslog server supporting centralized log management and analysis. And then journald writes logs to the systemd journal. gelf offers advanced log analytics and visualization by forwarding Graylog extended log format to the Graylog server, and fluentd sends log to a fluentd agent for flexible log processing and plugin based routing. The docker logs command instructs Docker to fetch the logs for a running container at execution time. It works only with containers utilizing the JSON file or journal driver. If you want to see a log or logs in our container, simply run command docker logs and the name of your container. But first, you need to see all dockers that run on our system. If we go to our Ubuntu terminal and run docker ps, you can see that we have one container that is running, and if we type docker ps-a, you can see all other containers that we have on our computer. So let's try to see the logs of this Gallant Hamilton container. I will simply type docker logs and the 3 characters of our running container. This is E76, and I will hit on enter. As you can see, we have all the necessary information that is possible to see. I will simply scroll up just for you to see how it looks like. And then the name of execution, start worker processes, when is shutting down, and so on. So this is how can you see the logs of your container, and you can also export them. Also, there is additional flags which can be used in a combination with the docker logs command. If you run docker, I will only, let me clear my screen first. If we run docker logs and then add -- details, you need to add your container name. For that, you can see additional log details. If you add, let's try another one. If you add, for example, follow or simply f and your container name, you can follow log output. Then another flag very useful is if you add since, you can display logs created after a specific timestamp. This option also accepts durations. Also, you can use tail command or simply n that specify the number of lines to show starting from the last line in the log. Also, there is an option to see timestamps. If you type timestamp or simply t, it will show timestamp. And then the last one I want to show you is until. It displays logs created before a specified timestamp. If you want to run databases in your local machine, you need to download, for example, MySQL. You need to download some additional software First, I want to run MySQL database. First, we need to download and install MySQL community server, and then we will install something called Workbench. First, I will choose this first option, Windows Server MSI installer. Let me download this. Let's click on no thanks, just install. We will now download this program. I will double click on this link. Let's click on next. I will accept the license. I will choose typical setup, install, yes. Then we need to run MySQL configurator. Let's click on finish. Once again, yes. And then I will click on next. We need to go through this wizard to be able to configure our recent MySQL server configuration. Let's click on next. Next again. Just to remind you, port is 3306 for our MySQL database or server. We need to add this root password and confirm our password. Let's click on next, next, and if you want you can add some sample databases. Just click on this box. Let's go to next, and finally we need to click on execute to apply this configuration, and simply wait for this to finish. And after some time, as you can see, we successfully configure our MySQL server, and then I will click on next and click on finish. So this is how can you install MySQL community server. As already mentioned, after that we need to install Workbench. I will go to different tab. This is MySQL community downloads. I will click this MSI installer, click on download. No thanks, just start my download, and then let's download our second software that we need to install. Double click on MySQL installer community. Let's click on yes. Yes, once again, and this is MySQL installer. Then here you need to choose the type that suits your use case. I will use this client only, and this will install some of the following, as you can see. Let's go to next, yes, and this will install MySQL Workbench and some other like shell and router. Let's click on execute to install our Workbench. So we need to wait for a little to this Workbench to be installed. You can track a progress here. So first we installed our MySQL community server, and now we are installing Workbench. And finally this is installed, and I will click on next, next again. This is our hostname, our port. Let's click on finish. Once again, let's click on finish, and start my workbench after setup and start my shell after setup. Let's click on finish. This is expected, and as you can see, we have our MySQL workbench. If you don't have this run, simply click on start and try to find your workbench. Here it is. Then if you want to connect to your workbench, simply click on this, create a new connection and add your password. The same thing we can install on our Linux machine. As you can see, I'm in my Ubuntu terminal, and then first we need to install our MySQL server. So I will run sudo apt install MySQL -server, and then I will add a password because we are running sudo. Let's click on yes, and we are installing our SQL server. Then we need to connect to our instance, but first we need to wait for this to be installed. And then we need to connect to our instance. I will run sudo MySQL. So we are in we are connected in MySQL instance, and then we need to set the password for the root user. For that, I already prepared this command: alter user root and localhost identified with native password by this is my password that we are specifying for this root user. Let me copy here and click on next. So after that we need to exit from here. I will type exit, and then you can now go and simply log to your MySQL client. But first, let's update our system. I will run sudo apt update, and then sudo apt full upgrade, yes. And this is how can you install MySQL to your Linux and your Windows operating system. In the previous chapter, I showed you how can you install MySQL community server, and then we installed something called Workbench that we can work with our MySQL database from Windows. Then we installed MySQL server on our Linux machine. We successfully connect to MySQL instance and add a password for the root user. And then in this chapter I will show you how can you create a container based on MySQL image from Docker Hub. But first we need to create a container based on MySQL Docker image. Let's first run Docker PC just to check if we have active container. We don't have any active container, and then I will run this command, docker run -- name. I will add the name for my SQL container. My SQL cont will be name of my container, and then I will add -e, which stands for variable, and my variable this time will be MySQL root password. MySQL underscore root underscore password, and then equal, and then I will add my password. This is the same password that I specified for Workbench and MySQL instance on Linux. Password is testing12356, and then we need to specify D and then P for port 803306. This is the port for MySQL, and then we need to add MySQL image and hit on enter, sorry. So it is unable to find it locally, and then it's pulling from Docker Hub official MySQL image, and after some time we can see that we just created our container based on MySQL Docker image. So let's try Docker PS. As you can see, this is MySQL image, and we are running this container based on this image. Let's, for example, go to our Docker desktop. You can see that we have MySQL container, and if you go to images, we have MySQL image. Let's go to our container, and if I want to log into this container, I can do it if I go to my Workbench. Let's go to our Workbench. I will click on new connection, for example, copy my host name. This is my local host 127.0.0.1, and then I will click on OK. This is our new connection. Let's click on our connection. We need to add our password. My password is testing1234556. Let's type again. Click on OK. Let's click continue anyway. As you can see, we are connected to our MySQL database thanks to the Workbench. So this is how can you connect to your MySQL database container, and then you can run a simple query right from here. You can create a table and so on. I will not go into much detail, just wanted to show you how can you create a database MySQL and how can you connect to this database thanks to this MySQL Workbench. Exactly the same thing we can do if you go to our Linux machine. And finally, if we want to log in to our container, to our MySQL database, you can use simple command. This is MySQL -h, and then we need to specify our local host address. This is 127.0.0.1. H stands for host, then -u. U stands for username. Our username is root, and then -p, which stands for password. So this is the whole command. MySQL -h, which stands for host. This is our host address. If you remember, exactly the same address or local host we used when we logged into our database, to our server using Workbench, this graphical tool, and then -u, our username is root and -p. When I hit enter, we need to enter our password, and our password is testing 1 2 3 4 5 6, and finally we are logged in our database, as you can see. And now you can work with your databases from Windows or from Linux. This is how can you create and work with your databases, and how can you create a container based on MySQL image from Docker Hub, and how can you connect to our MySQL container from Windows and from Linux machine. And now if you want to exit from here, simply type exit, and you can again run some Docker command right from your Ubuntu terminal. Thank you for watching, and I hope this was helpful. In this chapter I will talk about Docker networking. Docker networks configure communications between neighboring containers and external services. Container must be connected to a Docker network to receive any network connectivity. The communication routes available to the container depend on the network connection it has. Docker comes with 5 built-in network drivers that implement core networking functionality: bridge, host, overlay, IP LAN, and MAC VLAN. Let's talk about these 5 drivers that are implemented in networking functionality. First one is bridge. Bridge networks create a software-based bridge between your host and the container. Containers connected to the network can communicate with each other, but they are isolated from those outside the network. Each container in the network is assigned its own IP address because the network bridge to your host containers are also able to communicate on your LAN and the internet. They will not appear as physical devices on your LAN, however. Then we have host. Containers that use the host network mode share your host network stack without any isolation. They aren't allocated their own IP addresses, and port binds will be published directly to your host network. This means a container process that lists on port 80 will bind to your host IP and then 80. Overlay networks are distributed networks that span multiple Docker hosts. The network allows all the containers running on any of the hosts to communicate with each other without requiring OS-level routing support. Overlay networks implement the networking from Docker Swarm clusters, but you can also use them when you're running 2 separate instances of Docker image with containers that must directly contact each other. This allows you to build your own swarm-like environments. IP VLAN is an advanced driver that offers precise control over the IPv4 and IPv6 addresses assigned to your containers, as well as layer 2 and layer 3 of VLAN tagging and routing. This driver is useful where you're integrating containerized service with an existing physical network. IP VLAN networks are assigned their own interfaces, which offer performance benefits over bridge-based networking. And the last one is MAC VLAN, is another advanced option that allows containers to appear as physical devices on your networks. It works by assigning each container in the network a unique MAC address. This network type requires you to dedicate one of your host physical interfaces to the virtual network. The wider network must also be appropriately configured to support the potentially large number of MAC addresses that could be created by an active Docker host running many containers. So, which network type should you use, or we use? Bridge networks are the most suitable option for the majority of scenarios that you'll encounter. Containers in the network can communicate with each other using their own IP addresses and DNS names. They also have access to host network, so they can reach the internet and your LAN. Host networks are best when you want to bind ports directly to your host interfaces and aren't concerned about network isolation. They allow containerized apps to function similarly to network services running directly on your host. Overlay networks are required when containers on different Docker hosts need to communicate directly with each other. These networks let you set up own distributed environments for high availability. Mac VLAN networks are useful in situations where containers must appear as a physical device on your host network, such as when they run an application that monitors network traffic. IP VLAN networks are advanced option when you have specific requirements around containers' IP addresses, tags, and routing. Docker also supports third-party network plugins, which expand the networking system with additional operating models. These include Courier, which implements networking using OpenStack Neutron, and Viv, an overlay network with an emphasis on service discovery, security, and fault tolerance. Finally, Docker networking is always optional at the container level. Setting a container network to none will completely disable its networking stack. The container will be unable to reach its neighbors, your host services, or the internet. This helps improve security by sandboxing applications that aren't expected to require connectivity. How Docker networking works. Docker uses your host network stack to implement its networking system. It works by manipulating IP tables rules to route traffic to your containers. This also provides isolation between Docker networks and your host. IP tables is the standard Linux packet filtering tool. Rules added to IP tables define how traffic is routed and it passed through your host network stack. Docker networks add filtering rules which direct matching traffic to your container application. The rules are automatically configured so you don't need to manually interact with IP tables. Docker containers are assigned their own network namespace, a Linux kernel feature that provides isolated virtual network environment. Containers also create virtual network interfaces on your host that allow them to communicate outside their namespace using your host network. The details of how Docker networking is implemented is relatively complex and low level. Docker abstracts them from end user, providing a seamless container networking experience that is predictable and effective. Let's look at some simple Docker commands now that you know what is networking and how it works in Docker. Let me clear my screen first. I will type clear to clear our screen. If you want to see the list of all networking or networks which we have in our Docker in our system, we need to type Docker network ls, which stands for listing. As you can see, we have our list of our networks and including bridge, which is default. If we type, for example, docker inspect and some name of our container, let's go to our Docker desktop and find some container. Let's type MySQL cont, for example. We are getting our container in JSON file, and in this JSON file you can also see the IP address of our container. If I scroll down, you can see that gateway address is 172.17.0.1 and IP address of our container is 172.17.0.2. Docker offers us possibility to create our own network, so we can run a new command like docker network create and simply add the name for your network. Let's add a name for our network, something like my net. as you can see, this is our network, and now I will run again docker network ls. As you can see, we have my net, which is also bridge driver, and this is our local network, and then our network is on the list. Now it is possible to attach this network to our container. We can do that if you run next command, docker network connect, and then we need to specify the name of our network, which is my net, and simply the address of our container, which our container is names, just to see, MySQL cont dash cont. So in this command, just to remind you, we run docker network connect, the name of our network, and MySQL cont is the name of our container that we want to connect to this network. Let's hit on enter, and then if we type docker inspect and the name of our container, MySQL dash cont, we can see that we have our network associated with our network, and also we have new IP address, as you can see. Again, we can make a new container with the name of this network, and we can run, let's first type docker images. So we have this sample app 1, and I will try to configure a new container, but first let's stop our actual container, docker stop MySQL dash cont. Our container is stopped. Let's check this again. We don't have any running container, so we can create a new container with command docker run dash dash name. I will add this as sample app 2 or sample app cont 2, and then we need to add the dash network. I will add my net. As I remember, this is our name of our networking, my net, of course, and then I will type /d/p, and we need to specify the number of our host and port, and then our image is sample app 1. Let's hit on enter, and if I run docker ps, you can see that we have our sample app. Let's now go to docker inspect, and I will add sample app dash cont 2, we can see that we have our network attached to, as you can see, my net is our network mode. This is our network that we attached on this container. So this new container is just of this network. So this is how can you create a new container and add this network in your container. So this container is part of that network. Let me now clear my screen, and that's it for this chapter. Thank you for watching. Docker is the most popular platform for building and running software containers, sandboxes environments that are similar to virtual machine, but share your host operating system kernel. Containers have their own file system that contain the package, source code, and dependencies necessary for an application to run. Occasionally, you want to transfer files between your host and a container file system. In this chapter, we will talk about Docker CP or Docker command. The Docker CP command allows you to copy files and directories to and from your Docker containers, similar to Unix CP, but with some differences and limitations. You can use it whenever you need to interact with a container's context. Its a basic syntax is similar to a regular CP or copy. Simply add Docker, source and destination container. The content and the path referenced by src will be copied to dest. src and dest can either reference a path on your local file system or one within a container. Container references use container path syntax where container is the container ID or the name and path is within the container file system. The command can either copy to a container from your host or from a container to your host. It's not possible to copy files directly between containers. However, you can easily achieve this yourself by running Docker CP twice. Let's understand Docker CP behavior. Compared to Unix CP, Docker CP or copy command has a few significant differences in how it handles the destination path. The behavior varies depending on whether you're copying a file or directory. For file copies, the destination can be either a new file path or an existing file or directory. If a directory path is given, then the file will be copied into that directory. When a new path is given, then the directory must already exist. For directory copies, a new directory will be created if the destination path doesn't already exist. If the destination does exist, then the new directory will be copied into existing one, unless the source path ends with slash. Then content of the source directory will be copied into existing destination directory. So when do you want to use this Docker CP command? The Docker CP command is useful in several scenarios where you want to interact with a container file system. If you want to debug container issues, you can diagnose problems with container as a PS by copying out logs traces or other generated files that help you troubleshoot. Copy out or backup store files. Many containers create persistent data when they're used, such as uploads to a web application. Docker CP lets you make copies of these files on your host, ensuring you have a separate backup before you make changes to your container's deployment. You can make config file changes. Some of apps dynamically read their configuration files, so you can use Docker CP to copy in new values without having to restart the container. In general, it's best to avoid using Docker CP to apply changes to your container. Manually altering container file system is often an anti-pattern because it can cause drift compared to the container image. Your copied files will also be lost when the container restarts unless the destination path is bound Docker volume. To summarize, you can safely rely on Docker CP to copy files out of container. This simplifies common development tasks and makes it easier to experiment. However, if changes are required to a container's file system, then you should consider rebuilding the image to include your new files, unless you are only modifying config values or other persistent data that are stored in your value. So, if you want to copy files, simply use Docker CP, your source container and your destination container. When you use a bind mount, a file or directory on the host machine is mounted from the host into a container. By contrast, when you use a volume, a new directory is created with Docker storage directory on the host machine, and Docker manages that directory contents. When we want to use this bind amount, bind amounts are appropriate for the following types of use cases: sharing source code or build artifacts between a development environment on the Docker host and a container. When you want to use to create or generate files in a container and persist the file onto the host file system, and when you want to sharing configuration files from the host machine to containers. This is how Docker provides DNS resolution to containers by default by mounting /etc/resolve.config or conf from the host machine into each container. Bind mounts are also available for builds, so you can bind mount source code from the host into the bind container to test, lint, or compile a project. With bind mounts, we can control exact location or the mount point on the host to store the data. Bind mounts are basically used to provide additional information to the container, such as adding source code to see the changes and let us see the changes right away. Just like node-based application that have node daemon, which is a great tool to watch for changes in the application and then restart the application after saving the file. Mounting an Azure file share to a container instance is similar to Docker bind mount. If you mount a share into a container directory in which files or directory exist, the mount obscure files or directories, making them inaccessible while the container runs. With bind mounts, a file or directory in a host, such as an Amazon EC2 instance, is mounted into a container. Bind mounts are supported for tasks that are hosted on both Fargate and Amazon EC2 instances. Bind mounts in Linux enable you to mount already mounted file system to another location within the file system. Generally, bind mounts are used when restricting the access of specific users to designated parts of a website by replicating the website into directory into a jailed user's home directory. To create a bind mount, we can use either --mount or --volume flag. So you can run two commands. Let's try one. For example, docker run, and then you need to add --mount, then type equal, then you can specify bind, and then source equal, and then you can add your host path, and then after that destination path, container path. And also you can run exactly the same, docker run --volume. You can add your host path and simply add this container path. In general, mount is preferred. The main difference is that mount flag is more explicit and supports all the available options. If you use --volume to bind mount a file or directory that does not yet exist on the Docker host, Docker automatically creates the directory on the host for you. It's always created as a directory. Docker containers are easiest to use with stateless application because their file systems are ephemeral in nature. Changes made to a container's environment are lost when the container stops, crashes, or gets replaced. You can Dockerize stateful application such as databases and file servers by attaching volumes to your container. Volume provide persistent storage that is independent of individual containers. You can reattach volumes to a different container after a failure or use them to share data between several containers simultaneously. Volumes are a mechanism for storing data outside containers. All volumes are managed by Docker and stored in a dedicated directory on your host, usually on /var/lib/docker/volumes for Linux systems. Volumes are mounted to file systems path in your containers. When containers write to a path beneath a volume mount point, the changes will be applied to the volume instead of the container's writable image layer. The written data will still be available if the containers stop, as the volume is stored separately on your host. It can be remounted to another container or accessed directly using tools. Volumes work with both Linux and Windows containers. Several different drivers are available to store volume data in different services. Local storage on your Docker host is the default, but NFS volumes or CIFS/Samba shares and device-level block storage adapters are available as alternatives. Third-party plugins can add extra storage option too. So, let's talk about bind mounts versus Docker volumes. Bind mounts are another way to give container access to files and folders on your host. They directly mount a host directory into your container. Any changes made to the directory will be reflected on both sides of the mount, whether the modification originates from the host or within the container. Bind mounts are best used for ad hoc storage on a short-term basis, and they are convenient in development workloads. For example, bind mounting your working directory into a container automatically synchronize your source code files, allowing you to immediately test changes without rebuilding your Docker image. Volumes are a better solution when you are providing a permanent storage to operational containers. Because they are managed by Docker, you don't need to manually maintain directories on your host. There's less chance of data being accidentally modified and no dependency on a particular folder structure. Volume drivers are also offer increased performance and the possibility of writing changes directly to remote locations. So when you want to use these Docker files or volumes, volumes are designed to support the deployment of stateful Docker containers. You'll need to use a volume when a container requires persistent storage to permanently save new and modified files. Typical volume use cases including database storage. You should mount a volume to the storage directories used by databases such as MySQL, Postgres, and Mongo. This will ensure your data persists after the container stop. Application data generated by your application such as file uploads, documents, and profile photos should be stored in a volume. Essential caches. Consider using a volume to persist to content of any caches which would take significant time to rebuild. Convenient data backups. Docker's centralized volume storage makes it easy to backup container data by mirroring -var-lib-docker-/volumes to another location. Community tools and Docker desktop extensions can automate this process, providing a much simpler experience than manually copying individual bind mounted directories. And you can share data between containers. Docker volumes can be mounted to multiple containers simultaneously. Containers have real-time access to the changes made by their neighbors. And you can write to remote file systems. You'll need to use a volume when you want containers to write to remote file systems and network shares. This can facilitate simpler workflows for applications that interact with your line resources. You don't need to mount a volume to containers that don't have writable file system path or that only store disposable content. As a general rule, create a volume when you container writing data which will cause disruption if it's lost. So, the first thing I want to do is to check if I have any container that is running. Yes, I have one, so I will run docker stop 8e2. So let's run docker ps again. As you can see, I don't have any container that is right now running. And then I will create a new container. But first, let's go to our Docker desktop and remove our simple app cont. And I will delete this forever. Then, in our Ubuntu terminal, I will create another container from our sample app image. Let's run docker run d/p 8080, and then we need to add our image. This is our sample app 1, and if I run docker ps, you can see that we have our new container with a random name. And then we can run docker volume ls command to see every volume that we have on our system. Let's try that. Docker volume ls. So we have only one local volume, and this volume is automatically made by Docker. If we want to make or create our own volume, we can do it by running a simple command. Let's try docker volume create, and then I will add a name for this volume. So for example, I will add volume 1, and let's hit on enter. Then if we run again docker volume ps ls, we can see that we have now our volume 1 name. Then this new created volume, this volume 1, we can add to our container, and we can run a new container. For that, I will simply stop or remove this container. First, let's type docker stop, and we need to find 72d. Our docker is stopped, and then let's run docker mrm to remove this container 72d. Let me now try docker ps. As you can see, we don't have any container that is running, and now I will create a new container with this volume. Let's run docker run command /d/p 8080. Then I will add a name. Let's add my app 2 -v, which stands for container, for volume. Let's add a name for our volume. This is volume 1, and then we need to specify exactly the same folder, HTML, and then sample app1, which is our image app, our image name. And finally, let's hit on create. Then if you go to our Docker desktop, let's go to our Docker desktop. If you go to volumes, you can see that we have volume blade, and we have two volumes. One is created by Docker automatically, and one is our. You can also go to inside this volume, and if you go to container issues, you can see that our container app is using this volume, so this volume is now attached to our container. So this is how can you create a new volume, and how can you add this volume to your container. Of course, we can add this container to our, for example, MySQL image, you can run exactly the same command. So let's simply change this to my app3, and we need to specify different address and simply change our name of our image, and then your MySQL container will have this volume attached to it. So that's it. This was our demo on how can you create a volume and how to add this volume to our new container. Thank you for. If you want to see the size of our images, we can do that with the Docker images command, and all our images will be displayed by name, and among the data will be the size. There are official versions of the image that contain the addition of Alpine, and they are of a smaller scale, size, and serve us to create the necessary image very quickly. All these images are located like the others in the Docker Hub and can be used. Docker Alpine is one of the hundreds of publicly available container images that you can use to host applications or as base images for creating your own container images. However, Docker Alpine provides some special benefits that most other container images lack. It's extremely lightweight. The Docker Alpine images weight at under 3 megabytes and require less than 100 megabytes of RAM to run. This makes it fast to download. It also means that Docker Alpine places minimal load on your system. It has package manager. Unlike some other lightweight Linux distribution, Alpine provides a package management tool called APK that makes it easy to install additional software beyond what's included by default. This is particularly useful if you want to use Docker Alpine as a base image for packaging your own app inside a container, but you need to install additional libraries or utilities for your app to run. It's a fully open source. Docker Alpine, like Linux as a whole, is completely free and open source. This means that you can use Docker Alpine and distribute modified versions of it as a part of your own container image without worrying about paying licensing fees or violating any licensing terms. To be sure, Docker Alpine isn't always the best option. If you want to run containers inside a more traditional Linux environment, then provide more libraries and utilities by default. It will be better served using images based on distributions like Debian or Ubuntu. As an extremely lightweight distribution, Alpine Linux is a popular option for developers who want a simple, resource-efficient environment in which to run containerized apps. Downloading the official Docker Alpine image is fast and easy, as long as you're familiar with basic Docker commands and the Alpine package manager. You can easily modify Alpine to suit your needs. Don't forget that the size of the image is very important when working into containers, and precisely Alpine and other tags give us the opportunity to create and run our containers with minimal operating system that has only the necessary files and serves very well and does not take up much space. If you run Docker images in your Ubuntu terminal, you can see the size of your images. Of course, these images is much lighter when you use Alpine option or some other option which you can find in official Docker Hub. Also, my sample app 1 is only 2021 megabytes, and from that, as you remember, in this image we host our application, our HTML application that run on Apache server. So this is how can you check a size of your image or images, and why is good to use Alpine in some cases. Docker Compose is a tool that makes it easier to define and manage multi-container Docker applications. It simplifies running interconnected services such as front-end, back-end API, and database, and by allowing them to be launched and controlled together. Using a YAML configuration file, typically docker compose.yaml or YAML, you can describe each service and its dependencies as code. This setup can be committed to your source repository for consistent deployment. Once defined, all services can be started with a single docker compose command, making it easier to coordinate development or testing environments. Compared with manually starting and linking containers, Compose is quicker, easier, and more repeatable. Your containers will run with the same configuration every time. There is no risk of forgetting to include an important Docker run flag. Compose automatically creates a Docker network for your project, ensuring your containers can communicate with each other. It also manages your Docker storage volumes, automatically reattaching them after a service is restarted or replaced. Most real-world applications have several services with a dependency relationship. For example, your app may run in one container, but depend on a database server that's deployed adjacently in another container. Moreover, services usually need to be configured with storage volumes, environment variables, port bindings, and other settings before they can be deployed. By using Docker Compose app, you can spin up the entire stack with one command, ensuring consistency across environments. For example, a web app with a backend database and Redis cache can be launched together without separate configuration for each container. Using Compose to bring up the stack starts every container using the config values you set in your file. This improves development ergonomics, supports reissue of the stack in multiple environments, and helps prevent accidental misconfiguration. While tools like Kubernetes offer more advanced orchestration features for production environment, Docker Compose remains a valuable tool for a local development, testing, and simple deployment, especially for smaller applications or teams. What is the difference between Docker and Docker Compose? Docker is a platform used to build, run, and manage containers, while package applications with their dependencies. Docker Compose, on the other hand, is a tool that simplifies the definition and management of multi-container application using a docker compose.yaml file. While Docker handles individual containers, Docker Compose is used to configure and run multiple containers as a single service step. You can use Docker without Compose, however, adapting Compose where you're developing a containerized system allows you to deploy your app in any environment with a single command. Whereas the Docker CLI only interacts with one container at a time, Compose integrates with your project and is aware of the relationship between your containers. If you want to check a version of your Docker Compose, then you simply run Docker Compose version. If you remember from one of our previous chapter, we use this simple .html application to create our image. And now I want to try to run Docker Compose, but first let's check a version of our Docker Compose. For that, in my Visual Studio Code, you need to select your WSL Ubuntu for your terminal, and then we can simply run command docker compose version. As you can see, this is our Docker Compose version is v2.34.0 desktop 1. If we want to work with Docker Compose in our Visual Studio Code environment, we need to create a new file. I will hit this new file, and then let's add Docker name for this file, docker compose.yaml, and hit on enter. So as you can see, now I can add my docker compose YAML, and I want to specify all the information to run this file. First, I need to add version. For example, 3.8. Then we need to add services, then web app, then we need to add our image. Our image is, if you remember, sample app 1. This is our image. Just let's check our image in our Docker file. Sample app 1. And then we need to add ports. I will type ports, and port is 80. And this is our Docker compose YAML file. And now I will go and save this, and in our terminal let's run docker compose up-d and hit on enter. As you can see, network application is created and container app web app 1 is started. If I go and check docker ps, we can see that we have our new container called docker application -web app 1. If we go to our Docker desktop and check our container, you can see that we have created our application, which is web app, simple web application. So this is how can you work with the help of Docker Compose. Of course, I have only one image that I use here, but you can try with other images. So I hope this was helpful. Thank you for watching. In Docker Compose, depends on field is used to express the dependencies between the services of an application, and it can specify the order in which these services should be started or stopped. By default, Compose only ensure that the services listed under the depends on property are started before the dependent service. This means that Compose doesn't guarantee that these services are fully operational and ready to process requests, but only their containers are running. It is, however, possible to set conditions to define when one service should start or wait for another service to reach a specific state. These conditions are defined in the condition property and take three possible values: service started, service healthy, and service completed successfully. The service started condition is the default condition which is used by Compose and only checks whether the service container has started without verifying the service internal state of health. The service healthy condition is used to ensure that not only that service container has started, but also that the service inside the container has successfully passed a health check. It ensures that service is fully operational and ready to accept requests. It is often combined with health check property that allows developers to define a custom health check for a given service. The service completing successfully condition is used to ensure that the service container not only start and run, but also complete in execution successfully. It's useful in scenarios where the dependent service is a one-time job or task, such as a data migration script, and you want to make sure it finishes without errors before starting another service. To use service completing successfully, you should ensure that the dependent service exit with a zero status code upon successful completion. When set to true, the restart property allows you to manually or automatically restart the depending service whenever you perform a manual restart or operation using the Docker compose command. It's important to note that this setting doesn't affect the automated restart policy defined in the service itself that is typically managed by the container runtime when the container exits unexpectedly. Depending on external services, this depends on property only works with services defines within the same compose.yaml file. If your application relies on external services like a database hosted on a remote server, you will need to implement a custom retry logic in your application to handle dependencies gracefully. Just a quick follow-up. In your docker compose.yaml file, you have an option to simply add depends on clause. If we type depends on clause, and then you can add your condition if you want for another container and then conditions. In the condition property, you can add possible values for service started, service healthy, and service completed successfully. Just a quick follow-up, and I will not use this depend on clause, just want to understand how it can be used. In this chapter, I want to show you how it's possible to create a Docker Hub account and how to create a repository and image, and how can we add this image to our Docker Hub account. But first, we must use Docker Compose with simple command. First, let me go to my Visual Studio Code and I will run simple command with Docker Compose down. And as you can see, container application web app is removed and network application default is removed. So we are now in our regular mode, and then let's try to sign in to my Docker. If you don't have account, simply click sign up, and it will offer you to create your account. Simply put your work or personal address, your email, username, password, or you can sign up with your Google or GitHub account. Let me sign in with my username and password. I will click on continue, and after some time I will be logged in as my Vlada Rems in my Docker Hub account. As you can see, I have one repository and one simple image that I used for some testing before 10 months ago. Then, because we want to add our image from our local machine to this Docker Hub, we need to create a new repository. Let's hit on create repository. I will type sample app1, and in this short description this is my Apache and HTML application. And finally, you can choose between public and private. As I already told you, this repository must be public because we are using free version. If you want something more, then you need to buy one of these Docker Hub plans. So Docker Hub repository is a collection of container images, enable you to store, manage and share Docker images publicly or privately. As you can see, I am choosing this to be public. Let's hit on create. So we are creating our tag or our repository, and automatically this is my username, and we are getting this vladarams -sample app1. I don't have any image that I added to this repository, but as you can see, each repository can serve as a dedicated space where you can store images associated with particular application, microservice or project. And as you already know, I already logged in to my Docker Hub account, but we need to log in from our Ubuntu terminal. Let's go to our Ubuntu terminal, and from there we will be run Docker login. Hit on enter, and login succeeded. As you can see, if you want to log in with a different account, simply run docker logout and followed by docker login. Now the next step is to tag our images that we have locally on our laptop, and we can do this by command docker. As you can see, I already used docker images, so we have this. Let's run again docker images. This is my images. I want this sample app1 to add to my Docker Hub, to publish to my Docker Hub. So I will run a special command. First we need to tag our image. Let's type docker tag sample app1, and then I need to add my repository name, and my repository name you can see from here. We are successfully tagged our image, and vladarams is simply name of our Docker, is my username on my Docker Hub account, and this /sample app1 is our image from here, as you can see. Then finally with the command docker push, and then we need to run vladarams /sample app1. We can publish our image in our Docker Hub. Let's hit on enter. As you can see, we are now pushing our image from our local machine to the Docker Hub. So if you go to our Docker Hub, let's see if we successfully published our image. I will now go to our sample app, and you can see this is our latest image, and now it's we publish this image in our repository that we created earlier. This is my Apache and HTML application. OS type is Linux, tag is latest. This is my image, where is this pulled and pushed. And then you can see this is our command. If I go to latest, you can see all image layers that I used, and this is all layers. You can see environment, run, work there, run, and all the processes that we used here. If I go to repositories, you can see that I now have two repositories, and first one is my simple website and second one is Vlada Rem's app 1. So this is how can you publish your image from your local laptop to your Docker Hub. In the previous chapter I show you how can you publish your image from your local machine to your Docker Hub. And now I want to run a container from this Docker Hub Vlada Rems / sample app 1. But first we need to delete all images that we have on our local system, so I can run in my, let me find my Ubuntu terminal. I can run, for example, Docker images, and now I will delete with Docker RME sample app 1, or simply we can do this in our Docker desktop. Let's go to Docker desktop and I will simply delete all of my containers, as you can see, and in the images I will delete all of my containers and then images. As you can see, I don't have any container images and I have only this volume 1. It can stay, it really doesn't matter. So if we now run in our terminal, if I clear the screen, I can run simple command docker run /d/p. You already know how to run this, and then we need to add our host number, host port and our port 80, and then I will simply add the name of our image from our Docker Hub, and this image is Vlada Rems / sample app 1, and before I hit enter, you can see if we go to our Docker Hub, this is our image that I want to run, and let's hit on enter. As you can see, it's unable to find it locally. It's pulling from our Docker Hub, and let's try Docker PS. You can see that we now have our container which is running, and if I try with Docker images, we have our latest image, and we can check also if we go back to our container in our Docker desktop. You can see that we have our container, and if we go to images, we have our image. So this is how can you run a container from Docker Hub. A Docker Swarm repository is a collection of container images enabling you to store, manage, and share Docker images publicly or privately. Each repository serves as a dedicated space where you can store images associated with a particular application, microservice, or project. A Docker Swarm is a container orchestration tool running the Docker application. It has been configured to join together in a cluster. The activities of the cluster are controlled by a swarm manager, and machines that have joined the cluster are referred to as nodes. In Docker Swarm, there are typically several worker nodes and at least one manager node that is responsible for handling the worker node resources efficiently and ensuring that the cluster operates efficiently. Docker Swarm is still included in Docker CA, but there is a longer software as a service for Docker Swarm. Docker Swarm has two types of services, replicated and global. Replicated services. In Swarm mode, replicated services function based on a specific number of replica tasks that the Swarm manager assigned to available nodes. Global services function by using the Swarm manager to schedule one task to each available node that meets the global services, constraints, and resource requirements. A Docker Swarm is comprised of a group of a physical or virtual machine operating in a cluster. When a machine joins the cluster, it becomes a node in that swarm. In a Docker Swarm, there are typically several workers node and at least one manager node that are responsible for the worker node's resources run efficiently and ensuring the cluster operates efficiently. Docker Swarm load balancer runs on every node and is capable of balancing load requests across multiple containers and hosts. The Docker Swarm function recognizes three types of nodes, each with a different role within the Docker Swarm ecosystem. Docker Swarm Manager node. This is primary function of manager nodes is to assign tasks to worker nodes in the swarm. Manager nodes also helps to carry out some of the managerial tasks needed to operate the swarm. Docker recommends a maximum of 7 manager nodes for swarm. Docker Swarm Leader node. When a cluster is established, the Raft consensus algorithm is used to assign one of them as the leader node. The leader node makes all of the swarm management and task orchestration decision for the swarm. If the leader node becomes unavailable due to an outage or failure, a new leader node can be elected using the Raft consensus algorithm. Docker Swarm Worker node. In a Docker Swarm with numerous hosts, each worker node functions by receiving and executing the tasks that are allocated to it by a manager node. By default, all manager nodes are also worker nodes and are capable of executing tasks when they have the resources available to do so. Here are 3 simple reasons why companies use Docker Swarm. It leverages the power of containers. Developers love using Swarm because it's fully leveraged container design advantages. Containers allow developers to deploy the applications on services in self-contained virtual environments, a task that was previously the domain of virtual machine. Containers are proving a more lightweight version of virtual machine, as their architecture allows them to make more efficient use of computing power. Docker Swarm helps guarantee high service availability. One of the main benefits of Docker Swarm is increasing application availability through redundancy. To function, a Docker Swarm must have a Swarm manager that can assign tasks to worker nodes. By implementing multiple managers, developers ensure that system can continue functioning even if one of the manager nodes fails. Docker recommends a maximum of 7 manager nodes for each cluster. Auto load balancing. Docker Swarm schedules tasks using various methodologies to ensure that there are enough resources available for all of the containers. Through a process that can be described as automated load balancing, the Swarm manager ensures that container workloads are assigned to run one on the most appropriate host for optimal efficiency. So, just to clarify, a Docker Swarm is a container orchestration tool running Docker application. It has been configured to join together in a cluster. The activities of the cluster are controlled by Swarm Manager, and machines that have joined the cluster are referred to as nodes. So, just want to introduce you Docker Swarm, and if you have multiple containers, you can run Docker Swarm. One of the biggest challenges is how to manage secrets, such as API keys, passwords, and other sensitive information securely within Docker containers. This is where Docker secrets come in. Docker secrets provide a secure way to store and manage sensitive information in your Docker containers. They are encrypted at rest and in transit, and they are only accessible to authorized services. This makes them much more secure than storing secrets in environment variables or embedding them directly in your Docker images. There are two main ways to use Docker secrets. With Docker Swarm, if you are using Docker Swarm, you can create secrets and grant access to them in your compose files. And with Docker Compose, you can use secrets directly in your compose file to specify the location of a secret file. This file will be mounted into the container at runtime, and the secrets will be available to the container as environment variables. There are several reasons why you should use Docker secrets. It has improved security. Docker secrets are encrypted at rest and in transit, which makes them much more secure than other methods of storing secrets. Reduced risk of exposure. Secrets are never exposed in the environment or logs, which reduce the risk of them being accidentally leaked. It's easier to manage them. Secrets can be easily managed using the Docker CLI or Docker Compose. You can centrally manage all of your secrets in one place, which makes it easier to centralize control and keep track of them and ensure that they are used correctly. And that's it. A few best practices for using secrets. Never hard code secrets in your Docker files. This is a security risk, as anyone who can access your Docker file will be able to see the secret. Use a secret management service. There are a number of secret management services available that can make it easier to manage your service or secrets. Rotate your secrets regularly. This will help you to ensure that even if a secret is compromised, it will not be usable for long. Docker secrets are a powerful tool for managing secrets in your Docker containers that can help you to improve the security of your application and reduce the risk of data breaches. If you want to create a new password, you need to run a special command, which is docker secret, and then you can specify create, and then you can specify name of your password, for example, and name password.txt. If you type on enter, you will see an error. This error is because you need to run Docker Swarm init, and Docker Swarm init, and then you can see that Swarm initialized current node is now a manager. To add a worker to this swarm, you need to run the following command, docker swarm join, and then you can run and work with your Docker node. And if we try again our secret, we are also getting an error, but first you need to initialize this Docker Swarm. But without wanting to go deeper into the work with Docker Swarm, the only thing I wanted was to show you that this possibility also exists. Of course, it is not good to keep our credentials as plain text, so it is necessary to create a separate file, and we can use that file which contains important information as an initial protection for our password. If you want to learn more about this topic, the official Docker documentation is at your disposal. But this is simply how can you initialize your swarm, and after that you will be able to create your secret in file. Thank you for watching. In this last chapter of the Docker part of this course, I want to clear or to perform a cleanup from every image and every program that I run in this part of the course. First, I will go to settings, then go to apps, go to install apps. I will run my SQL, and then I will uninstall all SQL that I have in my installed on my system during this demo. So we are cleaning up from my Windows environment. So in the next chapter we will learn about Docker, and I want to perform a cleanup. As you can see, there is a various thing that we need to uninstall before we running this. Let me download my program, and I need to power off some of my programs, and then we need to wait for this server to uninstall. Let's see again. We need to MySQL to turn this off, and this, and finally let's retry. So it's very easy to install, but when you uninstall this MySQL components, sometimes it's very tricky and you need to turn off most of your application. Let's click on next, and I will now execute this to remove our SQL server. Let's click on finish, and finally let's uninstall our shell. As you can see, work with MySQL is very easy, but uninstalling takes a little time, so I wanted to show you just to and now I will uninstall my MySQL workbench. We need to wait until our program is being uninstalled. So after 32 seconds it will be deleted from our Windows machine. After that, I will go to my Linux terminal to delete MySQL instance, and while we're waiting, let's go to our terminal, and the first thing I want to do is to run sudo systemctl stop MySQL. We need to add a password for sudo because we are using sudo. Then we need to delete MySQL Server installation, and I will do that with simple command sudo apt purge MySQL dash server, and we will add a star to delete all, to remove all packages, as you can see. And then I need to remove any dependent packages, so I will run sudo apt auto remove, and finally we need to delete all the remaining files. I will run sudo rm for remove, dash r is recursive, and then dash atc MySQL dash var dash lib dash MySQL, and that's it. This is how can you remove all dependencies from your Linux. And then I will run sudo apt update to update our machine, and then after that sudo apt full upgrade. But before that, let's check our to uninstall this last MySQL program. And finally, as you can see, we don't have any MySQL on my laptop. And then I will run this sudo apt upgrade, and that's it. Let's run on clear to clear our screen, and let's go to our Docker desktop. I will pause this container. Let's remove our container, and then in the images I will simply delete this image, and that's it. We are ready to move on to Kubernetes. Thank you for watching, and see you in the second part of our course. Kubernetes is an open source container orchestration platform that automates many of the manual processes involved in deploying, managing, and scaling containerized applications. Kubernetes automates the configuration of your application and maintains and tracks resource allocation. A project of the Cloud Native Computing Foundation, or CNCF, Kubernetes was first introduced in 2014 and has become a widely adopted platform for organizations to run distributed applications and services at scale. What are the basics concept of Kubernetes? Kubernetes is a platform for managing containers which bundle the code, configuration, and dependencies of an application, allowing it to run as an isolated process with its own resources. Each application gets its own container or multiple containers which are grouped into Kubernetes pods. Kubernetes can run on bare metal servers, virtual machines, public cloud providers, private clouds, and hybrid cloud environments. One of the Kubernetes key advantages is it works on many different kinds of infrastructure. Kubernetes is built to help users to follow three core design principles. As explained earlier, a Kubernetes deployment should be secure. It should follow the latest security best practices, user-friendly. It should be operable using a few simple commands, extendable. It shouldn't favor one provider and shouldn't be customizable from a configuration file. There is also a lot of benefits of Kubernetes. Kubernetes automates much of the tedious work of deploying and scaling application and opens the way to cloud-native development methods that can save time and bring new software to market faster. Some of the main benefits include support for large, complex environment, a production environment running multiple applications will require many containers deployed across many hosts, all working together. Kubernetes provides the orchestration and management capabilities required to deploy containers at scale required for large workloads. Scalability. Kubernetes automatically scales based on your needs, providing the capacity your application needs while saving resources and costs. Portability. Kubernetes automatically scales and can run on site in your own data center, in a public cloud and in hybrid configuration of both public and private instances. With Kubernetes, the same command can be used anywhere. Consistent deployment. Kubernetes deployment are consistent across infrastructure. Containers embody the concept of immutable infrastructure, and all the dependencies and setup instructions required to run an application are bundled with the container. Separated and automated operations and development. Containers save developers time, empowering rapid iteration cycles. At the same time, Kubernetes helps operation teams to feel confident in the stability of the system. Hybrid cloud strategy support. Many organizations combine on-site data center with public or private cloud solutions and balance workloads between multiple cloud providers to take advantage of changes in pricing and service levels. The consistency and portability of Kubernetes can support these hybrid strategies. Continuous support for traditional application. Kubernetes can help you deliver and manage container as legacy and cloud-native apps, as well as those being refactored into microservices. Management of complex environments. Microservices in containers make it easier to orchestrate service including storage, networking, and security, but they also significantly multiply the number of containers in your environment, increasing complexity. Kubernetes groups containers into pods, helping you schedule workloads and provide necessary services like networking and storage to those containers. Improve security. Kubernetes security practices can help organizations to take effective steps toward better IT security. Administrators can apply policies for security and governance and segment policies by pods or group of pods. Development teams can identify security issues in containers at runtime and fix them at build stage, rather than updating or patching them in production. Role-based access control, or RBAC, can assign specific permission to users and services accounts. Role-based access control is implemented in Azure Cloud. So you can add role to your service based on different options. For example, you can add an owner a role to some service or some different scope. Kubernetes secret can safeguard sensitive data like encryption key. Also, it enables DevOps by providing a consistent infrastructure foundation for containers. Kubernetes can support a DevOps approach, which promotes an efficient working relationship between development and operation teams, employing CI/CD or continuous integration and continuous delivery or deployment helps streamline and accelerate the software development lifecycle. An evolution of DevOps, DevSecOps shifts security controls and vulnerability management earlier in the software development lifecycle. One of the most important lessons or chapters in this part of the course, in this second phase of this course, second part, is Kubernetes architecture. So I will go deep into Kubernetes architecture, and I hope you will carefully listen this chapter. So let's learn Kubernetes architecture, and let's understand what is Kubernetes architecture and how it works. And as I already said, let's take a look at main components. So first, what is a Kubernetes cluster? A working cluster, Kubernetes or working Kubernetes deployment is a called cluster, which is a group of hosts running containers. Administrators set the desired state of Kubernetes cluster, describing which application or other workloads should be running, along with which image they use, which resources should be made available to them, and other such configuration details. You can visualize a Kubernetes cluster as two parts, a control plane and a series of compute nodes, typically servers or virtual servers. The control plane is responsible for maintaining the desired state of the cluster, such as which applications are running and which container images they use. The nodes, meanwhile, follow instructions from the control plane and do the actual work of running the application and workloads. Each node is its own Linux environment and could be either physical or virtual machine. A Kubernetes cluster needs at least one compute node, but will normally have many more. A Kubernetes node consists of pods, with each pod representing a single instance of an application. A pod is made of a container or a series of tightly coupled containers, along with options that govern how the containers are run. A multitude of Kubernetes services work together to automatically identify which node is the best suited for each task, allocate resources, and assign the pods in that node to fulfill the request work. Kubernetes automatically send requests to the right pod, no matter where the pod moves in the cluster or even if it's been replaced. Keeping it all under control, Kubernetes provides a unified application programming interface or API to manage, create, and configure the cluster. Let's understand Kubernetes architecture and take a deeper look at what happens in a Kubernetes cluster. The control plane is the nerve of the central, home to the components that control the cluster, along with the data about the cluster state and configuration. These core Kubernetes components handle the work of making sure containers are running in sufficient numbers and with the necessary resources. The Kubernetes API, or Kube AP server, is the front end of the Kubernetes control plane, handling internal and external requests. The API server determines if a request is valid and if it is processed. You can access the API through REST calls, through the kubectl command line interface, or through other command line tools such as kube adm or admin. Then we have our Kubernetes scheduler, or kube scheduler. Consider the resource need of a pod, such as CPU or memory, along with the health of the cluster. Then it schedules the pod to an appropriate compute node. Controllers, or kube control manager, take care of actually running the cluster, and the Kubernetes control manager controls several control functions in one. One controller consults the scheduler and makes sure that correct number of pods is running. If a pod goes down, another controller notices and responds. Configuration data and information about the state of the cluster live in etcd. This is a key value store database. Fault-tolerant and distributed etcd is designed to be the ultimate source of truth about your cluster. As you can see in picture in front of you. To run the containers, each node has a container runtime or engine. Docker is one example, but Kubernetes supports other Open Container Initiative compliant runtimes as well, such as are key KT or CRIO. Each node contains a kubelet, a tiny application that communicates with the control plane. The kubelet makes sure containers are running in a pod. When the control plane needs something to happen in a node, the kubelet executes the action. Each node also contains kube proxy, a network proxy for facilitating Kubernetes networking services. The kube proxy handles network communication inside or outside of your cluster, relying either on your operating system packet filtering layer or forwarding the traffic itself. Beyond just managing the container that runs an application, Kubernetes can also manage the application data attached to a cluster. Kubernetes allows users to request storage resources without having to know the details of the underlying storage infrastructure. Persistent volumes are specific to a cluster rather than a pod, and that can be outlive the life of a pod. The container images that Kubernetes relies are stored on a container registry. This can be a registry you configure or a third-party registry. And what is a Kubernetes operator? A Kubernetes operator is an application-specific controller that extends the functionality of the Kubernetes API to create, configure, and manage instances of complex applications on behalf of a Kubernetes user and add the application functionality. It builds upon the basic Kubernetes resource and controller concepts, but includes domain or application-specific knowledge to automate the entire lifecycle of the software it manages. A Kubernetes operator can be built to perform almost any Kubernetes action, scaling a complex app, application version upgrades, or even managing kernel modules for nodes in a computational cluster with specialized hardware. Examples of software and tools that are deployed as Kubernetes operators include the Prometheus operator for monitoring and the Elastic Kubernetes operator for automating search. And I will now simply repeat all of these components of Kubernetes cluster. What are components of a Kubernetes cluster? A working Kubernetes deployment is called a cluster. You can visualize a Kubernetes cluster as two parts, the control plane and the compute machine, or nodes. Each node is its own Linux environment and could be either a physical or virtual machine. Each node runs a pod, which are made up of containers. What happens in the control plane? So let's briefly explain once again this Kubernetes cluster and all of part of this. So the nerve system or nerve center of Kubernetes cluster is the control plane. Here we find the Kubernetes components that control the cluster along with data about the cluster state and configuration. These core Kubernetes components handle the important work of making sure your containers are running in sufficient number and with the necessary resources. The control plane is in constant contact with your compute machine, and you've configured your cluster to run a certain way. The control plane makes it sure it does. Kube API server needs to interact with your Kubernetes cluster, and then he talks to the API. The Kubernetes API is the front end of the Kubernetes control plane, handling internal and external requests. The API server determines if a request is valid and if it is processed. You can access the API through REST calls through the kubectl command line interface or through the other command line tools such as kubeadmin. Kubescheduler. Is your cluster really healthy? If new containers are needed, where will they fit? These are concerns of the Kubernetes scheduler. The scheduler considers the resource needs of a pod, such as CPU or memory, along with the health of the cluster. Then it schedules the pod to an appropriate compute node. Kube Controller Manager. Controllers take care of actually running the cluster, and the Kubernetes Controller Manager contains several control functions in one. One controller consults the scheduler and makes sure that correct number of pod is running. If a pod goes down, another controller notices and responds. A controller connects services to pods, so requests go to the right endpoint, and there are controllers for creating accounts and API access tokens. And then we have etcd, configuration data and information about the state of the cluster lives in etcd. Just a simple key value store database, fault tolerant and distributed. etcd is designed to build the ultimate source of truth about your cluster. What happens in a Kubernetes node? Node is a Kubernetes cluster needs at least one compute node, but will normally have many. Pods are scheduled and orchestrated to run on nodes. Need to scale up the capacity of your cluster? You need to add more nodes. Let's talk about pod. A pod is the smallest and simplest unit in Kubernetes object model. It represents a single instance of an application. Each pod is made of a container or a series of tightly coupled containers along with options that govern how the containers are run. Pods can be connected to persistent storage in order to run stateful application. Container runtime engine to run the containers. Each compute node has a container runtime engine. Docker is one example, but as we already said, Kubernetes supports others. Kubelet. Each kubelet or each compute node contains a kubelet, a tiny application that communicates with control plane. The kubelet makes sure containers are running in a pod when the control plane needs something to happen in a node. The kubelet executes the action, and kube proxy is a network proxy for facilitating Kubernetes networking services. The kube proxy handles network communication inside or outside of your cluster, relying either on your operating system packet filtering layers or forwarding the traffic itself. So this is Kubernetes architecture, and there is one more subject that I need to mention, and this is OKD. This is a community project of packaged software component needs to run Kubernetes. In addition to Kubernetes, OKD offers developers and operation-focused tools that help teams speed up application development, efficiently deploy and scale, and maintain a long-term lifecycle. OKD lets developers create, test, deploy application on the cloud, while also supporting several programming languages, including Go, Node.js, Ruby, Python, PHP, Perl, and Java. This is the most simplest way to explain Kubernetes architecture. I hope this was helpful. Now that we know what is Kubernetes and how the infrastructure or architecture of Kubernetes looks like, we need to know what are microservices. So in this chapter I will try to familiarize you with the monolithic infrastructure. A monolithic architecture is a traditional software development model that uses a single code base to perform multiple business functions. All software components in a monolithic systems are independent or are interdependent due to the data exchange mechanism within the system. Modifying a monolithic architecture is restrictive and time-consuming because small changes affect large areas of the code base. In contrast, a microservice is an architectural approach that assembles software into small independent components or services. Each service performs a single function and communicates with other services through a well-defined interface. Because they work independently, you can update, modify, deploy, or scale each service as needed. A microservice is an architectural and organizational approach to software development where software consists of small interdependent services that communicate through a well-defined APIs. These services are owned by small, self-contained teams. Microservices architecture make application easier to scale and faster to develop, enabling innovation and accelerating time to market for new features. Let's talk about monolithic versus microservice architecture. With the monolithic architecture, all processes are tightly connected and run as a single service. This means that if one application process experiences a surge in demand, the entire architecture must be scaled. Adding or improving the feature of a monolithic application becomes more complex as the code base grows. This complexity limits experimentation and makes it difficult to implement new ideas. Monolithic architectures add risk to application availability because many dependent and tightly coupled processes increase the impact of a single process failure. With a microservice infrastructure, or architecture, an application is built as independent components that run each application process as a service. These services communicate through a well-defined interface using lightweight APIs. Services are built for business opportunities, and each service performs a single function. Because they run independently, each service can be updated, deployed, and scaled to meet the demand for specific application functions. Characteristics of microservices. It's autonomous. Each component service of a service in a microservices architecture can be developed, deployed, managed, and scaled without affecting the operation of other services. Services doesn't have to share their code or implementation with other services. All communication between individual components takes place through well-defined APIs. Each service is designed for a set of capabilities and focuses on solving a specific problem. If developers give more code to the service over time and service becomes complex, it can break down into smaller services. Advantages of microservices. One of the service advantage is agility. Microservices nurture an organization of small independent teams and take ownership of their services. Teams operate in a small and well-defined or well-understood context and are empowered to work more independently and quickly. This shortens the development cycle. You benefit significantly from the overall throughput of the organization. Also, one of the advantages is flexible scaling. Microservices allow each service to be independently scaled to meet the demand for the application function it supports. This allows teams to build infrastructure needs, accurately measure the cost of a feature, and maintain availability if the service experiences a surge in demand. Microservices allows for continuous integration and continuous delivery, or CI/CD, making it easy to try new ideas and come back if something does wrong. The low cost of failure allows for experimentation, makes it easier to update code, and speed up time to new release feature to market. Microservice architectures don't follow one-size-fits-all approach. Teams have the freedom to choose the best tool to solve their specific problems. As a result, microservices teams can choose the best tool for each job. Also, you can use reusable code. Dividing the software into small, well-defined modules allow teams to use features for multiple purposes. A service written for a particular function can be used as building block for another function. This allows the application to run on its own, as developers can create new capabilities without writing code from scratch. The independence of the service increases the application resilience to failure. In a monolithic architecture, if one component fails, it can cause the entire application to fail. With microservices, applications deal with complete service failure by degrading functionality and not crashing the entire application. Monolithic applications are easier to get started with, as you don't need much advanced planning. You can start and continue to add code modules as needed. However, the application can become more complex and demanding to update or change over time. A microservices architecture requires more planning and design before starting. Developers need to identify different functions that they can work independently and plan for consistent API. However, initial initial coordination makes maintaining the code much more efficient. You can make changes and find errors faster. Code reuse also increases over time. Monolithic applications are simpler than microservices. Developers install the entire application, code base, and dependencies in a single environment. In contrast, the deployment of microservice-based application is more complex, since each microservice is an independent software package that can be deployed. Programmers usually containerize microservices before deploying them. Containers package code and associated microservice dependencies for platform independence. Debugging is a software process for identifying coding errors that cause an application to behave incorrectly. When debugging a monolithic architecture, a programmer can track the movement of data or examine the behavior of code within the same programming environment. Meanwhile, identifying coding problems in a microservice architecture requires looking at multiple loosely related individual services. Debugging microservice application can be more challenging because several developers can be responsible for many microservices. For example, debugging may require coordinated test, discussion, and feedback among team members, which requires more time and resources. A small change in one part of a monolithic application affects multiple functions of the software due to tightly coupled coding. In addition, when developers make new changes to a monolithic application, they must retest and redeploy the entire system on the server. In contrast, access to microservices allowed for flexibility. It's easier to make changes to the app. Instead of changing all services, developers only change certain functions, so they can also independently apply certain services, such as approach is helpful in a continuous workflow in an application where programmers make frequent small changes without affecting the stability of the system. Monolithic applications face several challenges as they scale. A monolithic architecture contains all the functionality within a single code base, so the entire application must scale as requirement change. For example, if an application performance deteriorates because the communication functions experience an increase in traffic, you need to increase computing resources to accommodate the entire monolithic application. This results in a loss of resources because not all parts of the application are at peak capacity. Meanwhile, the microservice architecture supports distributed systems. Each software component receives its own computing resource in a distributed systems. These resources can be independently scaled based on current capacities and anticipated needs. For example, you can allocate more resources to a geographic location service instead of the entire system. Both microservice and monolithic applications have costs during deployment, development, and maintenance. However, the microservice approach is more cost-effective in the long run. You can scale microservice application horizontally by adding computing resources on demand. You only need to add resources for an individual service, not for the entire application. To scale monolithic system, companies need to upgrade memory and processing power for the application as a whole, which is more expensive. In addition to infrastructure cost, the cost of maintaining monolithic application also increases as the requirements evolve. For example, sometimes developers need to run outdated monolithic software on newer hardware. This requires custom knowledge, and developers have to rebuild the app so that it remains operational. Meanwhile, microservices operate independently of specific hardware and platforms, which keeps organization from costly upgrades. One of these is Kubernetes. A monolithic approach is more suitable when designing a simple application or prototype. Because monolithic applications use a single code base and framework, developers can build software without integrating multiple services. Microservice application can require significant time and effort in design, which does not justify the cost benefit of very small projects. Meanwhile, a microservice architecture is better for building a complex system. It provides a robust programming foundation for your team and support their ability to flexibly add more features. For example, networks use AWS Lambda to increase its streaming infrastructure and save development time. Despite its flexibility, developing using microservices require a different set of knowledge and design thinking. Unlike monolithic application, developing microservice requires an understanding of cloud architecture, APIs, containerization, and other expertise specific to modern cloud application. Moreover, troubleshooting microservices can be a challenge for developers who are new to a distributed architecture. A monolithic application runs on a single server, but microservice applications benefit more from a cloud environment. While it is possible to run microservice from a single server, developers typically host microservices with cloud service provider to ensure scalability, fault tolerance, and high availability. You need to have the right infrastructure in place before you can start with microservices. You need more effort to set up tools and workflow for microservices, but they are preferable for building a complex and scalable application. Now that you know what is microservices, which is one integral part of Kubernetes, let's now continue with this course, and I will talk to you in another chapter. So, if you want to work with Kubernetes on the local machine, we have to activate it, and we will do that by going to our Docker desktop. As you can see, this is our Docker desktop that we use with Docker. And let's first go and try to activate our Kubernetes service. So with Docker desktop, you can work with Docker images and containers, but also with Kubernetes on your local machine. Let's go to our Docker desktop. Let's go to settings. As you can see, we have this blade called Kubernetes. I will hit on Kubernetes, and then we will simply enable Kubernetes, and this will start a Kubernetes single or multi-node cluster with starting Docker desktop. And then you can choose a cluster provisioning method like kubeadmin or kind, create a cluster containing one or more nodes, and there is an advanced version to show Kubernetes internal container with using Docker commands. The only thing you need to do is to click apply and restart and simply click on install. As you can see, we are running kubeadmin one node, version is 1.32.2, and it's starting pulling images. And you can check right here that Kubernetes is starting, and that's it. But first, since we work in a limited environment, by activating this Kubernetes in Docker desktop, our local machine will behave like a master and worker node, which is good, while in certain company conditions, it happens that you have more computers working on your system or on that system, when we need to wait for our Kubernetes to be fully enabled. As you can see, it's now starting Kubernetes, and I will not pause this video just to show you how the whole process looks like. If you can see in the bottom of your screen, there is enable engine running, which is Kubernetes, as you can see, and then here is our Kubernetes right now is starting, and you can track all information of how much engine total CPU usage. You can see that this includes containers plus overheads, engine total memory usage, including containers plus overheads, and this is engine utilization. This includes container data, images, builds, and so on. As you can see, our Docker desktop is running, and this green means that everything went well. And then if you want to reset your cluster, simply go and click on reset cluster. When Kubernetes is fully enabled, I will show you something let's go to our containers. If you go to containers, you will see that there was no container that was created. If you go to our images blade, let me click on our images blade. I can show you that, and you can see that we activated a lot of images by default. There are all the components that we mentioned during the chapter on architecture. So we have, as you can see, this core DNS, kube proxy, etcd, API, kube API server, kube controller manager, kube scheduler, desktop Kubernetes, desktop storage provisioner, and desktop VPN kit controller. All of these are part of our Kubernetes, and you can simply go inside this cluster and see all layers if you want, and you can further examine all of these images. So, as I already told you, these images are part of our Kubernetes cluster, and with the help of these images we are able to work with our images or pods on our local machine. But there is another option that we can use to work with Kubernetes on our local machine, and that is Minikube. However, since we are in Docker, as a part of Docker of this course, we are already work with Docker Desktop, and integration in Kubernetes is already enabled. We will do this second part of the course with the same program. So I will use Docker Desktop in the continuation of this course. If you're a fan of Minikube, let's say a few words about Minikube. So maybe you will find it more efficient for you. Maybe, who knows. Minikube is a fundamental in the Kubernetes ecosystem designed to streamline and simplify local Kubernetes development, making it accessible to developers of all levels, and not only developers. Minikube is a lightweight, single-node Kubernetes cluster for local development and testing. It allows developers to create and manage a simplified Kubernetes environment on their machine, offering a convenient and efficient way to experiment with Kubernetes features without the complexities of setting up and maintaining a full-fledged cluster. Minikube's primary role is to provide a local Kubernetes environment that closely mirrors the behavior and functionality of a production cluster. This replication of Kubernetes features and behaviors on a smaller scale makes an invaluable tool for developers aiming to enhance their Kubernetes skills and test application in a controlled local environment. Minikube simplifies Kubernetes development by providing a local environment where the developers can replicate essential functions, and this enables them to work with pods, services, and deployments like a production cluster. The local Kubernetes cluster can run on a single virtual machine or directly on a host machine depending on the chosen configuration. Minikube primarily offers developers a lightweight and consistent Kubernetes environment, streamlining testing and experimentation. It empowers developers to gain practical experience without requiring a fully operational multi-node cluster. This leads to quicker development cycles and a more accessible learning curve, particularly for those new to Kubernetes. Minikube is particularly valuable for DevOps and teams working on Kubernetes-based projects. Its target audience include developers. Minikube enables developers to set up a local Kubernetes cluster with ease, facilitating application testing, debugging, and experimentation. Development teams benefit from Minikube by enabling collaborative development and testing in a consistent local environment. And it is good for Kubernetes beginners. So beginners in Kubernetes can use Minikube to reduce learning curve and understand Kubernetes concept before working with a full cluster. Also, you can do it with the help of Docker Desktop, and in this lesson I showed you how can you enable Kubernetes on Windows machine using Docker Desktop. So if you want, you can find online how can you set up Minikube. It's not that hard, but I won't confuse you because we already know what Docker Desktop is, and the first part of this course was we exclusively work with Docker Desktop. So in the continuation of this second part, with when I'll try to present you Kubernetes, I will use Docker Desktop and do everything with Docker Desktop. Thank you for watching. kubectl is a command line tool that enables communication within the Kubernetes API and the control plane. kubectl allows application deployment, cluster resource management, and resource monitoring. Overall, all CRUD operation, which is stand for create, read, update, and delete, on Kubernetes resource are carried out with kubectl help. The tool is compatible with all major operating systems such as Linux, Windows, and macOS. So why is kubectl so important? kubectl is one of the most crucial tools for managing the complete Kubernetes infrastructure, where application may be distributed across different clusters. The tool facilitates communication between users, Kubernetes resource, and external components by sending HTTP requests to the Kubernetes API server. In situation where the Kubernetes API server is publicly accessible, or when additional security measures are required, it is possible to configure kubectl to use HTTPS to communicate with the Kubernetes API server. To do this, you need to configure the Kubernetes API server to serve HTTPS traffic and configure kubectl to use appropriate SSL certificates and keys. In addition to communication, it also runs end-to-end resource management operations, including container deployment, viewing log files, knowing the state of resources, and more. The syntax for running the kubectl command is as follows: kubectl command, then type, name, and flag. Command refers to operation to be performed on a cluster. And a few examples if you want to include create, delete, and describe. Type refers to the resource type on which the operation needs to be performed. The resource type is not sensitive to upper or lowercase characters used when writing the command. Thus, regardless of capitalization, the same resource type will be recognized by kubectl. Name refers to the name of the resource. Unlike type, resource names are case sensitive. Capital and lowercase letters will give a different output. And flags is the optional part of the syntax and is used to mention the port number of the Kubernetes API server. A kubectl command can be applied to one or more resource types. For example, kubectl get pod 1. After running this command, the cluster should return pod 1. In the example, get is the command, pod is the type, and pod 1 is the name. No flags have been specified, set so the default value will be used. kubectl performs basic operations on Kubernetes clusters to ensure the tool exhibits complex behavior and executes intricate functions. Kubectl plugins can be written and installed in the infrastructure. These can be pre-existing plugins or custom-made ones depending on the needs of the application and the function it must execute. A few of the plugins are, for example, Kubescape, Stern, kubepug, Ingress, and Nginx. Overall, kubectl is a tool that helps manage Kubernetes cluster by communicating between the API server and the control plane. The tool performs several basic operations while also enabling engineers to perform more complex operations using extensions in form of plugins that are commonly available or can be written to specification. A pod is the smallest execution unit in Kubernetes. A pod encapsulates one or more application, and pods are ephemeral by nature. If a pod or the node it executed on fails, Kubernetes can automatically create a new replica of that pod to continue operation. Pods include one or more containers, such as Docker containers. Pods also provide environmental dependencies, including persistent storage volume. Storage is permanent and available to all pods in the cluster, and configuration data needed to run the containers within the pod. So, what does a pod do? Pods represent the process running on a cluster. By limiting pods to a single process, Kubernetes can report on the health of each process running in the cluster. Pods have a unique IP address, which allows them to communicate with each other, persistent storage volumes as required, and configuration information that determine how a container should run. Although most pods contain a single container, many will have a few containers that work closely together to execute a desired function. What are benefits of the pod? When pods contain multiple containers, communications and data sharing between them is simplified. Since all containers in a pod share the same network namespace, they can locate each other and communicate via localhost. Pods can communicate with each other by using another pod's IP address or by referencing a resource that resides in another pod. Pods can include containers that run when the pod is started, say to perform initiation required before the application containers run. Additionally, pods simplify scalability, enabling replica pods to be created and shut down automatically based on changes in demand. So, how does a pod work? Pods are created by workload resource called controllers, which manage rollout, replication, and health of pods in a cluster. For example, if a node in the cluster fails, a controller detects that the pods on the node are unresponsive and creates replacement pod on another node. Three most common types of controllers are jobs for batch type that are ephemeral and will run at task completion, deployments for applications that are stateless and persistent, such as web servers, HPPT server, stateful sets for applications that are both stateful and persistent as databases. If a pod has multiple containers, they are scheduled together on the same server in the cluster, whether VM or physical server. All containers in the pod share their resources and dependencies and can coordinate their execution and termination. For example, pods can contain init containers that run before the application containers run, setting up the environment for the application that follow. Pods are always or almost always created by controllers, which then can automatically manage the pod lifecycle, including replacing failed pods, replicating pods when necessary, and evicting the pod from cluster nodes when they are complete or no longer needed. Controllers use information in the pod template to create the pod, and controllers ensure that running pods match the deployment defined in the pod template. For example, by creating replicas to match the number defined in the deployment. How the pod communicate with each other? When a pod is created, it is assigned its own unique IP address. If there are multiple containers within the pod, they can communicate between each other simply by using localhost. Communication outside of the pod is achieved by exposing a port. Communication between pods in a cluster takes advantage of the fact that Kubernetes assigned a cluster private IP address to every PID or pod ID in a cluster, eliminating the need to either explicitly create links between pods or to map container ports to host port. In this way, every pod in a cluster can see each other without the need of net address translation. If we want to use the kubectl command, we have to go to our Visual Studio Code. I hope you have already know what is Visual Studio Code, and I'll already show you how can you install Visual Studio Code. And then in this Visual Studio Code, we need to open our terminal. Let's go to terminal and hit new terminal. In this new terminal, I will simply use my Ubuntu WSL option, and then if you can type kubectl in your terminal. So I will, for example, try to type kubectl, and you can see that we are getting some information, but you can see that if I type kubectl, you have this information that kubectl controls the Kubernetes cluster manager, and all information about kubectl you can find on this kubernetes.io -docs-references.kubectl. Also, there is some basic commands for beginner, for intermediate, and there is a deploy command, cluster management command, troubleshooting and debugging commands, advanced commands, setting commands, subsetting commands, and so on, subcommands. Also, you have option to add a help, to see help while using kubectl. But let's see what version of the kubectl we have here. I will type kubectl and version. Let's hit on enter, and client version is 1.32.2, customized version is 5.5.0, and server version is exactly the same as our client version. So we are getting response what client and server version and what customized version are we using. Then if we type, for example, another command, kubectl cluster -info, and I will hit on enter, you're getting the information of the cluster. So this is how can you add your information about your cluster. Also, you can use this kubectl cluster info -info dump command to further debug and diagnose cluster problems. If I want to see and get the object running in the default namespace, I will type, for example, kubectl get all. So you can see that we are getting objects running in the default namespace. This is our cluster IP and our port, and when this service Kubernetes started. During we work with Kubernetes, you will see further use of this command, but for now let's stick to this simple command. So this is how can you use kubectl in your Visual Studio Code. Also, don't forget to install, if you want to use Kubernetes in your Visual Studio Code environment. You can go to extensions and simply type Kubernetes, and you can install one of these extension. That's it, nothing else. So thanks to kubectl we can run this command. And just to remind you, kubectl is a command line tool that enables communication between Kubernetes API and the control plane. This command allows application deployment, cluster resource management, and resource monitoring. So you can create, read, update and delete on Kubernetes resource with the help of kubectl command. In this chapter I will try to create our first pod, especially now when we know what pod is. But first we must go to our Visual Studio Code, and then I will type a simple command. Just like when we start with Docker, I will run kubectl ctl run. I will add a name for my nginx -pod1, for example, and then I will specify my image, and this image will be based on nginx. Let's hit on enter. As you can see, our pod nginx pod1 is created. Exactly the same thing when we work with the Docker, and this image will also be pulled from official Docker Hub. If we want to check if this pod is created, we need to type kubectl get pods. As you can see, I have two pods. The first one when I'll try for myself, and the second one is this nginx pod1 that we just created. So you can see that we have name of our pod, status is ready, it's running, and age defined when this pod is created, 31 seconds ago, and the first one was 4 minutes ago. And then if I go to my Docker desktop, let's go to our Docker desktop, you can see that I have two containers that running. This is K8s, this is Kubernetes nginx pod, and the whole name of this with ID, pod ID, this is PID or pod, and then this is our image. We didn't specify any port and when this last started. Then if we go to images, beyond or beside our containers or images that are created when we enable our Kubernetes, there is also nginx which is running, as you can see, and this is the latest tag. Just to remind you, this is official image from our Docker Hub. If you go to our containers, I can go inside my container and see logs. For example, you can run inspect, as you can see. Then there is something called bind mounts executable. You can debug right from here. This is our files, this is our stats. So you can track your containers even more deeper. But for now, let's go to our browser, and I will run this localhost. So as you can see, we don't have this any message. This still run Apache, but we don't have any answer on our local host because we didn't specify our port. In the next chapter, I will show you how can you expose this pod. Welcome back, and if you remember, in the previous chapter we create our first pod, nginx pod 1. And if you want to expose this pod, you can do it by using pod forward flag. Once that we create our pod, and if you want to add port, so it can, this is an nginx based, this is a pod based on nginx image, we need to get our Nginx message. We need something that called exposed. So let's try to run the next command. kubectl port dash forward, the name of our pod, Nginx pod 1, and if I specified 8080 and if I run enter, you can see that we getting a mistake that this is unable to listen on port 80. So listener failed to create with the following error: unable to create listener. We need to specify bind permission is enabled to create listener. So what have we need to do? Because it can listen on port 80. If we change our host port and use exactly the same command, so I will type again kubectl port dash forward, then name of our pod, Nginx dash pod 1, and then I will specify another 8080. This is our new host port, and I will run enter. As you can see, that this message say that we activated port forwarding option, and now it's possible to get this message. If I go to my browser once again and open our private window, I will type localhost, and then in the continuation I will add 8080 port. As you can see, we are getting this message from Nginx. Then let's go back to our Visual Code. If I want to back to our terminal, I will simply hold Ctrl and Z. As you can see, it is stopped, so kubectl port forward Nginx pod is stopped. And then let's try to type kubectl get all, and we are getting some information. We see all of our pods with name, status, age when it's created, and we see that also this service at -Kubernetes is active. So we have this cluster IP, and it listens on port 443 with TCP, with the help of TCP. If I want to delete my pod, I can simply run kubectl delete pod, and name of my pod, let's try Nginx dash pod 1, and this pod is now deleted. I want to delete other one too. Let's try kubectl delete pod and the name of my first pod. This is Nginx dash pod. Let's hit on enter. Our second pod is deleted. And if I now try to type kubectl get pods, you can see that no resources found in default namespaces. So we don't have any port that is working, that is running right now. And if you go to our Docker desktop, you can see that we don't have any container. If you go to images, there is our Nginx images, but it's not active. So this is how can you create your pod. Then this is how can you expose your pod, get this Nginx message, and how can you delete your pod. In this chapter, I would like to show you how can you create a simple pod based on the Apache image. In the previous chapters, we work with Nginx image, and this image is also from Docker Hub repository and will be pulled from official Docker Hub repository. So the first thing we need to do is to create an Apache Docker image. In our Visual Studio Code, I will run a simple command. You already know, kubectl run. Then I will add a name for my Apache-pod, and then we simply type image and then httpd. So as you can see, this Apache pod is created. Let's try kubectl get pods. As you can see, this is our Apache pod. Status is running, and it created age is 10 seconds ago. And then we need to use our port forwarding flag or command. So just like from previous chapter, we will run kubectl port dash forward, and then you need to specify the name of our pod. This is our Apache pod, as you remember, and then I need to add our host port and our port. Let's try again. So let's try, for example, 8080. It's unable to listen. I will try some different port name. As you can see, I added 8090, for example, and it's now listening on this port. If we go to our browser and let's go to our browser, I will open a new window. Let's try localhost, and then I will add 8090 port, and as you can see, we are getting this message. It works. This is the default message from Apache server. And then if you go back to our Docker desktop, you can see that our container is running. This is our default name of our container, or of our pod, sorry. And if you go back to our images, there is HTTP image latest, and it's running. Let's go back to our Visual Studio Code. I will now press Ctrl and Z to stop this Apache port forward running. We are now exposing this pod, and I will simply run kubectl get all. So as you can see, exactly the same information that we have for our Nginx server, now we have from Apache server. And then we can simply run kubectl delete pod and the name of our Apache-pod to delete this pod, and then let's try kubectl get pods. We don't have any resources. Let me check my containers. So we don't have any container. If we go to images, our HDBD or Apache is images here, but it's not in use. So this is how can you create a pod based on Apache server. YAML is a human-readable data serialization language that is often used to write configuration files. Depending on who you ask, YAML stands for another markup language, or YAML is not a markup language, a recursive acronym which emphasizes that YAML is for data, not documents. YAML is a popular programming language because it is designed to be easy to read and understand. It can also be used in conjunction with other programming languages. Because of its flexibility and accessibility, YAML uses Ansible to create automation process in form of Ansible playbooks. YAML uses the YAML or .YAML extension and follows certain syntax rules. YAML has functions derived from Perl, C, XML, HTML, and other programming languages. YAML is also a superset of JSON, so JSON files are valid in YAML. There are no common format symbols such as parentheses, square brackets, endnotes, or quotation marks. And YAML files are easier to read because they use Python-style indentation to specify structure and mark nesting. Tab characters are not allowed by design to maintain portability across systems, so spaces, literal spaces, are used instead. Comments can be identified by using a pound or hash symbol. It's always best practice to use comments, as they describe the intent of the code. YAML does not support multi-line comments. Each line should be suffixed with a pound sign. A common question for YAML beginner is, what does 3 dashes mean? 3 dashes are used to indicate the beginning of a document, while each document ends with 3 dots. One of the most common use of YAML is to create configuration files. It is recommended the configuration files to be written in YAML rather than JSON, although in the most cases they can be used interchangeably, as YAML has better readability and easier to use. In addition to use the Ansible, YAML is used for Kubernetes resources and deployments. The advantages of using YAML is that YAML files can be added to source control such as GitHub, so the changes can be tracked and audited. Kubernetes works on the basis of a defined state and a real state. Kubernetes object represent the state of a cluster and tell Kubernetes what you want the workload to look like. Kubernetes resources such as pods, objects, and deployments can be created using YAML files. When you create a Kubernetes object, you need to include specification to define the desired state of the object. The Kubernetes API can be used to create an object. The API request will include the object specification in JSON, but most often you will provide the necessary information to kubectl as a YAML file. Kubectl will convert the file to YAML for you when it makes an API request. Once an object has been created and defined, Kubernetes works to ensure that the object always exists. Developers or system administrators determine the defined state of YAML or JSON file that they send to the Kubernetes API. Kubernetes uses the controller to analyze the difference between newly defined state and the actual state in the cluster. A Kubernetes deployment tells Kubernetes how to create or modify instances of the pods that holds a containerized application. Deployments can help to efficiently scale the number of replica pods, enable the rollout of updated code in a controlled manner, or roll back to an earlier deployment version if necessary. Kubernetes deployments are completed using kubectl, the command line tool that can be installed on various platforms, including Linux, macOS, and Windows. Kubernetes saves times and mitigates errors by automating the work and repetitive manual functions involved in deploying, scaling, and updating applications in productions. Since the Kubernetes deployment controller continuously monitors the health of pods and nodes, it can make changes in real time, like replacing a failed pod or bypassing down nodes to ensure the continuity of critical applications. Deployment automate the launching of pod instances and ensure they are running as defined across all the nodes in the Kubernetes cluster. More automation translates to faster deployment with fewer errors. What are Kubernetes deployment? Kubernetes offers several deployment strategies to handle a broad range of application deployment and development needs. Once you define the desired state of the application, the deployment controller goes to work. It makes changes at a control rate to optimize the deployment. What is Kubernetes recreate deployment? The recreate strategy terminates pods and are currently running and recreates them with a new version. This approach is commonly used in a development environment where user activity isn't an issue. Because the recreate deployment entirely refreshes the pod and the state of the application, you can expect downtime due to shutdown of the old deployment and the initiation of new deployment instances. What is a Kubernetes rolling update deployment? The rolling update deployment provides an orderly ramped migration from one version of an application to a newer version. A new replica set with the new version is launched, and replicas of the old version are terminated systematically as replicas of the new version launch. Eventually, all pods from the old version are replaced by the new version. This rolling updates deployment is beneficial because it provides an organized transition between versions. However, it takes time to complete. What is Kubernetes blue-green deployment? The blue-green deployment strategy offers a rapid transition from the old to new version once the new version is tested in production. Here, the green version is deployed along with new existing blue version. Once there is enough confidence that green version is working as designed, the version label is replaced in the selector field of the Kubernetes service object that performs load balancing. This action immediately switches traffic to the new version. The Kubernetes blue-green deployment options provides a rapid rollout that avoids versioning issues. However, this strategy doubles the resource utilization since both versions run until cutover. What is Kubernetes canary deployment? In a canary deployment, a small group of users is routed to the new version of an application, which runs on a smaller subset of pods. The purpose of this approach is to test functionality in a production environment. Once satisfied that testing is error-free, replicas of the new version are scaled up, and the old version is replaced in an orderly manner. Canary deployment are beneficial when you want to test new functionality on a smaller group of users. Since you can easily roll back canary deployment, this strategy helps gauge how new code will impact the overall system operation without significant risk. What are use cases for Kubernetes deployment? Deployment are the easiest way to manage and scale how applications run on a Kubernetes cluster, and Kubernetes Open API simplifies integration into CI/CD pipelines. Here are the some use cases. Run stateless web service like popular open source Nginx. The deployment can request that a fixed number of pod replicas be instantiated, and Kubernetes will maintain the number of pods during the deployment. Applications that require persistent storage, like a database instance, would use the stateful set type deployment and mount a persistent volume to ensure data strategy and longevity. Deployments can automatically scale the number of replicas in the cluster as the workloads increase. For example, they can automatically balance incoming requests between the replicas, create new replicas as demand increases, and terminate replica as demand subsides. How to create a Kubernetes deployment? As with most Kubernetes functions, deployments are described in YAML or JSON files, and they are created using kubectl apply. You can update a Kubernetes deployment by changing the pod template spec within the deployment. That will automatically cause an update rollout. Changing the pod template will prevent running pods from accepting requests, so that can be scaled back until all pods can be terminated. Once they have been terminated, the updated pod template will be used to create new pods. Now that we know what YAML file is, it's time to create a simple YAML file. So let's create our first YAML file. I'm in my Kubernetes folder, and I will create a new file, simple file. This will be nginx pod. .yaml. So as you can see, we already have this indentation, which is YAML file. And in this YAML file, the first thing we need to do is to add API version. So I will type API version, 2 dots, and this is version 1. Then I will hit on enter. The second thing we need to do is to choose what kind of service we want to use. I will type kind, and then I will add pod. As you can see, it is automatically added, but I won't use this. I want to write this step by step. Let's delete all of this information, and then in the kind I will write only pod. Then let's hit on enter again. So we need to add metadata, which is also part of this file. And then in the next line I will hit on tab. It is very important to hit on tab so we can add a name, and then we will add a name for our nginx. This will be called nginx-pod, and then we need to specify some more information. Let's hit on enter. I will again hit on tab. Let's go to containers. In the containers I will add name. This name for this container will be nginx1. Then I need to specify the image. Image will be official nginx from Docker Hub, and then we need to specify port. I will type port, and in the port section we need to specify container port, and this will be work on port 80. So this is how can you write your first YAML file, and then I will go to file and click on save. So this is saved. Let's see, we have one problem. Line 6. So this will be our nginx pod, and we need to take this image here, and finally let's hit on save. So this is how can you write your first YAML file. In this chapter, I want to show you how can we deploy this YAML file. It's very simple. You can use two commands. First one is that we must use kubectl, and you can use option create. But in the most cases, you will find that all people uses apply. So kubectl apply, then we need to add this F, which stands for force, and simple add your nginx dash pod .yaml, and I will hit on enter. So our pod nginx is created based on our YAML file. So it's very easy, as you can see, just specified your API version, what kind of service do you want to use. For example, this is just a simple demo, so we are using to create one pod. Name of this pod is nginx pod. In the specification, we need to specify that we want to create container, and then we need to specify the name of this container, and the official image from Docker Hub, and port is 80, as you can see. And now, if you go and type kubectl get pods, you can see that we have our nginx pod running. Also, you can check in your browser. If you go to localhost and simply run this localhost, there will be nginx message, and if you go to our Docker desktop, you can see that we have one container that we just created based on nginx image. So you can also check these logs from your container. Also, you can inspect whatever you want to see, and then you can also track files, or simply go to our Docker and simply type ls, so you can see the list of our what we have in our container. So you can even logged into your container with the help of Docker desktop. I can try any command I want. This is our files, so as you can see, and this is the stats of our container. So with the help of the YAML file, you can deploy almost anything. Exactly the same thing you can do to create Apache container. So in the next couple of chapters, we will do mostly with YAML files, and what I want to emphasize even more, this is just a simple demo that I want to show you how can create one pod. In the next chapters, we will see more difficult YAML file, more complex YAML file, and this is a good starting point for you. And even online, you can find even more examples of how can you create YAML file. So it's not so difficult. Just remember some basic steps. And now I will delete this with kubectl delete and the name of our pod, which is nginx-pod. We need to specify our pod, and now it is deleted. So if I go to kubectl get pods, you can see that we don't have any resource that run right now, and we don't have any containers. If we check our image, you can see that Nginx is no longer active. So this is how can you create your pod based on YAML file. Without proper logging and overlog consumption, you'll never be able to troubleshoot what's happening in your Kubernetes environment. Have you ever seen an error pop up on your screen when you're trying to install something or use a specific tool or platform? Have you ever had to go on a computer and look the output for a particular applications? So these are logs. Logs contain information about the system, operating system, the application, and many other aspects, as long as wherever you're viewing the logs support logging. What means by that is every application has the ability to send out logs, but sometimes they don't. It's all up to the developer or administrator to implement the functionality to save output logs of the app. Logging has been a lifesaver for almost everyone in the technology space. Whether you're a sysadmin, a cloud engineer, a developer, or anything in between, it's always guaranteed that you looked at logs at some point to solve a specific problem. In short, logs are the events that occur on a computer or an app. In Kubernetes, you're going to care about two different types of logs: cluster logs and Kubernetes resource or object logs. Cluster logs are in regard to how the cluster is performing, if the control plane is healthy, if the worker nodes are healthy, and depending on how they installed, how the Kubernetes components are performing, like etcd, scheduler, API server, etc. For example, in standard kube admin deployments, etcd will run as a pod, so it would be considered a Kubernetes resource or object log. However, if etcd is configured across clusters running on its own server, it may be not bootstrapped as a pod, and therefore would be considered a cluster log. Kubernetes or resource object log are any Kubernetes resource that's running. You get the logs and events for various Kubernetes resources, but the bulk of what engineers usually look at are pod and container logs, as this is the primary location to keep your information on the running application. The quickest way to check logs for pods is what the kubectl logs pod and name of your command. However, kubectl logs only work to check logs for pods and no other Kubernetes resource. So there is different types of logging methods in Kubernetes. When you're thinking about your logging strategy for a Kubernetes environment, there are a few different ways that you can output logs. First is application forward or forwarding, then we have sidecar and node agent forward. Let's break this down. Application forwarding is done inside of the application code. For example, let's say you are writing a front-end app. Inside of the app, you can specify the logic that say send the logs from here to this system. Although that may sound straightforward, it's arguably the worst way to manage logs. Why? Because you're putting a dependency on the code and the logging system. What if the logging system changes? Are you going to implement this for each and every app and piece of each app? This method should be avoided at all times unless you have some time of ridiculously compelling reason to you. For example, a compelling reason to do this is if you have a legacy application that already has the log functionality embedded into, so you should be planning how to change this functionality for the future. The sidecar methods, this is our second method, would be if you implement a log aggregator into a Kubernetes pod. You end up having two containers in the same pod. One of the container is the app itself, and the other container is the logging system you're using. This is an alright method and should definitely be used instead of application forwarding, but there's a better method called node agent forwarding. This is our third method. So the node agent forwarding method is a pod that runs on each Kubernetes worker node. The job of the pod is to read the log files of the containerized app and send them to whichever logging tool or platform you're using. This is the best method for a few reasons. First, you aren't implementing a sidecar which removes extra functionality for a pod which should technically be doing one job. And second, it segregates the workload process versus having dependencies and turn you to have one Kubernetes resource, that's our pod, that's doing one job, just sending logs. Let's talk about Kubernetes audit logs. The thing about logs is that logs can be considered pretty much any output: events, app logs, terminal output, exit events, and a lot of other pieces. Because of that, I can't cover everything without this chapter, but let's stick with the most important one. Kubernetes audit logs give you the ability to capture and view any output that the Kubernetes resource creates. For example, when you create a Kubernetes deployment, a lot is going on. The container image is being pulled from a registry. The pods are being scheduled on a worker node. The pods are either starting or failing, and if they're failing, there is no reason as to why. Scaling on the pods is done. Because of the detail, you may want to specify to collect certain logs, or maybe you want all of them. In the next couple of minutes, I want to show some kubelogs command, but first we need to create our pod, because I don't have any pod. Just to show you, if I go to my Docker desktop, in the container I don't have any containers, only I have two images, as you can see. But let's create our new pod. You already know how to create pod, so I will run kubectl apply -f for force and the name of our YAML file, nginx-pod.yaml. So our pod is created. Let me just type kubectl get pods, and we have our pod which is running. So I already told you that I want to show you how can you use this log command. The first thing I want to show you is kubectl logs and the name of our pod. Name of our pod is nginx-pod. As you can see, we are getting a lot of information of our pod. So as you can see, all the things that you want to see is here. All the information about Nginx, which version of Nginx, our Linux operating system, when it starts working, and so on. Also, there is another information, and that's it. This is how can you run this first log that prints a logs for a pod. Then you can use, for example, command to see the last 6 hours for this pod. Let's try. I don't have 6 hours, we have only 1 or 2 minutes for this pod, but let's try anyway. kubectl logs, and then I will add -- since equal 6 hours 6. Let me just add this to 6 hours, for example, and then I will add the name of our pod. Our pod name is nginx-pod, and I must run this again. So as you can see, this is the logs. With this command we are printing our log for the last 6 hours of our pod. Then we have used tail command or tail flag with recent n lines of logs for a pod. N is just a number, so I can run, let me clear this, I can run kubectl logs dash dash tail, and it's equal to, for example, 10. It will show me only 10 lines of my logs. Let's set 20. And then we need to specify the name of our pod, which is nginx-pod. As you can see, we are getting only first 20 lines of our logs. Then there is another option to print the logs for a pod in real time and follow new logs. For example, this command will be kubectl, then logs, then f, and our nginx-pod. So as you can see, this is the real time, and you can follow all new logs with this command. So it's simple: kubectl logs dash f and the name of your pod. Let me click on Ctrl Z to stop this live look at our logs, and then we can retrieve the logs of a specific container within a pod in a Kubernetes cluster. For that, you can run simple command kubectl, then logs, then the name of our pod, and then C for container, and then if you have more than one container, you just add the name of your container. So it is obvious that I don't have a new container. In this pod I have only one container, but with this command you can specify container within a pod in a Kubernetes cluster. Then the next command that I want to show you, so that you can specify the namespace if the pod is not in the default namespace. So for this you can run, for example, kubectl logs name of your pod. This is our nginx-pod dash n, which stands for namespace, and the name of your new namespace or desired namespace. Let me clear my screen. The next command is that you can do an output logs for a pod into a file named, for example, pod.log. Let's try that command: kubectl logs, the name of our pod, nginx-pod, and then simply add pod.log, and all of this log will be stored in this pod.log. But container pod log is not valid for this engine pod log. This is only for our container. Then if you want to view the logs for a previous failed pod, you can run this command kubectl logs -- previous and the pod name. This is our nginx -pod, and as you can see, previous terminated container was nginx1 in pod nginx, but it is not found. If you have more than one of this pod, then you will see your logs for a previously failed pod. Also, you can include timestamp on each command of the log output. It is also a very simple command. kubectl logs our pod name and simply add -- timestamp, and as you can see, you are getting your timestamp right on each line of the log output. So this is how can you do it. If I now try, for example, kubectl logs and nginx -pod, you can see that how it looks like without the timestamp pod. And if you have more containers in a pod, there is another command to view all the logs for all containers in your pod. Let me first clear this screen. And there is a 10 command for our log. Let me try kubectl logs nginx -pod and -- all -containers, and simply click on enter, and this will add all the logs for all containers, but we have only one pod with one container that is currently running, so it shows us only one container. And if you don't see the logs you're expecting, you need to check if your pod has restarting, for example using kubectl describe and then pod and the name of your pod. Let me try nginx again -pod, and here you can find every information that you need, and then you can try to see if this container is started or not. And it is started, as you can see, and it was successfully pulled. So if you want to see more logs, just hit on this command kubectl describe pod and pod name, and that's it. This is the 11th command in this demo. I hope this was helpful, and then I will show you just how can you log in to your container or pod. In these previous minutes I showed you how can you see logs from your container or pod, but this time I want to log in. Just like with Docker, command is very the same. First I will clear my screen, and then I will run kubectl exec -it. Name of our pod is nginx -pod and -- and this bin bash, we're creating just bin bash session for this container. Let's hit on enter, and we are now logged into as a root user in our container. And then we can type, for example, ls command to list all the files in our container, or whatever command that will help us to troubleshoot this container. If you want to see the logs for this container, we can also go to our Docker desktop, go inside our container, and in the first tab you can see logs, and here you will find out everything that you need about this container. So in this chapter I show you how can you see logs for your container and how can you log into your container. So this is two different things, but it's very helpful for troubleshooting, and I hope this was helpful. A replica set, or RS, is a Kubernetes object used to maintain a stable set of replicated pods running within a cluster at any given time. A Kubernetes pod is a cluster deployment unit that typically contains one or more containers. Pods, and by extension containers, are nevertheless short-lived entities. A container hosting a sample application, for example, could fail. As a host, you think the kubelet process would automatically recreate it, however pods aren't automatically rescheduled when they die. This has an impact on the containers within because they are not rescheduled and may be discarded owing to a lack of resources. To keep your application operating, you need to keep track of the health of your pods. The Kubernetes replication controller is in charge of ensuring the pod lifecycles are maintained by scheduling a replacement for any pods that fail. There are several distinct controllers, each having a different use case. They all have one thing in common. They all keep a watch on a specific cluster or pods to make sure the proper number of them are always running. A replica set in a Kubernetes is a Kubernetes object used to maintain a stable set of replicated pods running within a cluster at any given time. As I already told you, the main goal of Kubernetes controllers is to define a desired state by ensuring at any given moment, and pods of the same type are constantly running at all times. As such, replica sets, or RS, are often used to guarantee the availability of a service. Kubernetes will automatically deploy extra pod to replace those that fail or become inaccessible, preventing users from losing access to an application. If we didn't use a replica set, we would have to build as many manifests as the number of pods we require, which would be a lot of work to do for each application. A replica set has two main features: a pod template for creating new pods whenever existing one fails, and a replica count for maintaining the desired number of replica that the controller is supposed to keep running. A replica set also works to ensure additional pods that are scaled down or deleted whenever an instance with the same label is created. As a result, it ensures that a specified number of replica pods are running continuously. A Kubernetes replica set helps with load balancing, reliability, and scaling. Load balance replications allows Kubernetes to have multiple instances on a pod. This means that traffic is sent to different instances, which prevents a single instance from being overloaded. Reliability, replication that we have multiple instances of an application, which means that it won't fail just because one of these containers fail. And scaling, with Kubernetes you can quickly scale your application up or down by adding or removing instances. So, what defined a replica set? Selector is used to identify which pods in replica set is responsible for. Replicas indicate the number of pods that replica should maintain. Template defines the pod template that the replica set uses when creating pods and adding them to meet the required number of replicas. This is, for example, YAML file. And then inside YAML file we have API version. It defines the Kubernetes API that supports the resource replica set. Every API supports certain resource, and together with the kind we can unequivocally define them. And kind defines the source as a replica set for the Kubernetes API. And now we were working with deployments so far with our YAML file. Let's compare the replica set to deployments. Deployments are an alternative to replica set, as they are used to manage replica set. They are handy when it comes to rolling out changes to a set of pods via replica set. You can simply roll back to a previous deployment revision when managing a replica set using a deployment. You can also use a deployment to create a new revision of a replica set and then migrate existing pods from an older revision into the new revision. After that, the deployment can take care of cleaning up old, unused replica sets. In terms of usage, a replica set is in charge of ensuring that pods are available, whereas a deployment is responsible for managing different versions of an application by controlling one or more replica sets. A deployment is a higher abstraction that controls the release of a new version by managing one or more replica sets. Replica sets can still manage pods and scale instances of specific pods, but they can't make rolling updates or use several other features. Instead, this functionality is managed by a deployment, which is the resource that a Kubernetes user would like, or mostly like, interface with today. Then, when we start working with our pods, we already mentioned daemon set. So let's compare daemon set with replica set. Daemon sets are key component of the Kubernetes cluster and allow administrators to configure services or pods across all or a subset of Kubernetes node with ease. They ensure that a pod is replicated on some or all of the nodes. When a new node is added to a Kubernetes cluster, a new pod will be created on that node. Therefore, there is no need to indicate the number of replicas a daemon set should deploy. The daemon set controller guarantees that garbage collection is performed on pods associated with nodes when they are deleted. When you delete a daemon set, you will delete all the pods that it has produced. Daemon sets are frequently used to run cluster level application. For example, they are used for tasks including installing a cluster storage daemon, such as a clusterd or ceph on each node, using a log collecting daemon, such as fluentd or log stash on each node, and running a node monitoring daemon like Prometheus node exporter, collectd, or datadog agent on each node. Like a replica set, a daemon set is a controller that ensures that pod operates on all nodes in the cluster. A daemon set also had familiar functionality when it comes to automatically adding or deleting pods when a node is added or removed from a cluster. You should use daemon set instead of replica set for pods that perform machine level function like machine monitoring or machine logging. The life cycle of these pods is related to the life cycle of the machine. They must be operating on the machine before other pods can start, and they are safe to terminate when the machine is ready to be rebooted or shut down. So if you remember, we are again in our Visual Studio Code, and after we completely looked at a replica set, what is a replica set? Now we know what is a replica set. Let's see how can we work with replica set. But first, I will exit from our container. If you remember, we were logging in our nginx pod YAML, and then I will open a new file, create a new file, nginx-deployment.yaml, This is our new file, and then I will paste this code, this YAML file, and then just let me try to explain. As you can see, we have this API version, and as I already told you in one of the previous chapter, this defines the Kubernetes API that supports the resource, for example, replica set, and every API supports certain resources, and together with kind, you can define them. And then in the next line, we have kind that defines the resource as a replica set for the Kubernetes API. And then you have this metadata. We have our Nginx replica set name for this. This is our app, which stands for Nginx. Then we have selector. As you can see, with the spec option, you can define your replicas. We have 3 replicas here. You can set number whatever you want, but let's make it simple and keep this number 3. So we will create 3 pods, and selector used to identify which pods this replica set is responsible for. This is our Nginx app. As you can see, this is our label, exactly the same name. And then replicas indicates the number of pods that the replica should maintain, and this template option, as you can see, defines the pod template that the replica set uses when creating pods and adding them to meet the required number of replicas. And all of our containers will listen on port 80. And now let's try to run this YAML file. And if you don't have your terminal running, simply click on terminal, click on new. I have opened my terminal already, and then I will simply type kubectl apply -f for force, and the name of our YAML file, it's nginx deployment.yaml, and just hit on enter. Let me try the one thing you must do is to go to file and save this file, and then we can run our command kubectl apply -f nginx deployment.yaml. As you can see, our replica set .apps.nginx replica set is created, and we are getting this first error because I didn't save my file. So every time you change something in your manifest or your YAML file, you must save this file. And then after we created our pods, our replica set pod, let's type kubectl get pods. As you can see, we have 4 pods. The first one is Nginx pods that we created in the previous chapter, and then we have 3 Nginx replica set pods that we just created. So this is how can you create more than 1 pods using replica set command. And if you go to our Docker desktop, you can see that we have our 3 pods that we just created. This is Nginx image, and it's running, and that's it. This is all for this lesson. Kubernetes services are resources that map network traffic to the pods in your cluster. You need to create a service each time you expose a set of pods over the network, whether within your cluster or externally. Kubernetes services are API objects that enable network exposure for one or more cluster pods. Services are integral to the Kubernetes networking model and provide important abstractions of lower-level components which could behave differently between different clouds. Services are necessary because of the distributed architecture of Kubernetes clusters. Apps are routinely deployed as pods that could have thousands of replicas spanning hundreds of physical compute nodes. When a user interacts with your app, their request needs to be routed to one of the available replicas regardless of where it's placed. Services sit in front of your apps to achieve this behavior. All network traffic flows into the service before being replaced to one of the available pods. Your other apps can communicate with other service IP addresses or DNS name to reliably access the pods you exposed. DNS for services is enabled automatically through the Kubernetes Service Discovery system. Each service is assigned a DNS A or AAA record, which stands for IPv4 and IPv6 record, in the format service name -namespace .svc, that stands for service, .cluster domain dash. A service called demo in the default namespace will be accessible within a cluster.local cluster at, for example, demo.default.svc.cluster.local, for example. This enables reliable in-cluster networking without having to look up services IP addresses. Let's find out Kubernetes service types. All Kubernetes services ultimately forward network traffic to a set of pods they represent. However, several different types of services exist with their own characteristics and use cases, but I will mention 5 that is currently available, and then we will work with first 3. First is cluster IP service. Cluster IP services assign an IP address that can be used to reach the service from within your cluster. This type doesn't expose the service externally. Cluster IP is the default service type used when you don't specify an alternative option. It's the most common kind of service you will use as it enables simple internal networking for your workload. Then we have node port services. Node port services are exposed externally through a specified static port binding on each of your nodes. Hence, you can access the service by connecting to the port on any of your cluster nodes. Node port services are also assigned a cluster IP address that can be used to reach them within the cluster, just like cluster IP services. The use of node port services is generally unadvisable. They have functional limitations and can lead to security issues. So anyone who can connect to the port on your nodes can access the service. Each port number can only be used by one node port service at a time to prevent conflicts. Every node in your cluster has to listen to that port by default, even if they are not running, and a pod that's included into the service. And no automatic load balancing. Clients are served by node they connect to. When a port node service is used, generally to facilitate the use of your own load balancing solution that reroutes traffic from outside the cluster. Node pods can be convenient for temporary debugging, development, and troubleshooting scenarios where you need to quickly test different configurations. The third one is load balancing services. Load balancing services are exposed outside of your cluster, an external load balancer resource. This requires a connection to a load balancer provider, typically achieved by integrating your cluster with your cloud environment. creating a load balancer service will then automatically provision a new load balancer infrastructure component in your cloud account. This functionality is automatically configured when you use a managed Kubernetes such as Amazon AKS or Google GKA, for example. Once you created a load balancer service, you can point your public DNS records to the provision load balancer's IP address. This will then direct traffic to your Kubernetes service. Therefore, load balancers are the service type that you should normally use when you need an app to be accessible outside Kubernetes. And then we have something called external name services. These services allow you to conveniently access external resources from within your Kubernetes cluster. Unlike the service types, they don't proxy traffic to your pods. When you create an external name service, you have to set the spets.external name manifest field to the external address that you want to route to, such as example.com. Kubernetes then add a CNAME DNS record to your cluster that resolves the service internal address, such as my-external-service.app-namespace.svc.cluster.local to the external address example.com. This allows you to easily change the external address in the future without having to reconfigure the workloads that refer to it. And the fifth service is headless service. Headless services are a special type of service that don't provide load balancing or a cluster IP address. They're headless because Kubernetes doesn't automatically proxy any traffic to them. This allows you to use DNS lookups to discover the individual IP addresses of any pods selected by the service. A headless service is useful when you want to interface with other service discovery systems without kube proxy interfering. You can create one by specifically setting a service spets.cluster IP field to the none value. So, which service type should you use? The correct Kubernetes service type for a particular workload primarily depends on whether you'll need external access. If you will interact with a service from outside Kubernetes, then load balancers should be preferred. A node push service can be useful instead if you can accept its trade-offs. A load balancer integration is unavailable, or you plan to implement your own load balancing solution. For workload that will be only accessed within your cluster, typically include database connections, caches, and other internal system components. Cluster IP should be used to prevent inadvertently exposing the service. Developers and operators can still connect to these services from their workstation to debug problems and manually interact with workloads using the port forwarding feature available in kubectl. Ingress are another type of Kubernetes networking object. They are often used in conjunction with services. Whereas services manage how networking is managed within your cluster, ingresses are used to control external access, typically based on HTTP and HTTPS routes. Ingresses make it much easier to run multiple apps in one cluster. Ideally, you want to avoid creating a new load balancer service for every app, as your cloud provider will bill you for each load balancer resource you use. Ingresses allow you to work with one load balancer service that reroutes traffic based on HTTP characteristics such as hostname and port. You can direct requests to app.example.com to your web app service, for example, while api.example.com targets the backend service. To use ingresses, you have to run an ingress controller inside your cluster. The controller creates a single load balancing service that you direct all external traffic to. When requests hit that service, the ingress controller compares their characteristics to the ingress rules you created. It then forwards the request to the service indicated by the matching ingress object. So, in the previous chapter, we have detailed explained what is service in Kubernetes. And in this chapter, I will show you how can you use this service, and with the help of YAML file, let's create our pods. But first, as you can see, we are in our Visual Studio Code, and then we need to create a new file, and this file will be called service-nginx YAML, service-nginx dot YAML, and I will copy my code here, and this is our, as you can see, this is our app version 1, kind service, metadata is nginx replica set, this is our selector, and protocol is TCP, port is 80, target port is 80, type is load balancer. Then I will go and simply click on save to save this file. Finally, if I want to run this service, we need to run the following command. First, I will run my nginx deployment. Let's try again, but in our terminal, kubectl apply -force, the name of our deployment, nginx deployment.yaml. There is a mistake. We need to specify the exact name of our file, of our YAML file, and then, as you can see, if you run again this YAML file, it will again run exactly the same YAML file, and there is also nginx replica set, so it will of course keep all my containers, so my pods and containers that we created in some of the previous chapter. And then we need to run this service nginx YAML. So let's run kubectl apply -f and the name of my nginx. This is our service nginx.yaml, and as you can see, replica set is created for this service-/nginx- replica set is created. And then if you run our kubectl get pods, you can see that we have our pods which is running, and then I will run kubectl get service, and we have now, as you can see, two services, and we are getting our cluster IP, which is for Kubernetes, and for nginx replica set we are here to we can see that we have our load balancer with cluster IP address. And if you want, you can copy this load balancer address 10.97.149.2010, go to your browser, simply type localhost, and you will get the welcome message from your nginx server. So this is how can you create a service from YAML file. Cluster IP is the default service type in Kubernetes, and it provides internal connectivity between different components of our application. Kubernetes assigns a virtual IP address to a cluster IP service that can solely be accessed from within the cluster during its creation. This IP address is stable and doesn't change even if the pods behind the service are rescheduled or replaced. Cluster IP are an excellent choice for internal communication between different components of our application that don't need to be exposed to the outside world. For example, if you have a microservice that processes data and sends it to another microservice for further processing, we can use a cluster IP service to connect to them. to create a cluster IP service in Kubernetes, we need to define it in a YAML file and apply it to the cluster. I'm in my Visual Studio Code, and if we want to see how can we use this type of service, the first we need to see if there is any active pods that are running. So we have this Nginx pod, and I will simply delete this kubectl, delete force service dash nginx dot YAML. So we deleted our Nginx pods from previous chapter, and then I will run again kubectl delete f. This is our nginx dash pod dash YAML, and we delete our nginx pod. Let me check just kubectl get pods, so we don't have any resource or any pods or container that is running in our environment. Let's check it in our Docker desktop. As you can see, we don't have any containers that is running. I will now open a new file. We need to add a name for this file. This will be nginx cluster IP dot YAML, and then I will simply paste this manifest that I already create to save on time. This file will be included in this chapter, in this lesson, just like every manifest or YAML file that we will be using or we are used in this part of our course. And then let me just explain what we have here. As you can see, I am now using two kinds. First one is service and the second one is deployment. Both of these manifests are included in one YAML file. So with these three dash, as I already explained in one of the previous chapter, you can see that we just, this is a border for our two type of services or two kind of services. First is service, second is deployment. And then we will create cluster IP with our Nginx service, and we will create, let me add just one replica set. So I want to create one pod, and this is our container name, and this will use the latest Nginx image from Docker Hub. So as you already know, we need to go to file to save this file, and finally I will run kubectl apply f and the name of our YAML file, nginx cluster IP .yaml. As you can see, we have two things. We created our service and our deployment with one YAML file. And let's type kubectl describe service. If I hit on enter, we can see that the type of our service is cluster IP, just what we specified in our service in our YAML file. And then you can see your IP address, port, endpoint, and so on. And you can see all other information that you need. And then if I want, I can log in to my pod. First, let me try to run kubectl get pods. I will then run, let's try kubectl get service. So as you can see, we have this service, and kubectl get all. As you can see, we have our services deployment pod, which is the name of our pod, and our replica set, which is created. And then I want to finally log in to our Kubernetes, to our pod. I will type kubectl exec-it and the name of our pod. This is the name of our pod. And then dash dash bin bash. As you can see, we are logged in to our pod. And then if you want, you can try something like curl, and you can run http localhost http, and I forgot to run curl, and then you can see we have the option to get to the web server in our pod. This is a welcoming message, and as you can see, there is our HTML document, and welcome to Nginx. This is our web server, which is successfully installed and working. So this is how can you, I will type now exit, to exit from our pod. So this is how can you set up cluster IP with the help of YAML file and use this type of service. Node port services extend the functionality of cluster IP services by enabling external connectivity to our application. When we create a node port service on any node within the cluster that meets the defined criteria, Kubernetes opens up a designated port that forwards traffic to the corresponding cluster IP service running on a node. These services are ideal for applications that need to be accessible from outside the cluster, such as web application or APIs. With node port services, we can access our application using the node's IP address and the port number assigned to the service. Once again, we are in our Visual Studio Code, and for this lesson we need to open up this file, service type node port file, that you can download from this for this lesson. Then we need to, first I will clear my screen, then I will open a new file, and this file will be, the name of this file will be nginx dash node port .yaml. Let's hit on enter, and I will simply copy this file. Once again, we are creating our service and deployment in the same YAML file. As you can see, in this service file we are using version 1 API version. Name is Nginx service, app is Nginx, type is node port, that is important. And then we have our TCP file, target port is 80, and node port port is 3007. Then, as you can see, in the deployment we are creating our Nginx deployment. I will add this to be one replica. You can leave it 3 if you want, and then we will create our service. But first, let's delete kubectl delete -force -nginx -cluster IP .yaml, and we deleted our pod and services from previous chapter. I will now try kubectl get pods. As you can see, we don't have any pods, or kubectl get service. We have this cluster IP only, but it really doesn't matter. Let's now save this file. This is our nginx node port.yaml, and then I will run our command, exactly the same command. Let's try kubectl apply -f for force, and the name of our engine x node port.yaml. I will hit on enter, and we are successfully create our service and deployment. Then let's type kubectl get pods. We have our pod, and then let's try to see our service. Kubectl get service. So you can see we have this node port, and now I will type kubectl describe service, and if we check our type, we have our node port type here. And then if you want, you can go to your browser and type localhost and the name of our node port. Let's go to our browser. I will open a new browser. Let's type localhost 33-0, and we are getting our welcome to nginx message that we successfully installed our server and it's working. So this is how can you work with service type node port. If we go back and check our Docker desktop, you can see that we have our container which is running, and that's it. Thank you for watching. Load balancer services connect our application externally, and production environment use them where high availability and scalability are critical. When we create a load balancer service, Kubernetes provisions a load balancer in our cloud environment and forwards the traffic to the nodes running the service. Load balancer services are ideal for applications that need to handle high traffic volumes, such as web application or APIs. With load balancer services, we can access our application using a single IP address assigned to the load balancer. After creating the load balancer service, Kubernetes provisions a load balancer in the cloud environment with a public IP address. We can use this IP address to access our application from outside the cluster. We learned that Kubernetes offers a powerful range of services for managing network connectivity among various components of our application. Cluster IP, node port, and load balancer services are the three primary service types, each with distinct characteristics. By understanding these differences, we can select the appropriate service for our application, ensuring security, scalability, and availability. Consequently, it's crucial to assess our application's requirements carefully before deciding on a service type. By choosing the correct service type, we can effortlessly and confidentially build and manage applications on Kubernetes. And finally, the third service type is load balancer. We are again in our Visual Studio Code, and let's first delete our previous deployment. I will type kubectl delete -f, and let me just quickly check my nginx node port.yaml. We deleted everything, so if we try to kubectl get pods, we don't have any pods in our system. Let me check my Docker desktop, and everything is fine. We can continue with our third example. I will create to open a new file, and the new name will be nginx load balancer -load balancer.yaml. I will copy my file, and as you can see, we're having exactly the same option, but type is now load balancer for our service, and other deployment is pretty much the same. Let's save our file, and then I will clear my screen, and let's apply this kubectl apply -force or f, and the name of our YAML file .yaml. I made a mistake. Load. Sorry. We need to hit dash. And we successfully created our service and deployment, and in the as you can see, a little mistake can cause a much problem. And then let's see if we had our pods running. kubectl get pods. We have 3 pods. I specify 3 in our replica. Then if I type kubectl get service, we have our load balancer address, as you can see, 10.106.69.89, and if you go to your browser and type localhost, you will get the nginx. You will see that our server, nginx server, is here running, and you will get this welcoming message. But first, let's try and type kubectl get all. You can see all our pods, all our services, all our deployment, and our replica set. And then ingress is localhost. Let's go to our browser, and I will open a new incognito browser. I will type localhost, and finally, as you can see, we're getting this welcoming message, as I already told you. So everything worked fine, and we have our nginx server that is running. So this is how can you use service types. Just to remind you, we used 3 service types. First was cluster IP, then we used node port, and finally we are using in this chapter load balancer Thank you for watching, and I hope this was helpful. Just like when we learn how to working with different images in Docker, it is possible to run the same images in Kubernetes. Let's try to run Ubuntu image from Docker Hub. But this time I want to create a single pod based on official Ubuntu image, and I want to specify in my YAML file some command and the limits number of my CPU and memory. First, as you can see, we are in our Visual Studio Code. I will simply clear my terminal from previous chapter, and then I will create a new file, and this file will be named ubuntu-pod.yaml, and here I will copy this manifest. As you can see, we are now using our API version 1, kind is pod, metadata, the name is Ubuntu pod, and we are using this latest Ubuntu, as you can see. And finally, I'm using bin bash c command, sleep. I will explain you later what this means. And then I have some limits here for our memory and how much CPU I want to restrict or add to this pod. So let's run first. Let's save this file, and after that let's run our well-known kubectl apply -force and the name of our YAML file, Ubuntu YAML, and our pod is created. Let's try kubectl get all, kubectl get all. As you can see from the previous chapter, I have this deployment for load balancers for Nginx, but now we are running Ubuntu pod and it's running. As you can see, let's, for example, type something like kubectl get pods. I have one Ubuntu pod and it's running. So all of our pods are in running state, and our Ubuntu is also in running state. If I didn't specify this command bin bash and sleep time, our Ubuntu pod will be restarted a few times. So thanks to sleep command, our container is not crashing, and if you remove this particular command, let me just show you here. If you remove this sleep command for our YAML file, it will restart again, just like in our Docker part of this course. So with the help of this C sleep and our number, our Ubuntu pod is running. And in our resources limits, I limit my pod to certain number of CPU and certain amount of memory. So this is how can you create an Ubuntu image in your Kubernetes and avoid crashing. Then let's run, for example, to describe our service. If I didn't run that command, let's try kubectl describe service. We can see that, but this time I must add the name of my pod. This is our Ubuntu pod. this is not service, this is our pod, so I will run Ubuntu pod. As you can see, all information of our Ubuntu pod you can find here. As you can see, let me find again, this is the name of our Ubuntu pod, namespace is default, priority is 0, and start time, labels, status is running. This is our IP address of this pod, 10.1.0.23. This is our ID of our Ubuntu container. Image is latest Ubuntu. It is pullable from Docker Hub. We don't have any port or host port. It's bin bash command, as you can see, and state is running. When it run, and then we added our limits for CPU and memory, and request exactly the same. And all other information you can find here. Container is initialized, ready, container is ready, and that's it. This is how can you work with Ubuntu image in Kubernetes. If I delete, you can try if you want, if you delete this command, then our Ubuntu service will be crashed and it will restart a few times, as we already saw in our Docker part of this course. Thank you for watching. If you remember, we already used MySQL image from Docker Hub to create our container in our first part of this course when we learn about Docker. But this time I will use YAML file to create our database pod. Just like in the previous chapter, when we create our Ubuntu pod, now we will run this YAML file, but first you must go to Visual Studio Code and create a new file. So let's create our new file, and this time I will add a name for this file, MySQL pod -pod.yaml, and I will copy this MySQL pod, as you can see, and in this MySQL pod we are running a simple pod. This is the name of our pod, and then this is the name of our container. Image is MySQL latest that will be pulled from official Docker Hub, and I will use something called environment. As you can see, this is just a list of environment variables to set up in the container. Then we need to specify name for my root password. This is our value root password. Then MySQL database. This is the name of our SQL database that I want to create inside this container. This is our example user, and name for MySQL password for example password. So with this environment we are specifying the name of our root password, we are adding MySQL database, we are creating a user and adding a password for this user. And then we have port. It's listed on container port 3306. If you remember, this is a port for MySQL database, and protocol is just TCP. So I will now save this file. So you must save this file if you want to run your kubectl command without any problem. As I already mentioned, it sets environment variables for the root password, database name, username, and user password. But this should be adjusted based on your requirements and kept secure in production settings. You can use something called Kubernetes secret. Of course, this is just a basic example, so in the real world, in the real production environment, you cannot specify, it is not recommended to specify this password as a plain text. So I will use this just to show you an example how can we create our MySQL pod. And of course port 3306 is exposed for MySQL communication, as I already told you. Then I will run kubectl, apply force, and MySQL dash pod dash YAML. We created our pod, and after that let's try to see our pod. Kubectl get pods. As you can see, we have our MySQL pod, and container is in the phase of creating, so we need to wait a few moments, and then I will try again kubectl get pods. Also, you can use MySQL Workbench. If you remember, this is a graphical tool that you install to connect to your database server, and you can work with database and rows, tables and rows. Also, if you forgot how can you install Workbench, MySQL Workbench, go back to our Docker part when I explain how can you install MySQL Server and MySQL Workbench for Windows machine. Let's try again. As you can see, MySQL pod is up and running, and if I go to our Docker desktop, you can see that we have our MySQL container, and if I go to images, we have our MySQL image, exactly as Ubuntu image. Let's go back to our Visual Studio Code, and right from here I will try to go inside our pod. So with a simple command, kubectl exec-it and the name of our pod, this is MySQL -pod, and then we will run --bin/bash, and enter. As you can see, I am in my container, and then you can run different commands against your pod. In this chapter, I just wanted to show you that it's possible to create a pod based on official MySQL image from Docker Hub. I hope this was helpful, and just like in previous chapters, and this file will be added to this lesson, to this chapter, so you can download it and try for yourself. Once again, thank for your attention. In this course so far, I showed you a lot how to create different pods based on official images from Docker Hub, and now I will try to deploy a multiple containers. This time I want to use more complex YAML file, so it will Docker and something called volume mounts, empty dir, and so on, just like an example from the lessons that will follow. I will now create a new file. Let me first clear my screen just to make it easier for us, and then I will add a new file, and this file will be named multiple-pod-YAML, and I will copy this manifest, this YAML file, into our new file that we just created, and I will now explain you. Let me first save this, not forget, and I will now explain you what I want to achieve. I want to create a multiple pods. So in this multi-container pod, I will create 3 containers. First is Nginx container. It serves the shared data on port 80 using Nginx, as you can see. Then I want to create Ubuntu container. It writes a simple HTML file to the shared volume and keeps running. This is our command. And finally, I want to create a log container. Continuously logs the content of the shared volume. So this is how it looks like. And then I want to use something called shared storage. An empty dir volume named shared data allows containers to share files. These volumes get mounted in different paths on each container. As you can see, we have our empty dir and it's called shared storage. This is our volume mounts. And finally, the container communicate indirectly via the share volume or data, dash data. This is mount path. I specified already that here, as you can see. And I will use environment variables. The Ubuntu container uses environment variables like greeting to demonstrate variable configuration. This design demonstrates multi-container interactions with shared storage, resource sharing, and environment variables. So this is more complex YAML file, and I will try to show you some more complex examples so that we look at all possibilities. What can we achieve with our YAML file and in Kubernetes? So we copied this to our file, multiple pod.yaml, and then we need to save this file. We already did that. And finally, let's run our kubectl command, apply -f and the name of our file.yaml. We created multi-container pod, as you can see, and let's run our kubectl get pod. As you can see, we have our multi-container pod. We have 3 containers inside this pod. So this is how can you create multiple containers inside one pod. So let's, for example, try kubectl get all, and we are getting all the information for our pods, for our service, which is Kubernetes, Nginx. This is from previous chapters. Our deployment apps, as you can see, we have 303 and replica sets from our Nginx deployment. Also, I can simply now delete our, just let me check, we are running on Nginx. For example, I will type kubectl delete -f. First I will run Nginx -load balancer .yaml. Then I will delete our Ubuntu -pod.yaml, and then I will delete, we need to wait for a second, and then I will delete our MySQL pod. Let me check just. So we are having our Ubuntu again, and I will now try to run this kubectl get all and get pods. So we have our multi-container pod only, which is running, and let's now try kubectl get describe service. As you can see, this is our default. You can see all information about our kubectl that we just created. So in this simple example, I just wanted to show you how can you create multiple containers in one pod. If you go to our desktop, Docker desktop, you can see all containers that are running, our images. This is BusyBox, as you can see, and in the volumes I have only one volume that we just created. So thanks to this BusyBox image, we created our 3 container in one pod with our YAML file. Thank you for watching, and I hope this was helpful. Kubernetes volume provides a way for containers in a pod to access and share data via the file system under usage, entails the declaration of the volume in a pod by specifying a volumes property under the spec volumes field in a pod in a manifest file, followed by the volume in an array format. And once again, we are in our Visual Studio Code, and I will create a new file. For example, this be simple volumes.yaml, and in this file I would like to present you this configuration like it looks like spec dash and then volumes, and then I will add name, for example x epsilon z. So this is the configuration will look like this. Volume mount, on the other hand, entails mounting of the declared volume into a container in the same pod. A volume mounts property spec.container.volume mounts, as well as the name property, which is the volume name to be mounted, and the mount path field where the volume will be mounted, are declared in a container in a pod. The configuration will look like this. So let's see how this configuration will look like this. I will just hit on enter a few times so we can separate these examples, and let's create our configuration for volume mounts. For example, I will type spec again, then I will run containers, dash name. I will add my app, for example, and here will be add image. I will add, for example, nginx. Then we need to add volume mounts, and here we need to add a name for this volume mounts. This will be xyz, and finally we need to specify the mount path. This example will be, for example, dash app /app/config, and this will be configuration of our volume mounts. So volume and volume mounts go hand in hand. You cannot create a volume without mounting or mount a volume that has not been created. I will now write a whole example of a volume declaration in a pod and mounting of the declared volume in a container. So let me hit on enter a few times, and just for this example let me try again spets, then containers, then I will add name, in this field let's add my app name, then we need to specify our image, and in this field let's add nginx image, and then we need to add our volume mount, then let's add a name, the name for this volume mount will be xyz, for example. Then we need to add our mount path, and our mount path will be dash app dash config, and in the next line we need to specify our volume name. Volumes, and here let's add a name xyz. So it is vital that the name of the volume to be mounted in the container under the volume mounts .name property is the same name as the name of the volume. So this is how can you write the whole script for your volume and volume mounts. So let's continue with what type of volume exists. That you know how to write a script and configuration of our volumes and volume mount, let's see what type of volumes types that is supported by Kubernetes. There are volume types that require external configuration like AWS Elastic Block Store and Azure Disk, etc. This is for cloud. This is cloud services, and which might involve billing or payment. And there is also something like empty dir, host path, secret, and config map. Volume types are classified into two categories. Ephemeral. This is the category with the same lifetime as the pod lifecycle, but persists beyond container restart. It is a fast volume solution, but not durable and should be used for temporary data or applications that do not require data persistency. The volume types under this category are empty dir, config map, secret, etc. And durable one, these are volume types that outlive the pod lifecycle. The lifetime is independent on the pod lifecycle but persists across both container and pod restarts. Data is preserved in this category when pod crashes or is deleted. The volume types under this category are host path, persistent volume claim, as I already mentioned, AWS Elastic Block Store, GCA persistent disk, Azure disk, etc. Why volumes are so important? Data persistence on disk files in a container are ephemeral, which presents some problems for non-trivial application when running in containers. One problem occurs when a container crashes or is stopped. The container state is not saved, so all of the files that were created or modified during the lifetime of the container are lost. After a crash, kubelet restart the container with a clean state. Shared storage. Another problem occurs when multiple containers are running in a pod and need to share files. It can be challenging to set up and access a shared file system across all of the containers. The Kubernetes volume abstraction can help you to solve both of these problems. So how volume works? Kubernetes supports many types of volumes. A pod can use any number of volume types simultaneously. Ephemeral volume types have a lifetime linked to a specific pod, but persistent volumes exist beyond the lifetime of any individual pod. When a pod ceases to exist, Kubernetes destroys ephemeral volumes. However, Kubernetes does not destroy persistent volumes. For any kind of volume in a given pod, data is preserved across container restart. At its core, a volume is a directory, possibly with some data in it, which is accessible to the container in a pod. How that directory comes to be, the medium that backs it, and the content of it are determined by the particular volume type used. To use a volume, you need to specify the volume to provide for the pod in .spec volumes and declare where to mount those volumes in .spec.containers volume mounts, as I already showed you in our configuration in the beginning of this chapter. When a pod is launched, a process in the container sees a file system view composed from the initial content of the container image, plus volumes if defined mount inside the container. The process sets a root of file system that initially matches the contents of the container image. Any writes to within the file system hierarchy, if allowed, affect what the process view when it performs a subsequent file system access. Volumes are mounted as specific paths with the container file system. For each container defined within a pod, you must independently specify where to mount each volume that the container uses. Volumes cannot mount within the other volumes, but see using subpath for a related mechanism. Also, a volume cannot contain a hard link to anything in a different volume. In the previous chapter, I already mentioned something called empty dir and host path. So, in this chapter, I will show you how can you work with empty dir and host path. But first, let's look at theory of empty dir in Kubernetes. An empty dir volume is a type of ephemeral storage that is created when a pod is assigned to a node. This volume provides temporary storage for the pod during its life cycle. The data stored in an empty dir volume is initially empty and can be accessed by all customers within the same pod. Once the pod is deleted, rescheduled, or moved to another node, the data is permanently erased. How does empty dir work? First, creation. The empty dir volume is automatically created when a pod starts and exits as long as the pod is running. Then access. All containers in the same pod can read from and write to the empty dir volume making it a great choice for sharing temporary data between containers. Deletion: the volume and its content are deleted as soon as the pod terminates or is rescheduled. What is mtdir used for? For temporary file storage, for the data that is only needed during the life cycle of a pod, such as intermediate processing result or temporary caching. Sharing between containers. Containers in the same pod can use an mtdir volume to share files and data. For example, a logging container can collect logs generated by another container in the same pod. High speed in-memory storage. When configured with media, memory and mtdir volume uses the node RAM instead of disk, providing faster access to data. This is useful for workloads that require high performance temporary storage. What is the difference between hostpath and mtdir? Although both mtdir and hostpath are Kubernetes volume types, they differ significantly in their functionality and purpose. So, purpose for mtdir is that he provides ephemeral pod-specific storage for temporary data that exists only for the life cycle of the pod. On the other hand, hostpath maps a directory of file on the host node file system into the pod, allowing the pod to access host level data. Data lifecycle. mtdir data is deleted when the pod is terminated or rescheduled. In the hostpath, data persists on the host node even the pod is deleted or rescheduled, making it tied to the node. Use cases. mtdir is temporary file storage and data sharing between containers in a pod, and high-speed RAM-based storage for performance-critical tasks. Hostpath is accessing host-specific files or directories, and persistent storage for logs or node-level configuration file. Node dependency. mtdir not tied to a specific node. If the pod is rescheduled, the storage is recreated but the data is lost. Hostpath tied to the node where the pod is running. If the pod is rescheduled to a different node, the volume will not be available unless the same path exists on the new node. And mtdir volume is a volume type that is first created when a pod is assigned to a node. Also, mtdir security is safer, but not direct host file system, direct host file system access. If you're using hostpath, it's a higher risk access to host file system. Lifespan for mtdir is dependent on the life cycle of the pod on that node, but it recreates when the container crashes or restarts. When a pod dies, crashes, or is removed from a node, the data in the mtdir volume is deleted and lost. This type of volume is suitable for temporary data storage. So, how to create an mtdir volume? And the mtdir volume type is created by first creating a volume and then declaring the volume type name as a field in the pod manifest file under the volume property section with empty curly braces as its value. So this example will be something like this. If we use the same volume.yaml file for our example, I can type volume mount and then hit enter, add mount path, and here I will add, for example, something like app config, and I will add a name for this mount path. Let's see, for example, like my volume, and then I will add a volume. In the new line I will add a name for this volume. This will be my volume, and then after that I will add empty dir specification and curly braces. So this is how can you add this to your YAML file. Now that you have seen that what volume and volume mount entail and their functionalities, theoretically, it is now to put this into practice by following steps that I will show you. And let's see how can we create a volume with empty dir as the volume type. So we will create our emptydir.yaml file. Let me create our new file. This will be, as I said, emptydir.yaml, and here I will only simply paste our code, and I will now explain the whole system. But first let's save our YAML file. We can also save all. As you can see, in our YAML file, in our deployment, there is API version, the deployment object API version. Every object in Kubernetes has its own API version with values which includes version 1, apps / version 1, batch / version 1. It's depending on object. Then we have kind. This field declares the object and the value must be in sentence case. This is our pod for now. Then we have metadata name. The name of the object to be created is declared in this field. Then we have spets.containers.name, and exactly the same we have for image. First field declares the name of the container image, and the second is the container image for the application is declared in this field. Then we have volumes.name. The name of the volume is declared in this field, and volumes.emptydir. As you can see, the volume type is specified in this field. Then we have volume mounts.name. As you can see, this is our name. This declared volume is injected into the container in this field, which is why the declaration is under the container specification. The name must be the same as the name of the volume. And finally, volume mounts.mount path, the path where the volume will be mounted. So this is our complete YAML deployment file, and now we need to, and of course -path is the path where the volume will be mounted. Volume mounts.mount path. This is volume mounts.mount path is the app. Now if you don't know how to open terminal, simply click on terminal, click on new terminal, go to here and choose Ubuntu WSL. I already did that, and then we need to create the pod using Kubernetes command to create this emptydir. I will now type kubectl. Let me open now my new WSL, and let's try kubectl create, or you can use our apply -f, and now I will type emptydir.yaml. Our pod my app is created. And now we can check the status of the pod, and let's see if it's running. This is kubectl get pod, and you can see it's running. Our my app is running, and it's created before 16 seconds ago. Now we can check the pod description for more information about the volumes in the pad. I will run kubectl describe pod, and my app is the name of our pod, and you can see we can check our image, and you can see that we have my volumes empty there, and this is a temporary directory that shares a pod lifetime. Of course, you can go inside your pod and perform some basic information, but for now let me just check the whole pod, and you can see what is the node, desktop node, IP address, start time, no labels, no annotation, status is running. This is our IP of our pod. We have containers, my app, this is our container ID, image is nginx, this is our image ID, it is official Docker nginx image, port is 8080 TCP, just as we added here, and host port is TCP, the date when it started, it is ready. As you can see, mount is app from my volume, rewritable, and all other information. And finally, this is volume, my volume empty there. So this is how can you create your empty there volume. And now if you want to go inside our pod, we can run the new command we already see or saw or work with this command, kubectl exec -it, and then the name of our pod, my app -- bin. And as you can see, we are now logged in our pod, our my app pod. I will now type ls just to check if the directory is still available. As you can see, we have this app boot docker entry point directory, and we can, for example, run ls app, and we can run something like that, ls app, and then I can, for example, you are now checking the value in the directory for the existing data. It should be empty. It is empty, and then I can, for example, create a file and write some data into it. Let's write a file. I will use, and let's add some name, and then I will add app -new /new file. Let's add that, and let's check if our data is stored. I will run ls app - and there is a new file, as you can see. And now that we see that our file is stored, let's display the content of our new file. Let's add cat app -new file, and this is our message that we used in this system. Now I will exit the pod and delete my pod. Simply type exit. So we are back again on our terminal, and simply I will run kubectl delete pod my app, and pod is deleted. So if I run again, for example, kubectl get pod, there is no our pod. And that we know how to set up a pod with mtdir and write something with our basic Linux command, so you need to know basic Linux command. Let's see how can we work with hostpath volume type. Hostpath volume type is a durable volume type that mounts a directory from the host node file system into a pod. The file in the volume remains intact even if the pod crashes, is terminated, or it is deleted. It is important that the directory and the pod are created or scheduled in the same node. But first I will go to our YAML, volumes.yaml, and I will hit on enter a few times just to show you how this manifest represents a host path configuration inside the pod. First you need to write volumes, then in the next line we need to add a name, and then it will, for example, host path volume, this is the name of our volume. Host path volume, so this will be the name of our volume, and in the next line you need to hit a tab, and I will add a name for this host path, and in the second line we need to hit a tab again, and let's add a path and dash data. So this represents directory location on our host. In the next few minutes I will show you how can we create and use a host path volume in a pod. First we need to create a host path volume, and just like the mtdir volume type, however the volume type name is a host path and it will replace the empty disk in the pod manifest file. We can also declare a path property, which is the directory location on the host and a child of host path property. So let's first create our manifest file. This will be host path volume YAML. I will hit on new file, and I will add the name for my file. We need to add .yaml, and in this file I will be copy this simple code, as you can see, and our configuration will look like this. I already told you what and how it looks like, and now in the volumes we add a name for our volume, and host path is path, this is mount that we want to path this of the directory on the host. And let's now save all. You need to open your terminal. Let me clear my screen in my terminal, and finally we need to run this manifest, and it will create a hostname volume and mount into a pod. And after that we will try to test the functionalities. First let's run kube kubectl, then then apply. If you more like create, you can use create option or command -f, which stands for force, and I need to rename my file. No, I don't want to delete it, just want to rename my file. Hostpath, let me add volume, and I need to rename this empty dir, just to, there will be a lot of files, so I want to add all clean. And this is our hostname.yaml. Let's create our pod. Let's check if our pod is created. kubectl get pod. As you can see, our pod is running and created 10 seconds ago. And then I will go inside my pod in our directory, just like in previous chapter. Let me find this address, and I will simply change my app name. This will be, sorry, this is exactly the same command. So let's first describe our pod and check. As you can see, let me try again from the beginning, just to be sure what we are doing. So we are adding kubectl describe pod my app, and now I want to see if this volume is our hostname volume. Is it created within this pod? Let me go. As you can see, this is 10.1.0.35. This is different IP address. And finally, let's check our my volume. It's a host path bare host directory volume. So as you can see, we are now created a pod with a hostname type. Also, if we go inside our pod, so I need to add my app and enter. We are now logged in our pod, and we can, for example, change the app directory or go to our directory. Let's type cd -app. So we are inside our app, where the mount path value from the YAML manifest file, and I will now create a new file using echo command to store some data in the file. Let's run exactly the same echo file, and then I will run exactly the same sentence, and this will be our new file .txt. Sorry, I need to add my, and run this echo command. Let's try ls to check if our data is created, our file is created. And finally, let's do a cat command to see if our sentence is printing. Simply cat file txt, and you can see I'm getting my sentence that I created in this file. Now I will hit on exit to exit from container for our pod, and finally let's delete our pod. Simply run kubectl delete my pod my app, and my pod is deleted. Let me try kubectl get pods, and we don't have any pods that running in our system. So this was a long demo, but I just wanted to show you how can you create what is an empty dir and what is a host path volume, and how to create both of them, and how to go inside your container and see or add some file into that disk. Thank you for watching, and I hope this was helpful. Kubernetes config map is a built-in Kubernetes API object that's designed to store your application non-sensitive key value config data. Config map allow you to keep config value separate from your code and containers images. Values can be string or base64 encoded binary data. Once you've created a config map, its content will be saved to your Kubernetes cluster. Pods can then consume the config map value as environment variable and config map or command line arguments or file system volumes. Config map are intended to store a relatively small amount of simple data. The total size of a config map object must be less than 1 megabyte. If you need to store more data, you should split your configuration into a multiple config maps or consider using a separate database or key value store. It's a good practice to use a config map to supply any configurable value that your app needs to at runtime. The key value pairs within the config map can be injected directly into your pods in several different formats. Because config maps are part of the Kubernetes API, it's possible to alter their values without redeploying your app pod. What is a Kubernetes config map used for? So you should reach for a config map when your app deployment needs access to config values that could change independently of your code. A classic example is a system that uses a database connection. You will need to supply the hostname or IP address of the database server for your app to function correctly. In general, a config map is the right place to deposit any user customizable settings that your application supports. End users can create a config map before installing your app in their cluster, enable them to configure their deployments ahead of time. Developing your app to read config values from its environment or file system allows you to decouple configuration from code and easily support multiple deployment methods. When you're working locally on your laptop, you can set environment variables straight into your shell. For Kubernetes deployments, you can reference values in a config map. Kubernetes stores config map in its etcd data store. You shouldn't directly edit etcd data. Instead, use the Kubernetes API server and kubectl to create and manage your config map. To backup config map values, follow the guidance to set up a backup for etcd, and these backups will contain a complete copy of your cluster data. Because config map are regular Kubernetes API objects, you can create them using YAML Kubernetes manifest files. They require a top-level data field that defines the key value config pairs to store. Keys can only contain alphanumeric characters and symbols. So let's go to our Visual Studio Code and see how can we create a config map. Welcome back, and in the continuation of this chapter, we need to first create the config map and in our manifest or our YAML file, and then we need to apply to our cluster, and then we will create another file. But first, let's make it simple and create our demo config.yaml file. I will open a new file, and this file name will be demo-config.yaml. The second file, I will create another file demo pod.yaml, demo-pod.yaml. So we have two empty files, and in the first file I will simply copy this, and this is our config map, and in the other we have other example with environment variables. I will simply copy our second file, go to our demo, we need to copy this one to our demo config file, and let me delete this. And finally, this is our AP version v1, and I will go and save all to save all our files. Let me just go and we have just two files. In our demo config file, first we need to create our config map. The following config map stores three properties. As you can see, we have database host, debug mode, and log level. We already save our manifest. This is our demo config YAML, and now I will use kubectl to apply it to our cluster and then create a config map object. So in our terminal, let me clear my screen. I will run kubectl apply -f, and the name of our YAML file, the first one is demo config.yaml, and our demo config is created. Now we can list our config maps that we created by running the kubectl command. Let's run kubectl get config maps. Sorry, I made a typo. So let's run kubectl get config map. As you can see, we have our demo config map that we created, and you can also inspect the key value pairs within a config map using kubectl describe command. So let's try kubectl describe config map, and the name of our YAML file, demo config, or demo, or the name of our config map. So as you can see, we are using our key value pairs within the config map to see our file. This is the name of our demo file. Namespace is default. We don't have any labels or annotation. Data host, as you can see, is 129.168.0.1. This is database host. Debug mode is 1, and log level is verbose. It's our binary data. Events is none. So this is how can you create your config map. Once that we create our config map, we can continue to our pod. So you can access all part of the config map as environment variables. Let's go to our demo pod, and this is environment. As you can see, config map reference. So you can see that it selects config map to populate the environment variables with. We use our environment variables form, and this is the name of our config map. demo config, as you can see. And finally, we can, as I already mentioned, access all part of our config map as environment variables, command line arguments, or mounted file. Environment variables are familiar, easy to consume in code, and open to easy inspection. They are a good way to supply a small number of simple values to your application. So the following pod, this is our demo -pod.yaml, makes the content of the demo config or our config map available as environment variables, as I already mentioned. So we created our manifest file, and that environment for field instruct Kubernetes to create environment variables from the source nested within it. The config map ref refers to config map by its name and select all its key value pairs. After we add the pod to our cluster, then retrieve its logs to see outmap from the printnf command as you want. So let's try to apply this demo pod YAML. Let's go and save all just in case, or simply save. I will now run kubectl apply dash, and let's add demo.pod.yaml, the name of our file. As we can see, we created our pod. Let's try, for example, kubectl logs and pod dash demo dash pod. As you can see, we have listed all our variables within our pod. So this Kubernetes service run on 443. This is our port, hostname, root, and so on. This is our path, as you can see. And that's it. This is how can you create and work with config map and save this into your pod. I hope this was helpful. If you want to understand it, try again or simply watch this lesson again. Just to remind you that config map are intended to store amounts of simple data. So this is how can you do it, and we are using our pod with the help of the config map to store some data. Thank you for watching, and see you in the next lesson. Kubernetes offers advantages like easy workload management with containers, but handling stateful application requires care. By default, Kubernetes pods have writable disk space and gets deleted along with the pod, which can be problematic. For application storing data, like databases or logs. To solve this, Kubernetes provides persistent volumes, or PV, which is an abstraction for managing data storage. Persistent volume allows users to allocate storage for containers without worrying about the underlying system or storage details. This API object, managed by the cluster administrator, supports various systems like NFS, iSCSI, or cloud storage. In this chapter, we will explore Kubernetes persistent volume and their best use cases. Kubernetes persistent volume ensures data retention regardless of a pod lifecycle. This ensures that data remains even if pods are deleted or rescheduled. Persistent volume claims, or PVC, request and mount specific storage to pods. This simplifies storage management for developers. Kubernetes supports multi-storage types, including a local storage, network attached storage or NAS, and cloud storage platforms, allowing flexible storage options. Persistent volume can be dynamically provisioned through storage classes when no existing PV matches the user request, automating the creation and binding process. So what are persistent volumes, or PVs? A persistent volume defines storage data, like storage classes or implementations. Unlike ordinary volumes, a PV is a resource in a Kubernetes cluster. Creating a PV is the same as creating a storage resource. Users must request this resource via persistent volume claims or PVC. These are storage requests. A persistent volume mounts into a pod using a PVC. The cluster administrator can map different classes to service level and backend policies. You can configure persistent volumes through a YAML file and specify which volume type to use. Persistent volumes solve the challenges of managing data storage in a Kubernetes cluster. Kubernetes persistent volume provide a storage abstraction layer. They enable seamless storage management while ensuring data persists. This lets developers and operators focus on app logic, not storage. A key benefit of persistent volume is that they decouple storage from pods. This decoupling allows for greater flexibility in managing pods. A Kubernetes persistent volume keeps its data if a pod is deleted or rescheduled. Also, Kubernetes persistent volume claims support various access modes. They allow many pods to read and write data at the same time. Persistent volume play a crucial role in a data storage in a Kubernetes cluster. They bridge the apps in the pods and the storage system, simplifying storage management. They also help deploy and scale containerized apps, and this lets developers focus on their core task. Furthermore, Kubernetes persistent volume provides a reliable and consistent storage solution. A persistent volume's data is not tied to a specific pod, so if a pod fails or someone reschedules, the data remains accessible. This ensures data integrity and high availability. Both are crucial for apps that need Kubernetes persistent volume for storage. Persistent volume claims is a declaration defining the request for storage usage, especially for data usage, which is mounted into a pod. A PVC is configured for use by developers who do not necessarily care about the specific implementation of the underlying data storage, but more so about the business-related data storage size, access methods, etc. Let's talk about life cycle of persistent volume and persistent volume claims. In a Kubernetes cluster, a persistent volume exists as a storage resource in the cluster. A PVC are requested for those resources and also act as claim checks to the resource. The interaction between PV, persistent volume, and persistent volume claims follow this life cycle. Provisioning, the creation of PV either directly static or dynamically using storage class. Binding, assigning the PV to the PVC. Using, pods use the volume through the PVC. And reclaiming, the persistent volume is reclaimed either by keeping it for the next use or by deleting it directly from the cloud storage. A volume will be in one of the following states. Available, this state shows the PV is ready to be used by PVC. Bound, this state shows that the PV has been assigned to a PVC. And released, the claim has been deleted, but the cluster has not yet reclaimed the resource. And failed, this state shows that an error has occurred in the persistent volume. There are two ways to provision persistent volume storage in Kubernetes. First is static. PV or persistent volume are created by Kubernetes cluster administrator and exist in the Kubernetes API. PVs represent real storage, and these stores provided by PVs are available to all users in the cluster. With static provisioning, the persistent volume is created in advance by the cluster administrator, and developer creates the persistent volume claim and the pod uses the storage provided by persistent volume through the persistent volume claims. And we have dynamic. For dynamic provisioning, when none of the static persistent volumes created by the administrator can match the user's persistent volume claim, the cluster will try to automatically provision a storage volume for persistent volume claim, which is based on storage class. In the dynamic provisioning direction, the PVC needs to request a storage class, but this storage class must be pre-created and configured by the administrator. The cluster administrator needs to enable the access controller for default storage class in the API server. Binding: the user creates a PVC or has previously created one for dynamic provisioning, specifying the request storage and access mode. The master has a complete loop to monitor new PVCs, find matching persistent volumes, if any, and bind the PVC and PV together. If a PV is ever dynamically provisioned to a new PVC, the loop will always bind the PV to the PVC. In addition, users will get and always get at least the storage they request, but the volume may exceed their request. Once bound, the PVC bindings are exclusive no matter what their binding mode is. If no matching persistent volume is found, the persistent volume claim will remain unbound indefinitely, and once the persistent volume is available, then the persistent volume claim will become bound again. For example, if a cluster is provisioned by many of 50 gigabytes persistent volumes, it will not match the 100 gigabytes personal volume claim request, and the personal volume claim will not be bound until 100 gigabytes persistent volume are added to the cluster. The pod uses PVC as a volume, and the Kubernetes cluster looks at the bound persistent volume by the PVC and mount it to the pod. The users can specify the access method when using PVC as a volume. For volumes that support multiple access methods, the user specified which mode is desired when using their claim as a volume in a pod. Once a user has a bound PVC, the bound PV belongs to that user, and the user can access the possessed persistent volume through the persistent volume claim contained in the pod storage. One of the common use cases of persistent volume is database management. Databases often require persistent storage to maintain data integrity and ensure high availability. By using a persistent volume, administrators can ensure that the data stored in the database remains persistent even if the corresponding pod goes offline or gets rescheduled. Another use case for persistent volumes is file sharing and collaboration applications like content management system or file servers often require shared storage where multiple pods can read and write data simultaneously. Persistent volumes provide the necessary functionality to meet these requirements. In addition to databases and file sharing applications, persistent volumes can also be beneficial in other scenarios. For example, in machine learning application, where large data sets need to be stored and accessed by multiple pods simultaneously, persistent volumes offer a scalable and efficient solution. Similarly, in Internet of Things or IoT deployment, where sensor data needs to be collected and stored persistently, persistent volume can ensure data reliability and availability. Overall, persistent volume are a powerful tool in the Kubernetes ecosystem. They provide a flexible and reliable way to manage data storage, decoupling it from individual pods and enabling seamless scaling and management of application. By understanding the purpose and benefits of persistent volumes, developers and operators can make informed decisions about when and how to leverage this technology and applications. Now that we know what is persistent volume and persistent volume claim, in this continuation of this chapter, I will now create a new file. In this file, I will name PV and pv-pvc.yaml, and finally I will copy this YAML manifest, and in this YAML manifest, as you can see, we are creating a persistent volume, which is the first part of this manifest. So the name is shared volume, and data is shared and hosted on /data/share volume, as you can see here. And capacity is 1 gigabyte. Access mode is read write many. Reclaim policy is retain. Storage class is manual. Then in the second part we are creating our persistent volume claim. This claim, this is the claim that bind pods to the volume. Multiple pods can use the same claim. So this is a share volume claim. It uses exactly the same access mode, storage, and storage class name, as you can see here, and the name is almost the same. And then we are creating two pods, both pods app1 and app2 mount the share volume at data, as you can see here, dash data, using the shared volume claim. So this setup allows multiple pods to access the same shared volume. And then we need to save this file. I will click on save all, and then in our terminal I will run kubectl apply -f and the name of our YAML file. As you can see, we successfully created persistent volume and persistent volume claim and pod app and pod app1 and pod app2. Let me try to run kubectl get pod, and as you can see we have two pods that is running, and these pods share the same volume. If I go to our Docker desktop, you can see that we have two apps. Let's go inside one of these apps, and let me try to find, and if I go to bind mounts, you can see that we have this data dash share volume that is the part of our app1 and app2. Let's go to our app2. This is our logs. Let's go to bind mounts, and you can see there is data share volume for all of our containers. So this is how can you work with your and create a pod. So in this chapter I wanted to show you how can you create persistent volume and persistent volume claim, and how can you create multiple pods that can or that have access to the same shared volume. Thank you for watching, and I hope this was helpful. In this chapter we will do an example of a YAML file for a Kubernetes pod using a persistent volume. Let's go to our Visual Studio Code. If you didn't, just go to our Visual Studio Code, and I will create a new file called mypv.yaml. Then I will copy this manifest. As you can see, persistent volume for mypv define the storage resource in Kubernetes that persist independently of any pod. Then if I scroll down, this kind of persistent volume claim represent a request to bind the pod of the persistent volume, and this is my pod. It uses the persistent volume by referencing the claim in its volume section and mounts it into container at -data, as you can see here. So this setup ensures that our data remain accessible and persistent even if a pod is deleted or recreated. So in the last chapter, in the previous chapter, I introduced you with the persistent volume and the persistent volume claim terms, and we saw how can we create multiple pods to access the same shared volume. But now I want to create a simple pod that have this persistent volume. So we need to run our kubectl, but first let's save our file. I will run save all, and finally let me just run kubectl apply -f, and then I will add my-pv.yaml, and we successfully created one pod with persistent volume and persistent volume claim. Then we can, for example, try kubectl get all, and you can see all services that are currently running, and we have my pod that is running. Of course, the first two pods are from the previous chapter, so my pod is exactly what I want to do in this chapter. Also, let's try kubectl get service, and we have our cluster IP. If I try kubectl describe pod and pod my pod, we can see that we have our persistent volume claim type. So this is how can you create and run this persistent volume and persistent volume claim on one pod. So I will now simply leave this as it is, and let's go to our next lesson. Docker Desktop includes a standalone Kubernetes server and client, as well as Docker CLI integration, enabling Kubernetes development and testing directly on your machine. The Kubernetes server runs on a single or multi-node cluster within Docker containers. This lightweight setup helps you explore Kubernetes features, test workload, and work with container orchestration in parallel with other Docker functionalities. Kubernetes on Docker Desktop run alongside other workloads, including Swarm services and standalone containers. Docker Desktop Kubernetes can be provisioned with either the kubeadmin or kind provisioners. Kubeadmin is the older provisioner. Let's go to our Docker Desktop, and if I go to Settings and go to Kubernetes, you can see that we, in the beginning of this second part of our course, enabling this Kubernetes, so we are starting a Kubernetes single or multi-node cluster when starting Docker Desktop. So you can see it's running, and it's green here, and Kubernetes is running. Also, you can see the usage of your CPU and memory usage and engine disk utilization. Also, there is a cluster settings I already mentioned. It can be kubeadmin or kind. Also, you can enable this to show system containers, and this is advanced. So, this kubeadmin supports a single node cluster, so you can select the Kubernetes version. It's slower to provision that kind, and it's not supported by enhanced container isolation or ECI, meaning that if ECI is enabled, the cluster works, but it's not protected by ECI. Kind, it's a newer version and newer provisioner, and it's available if you are signed in and are using Docker Desktop version 4.38 or later. It supports multi-node cluster for a more realistic Kubernetes setup. You can choose the Kubernetes version. It's faster to provision than kubeadmin, and it's supported by ECI or enhanced container isolation. When ECI is enabled, the Kubernetes cluster run in unprivileged Docker containers, making it more secure. Note, however, that kind that requires the Docker desktop must be configured to use container D image store, and this is the default image store on Docker desktop for 4.34 and later. And Kubernetes clusters are not automatically upgraded with Docker updates, Docker desktop updates. To upgrade the cluster, you must manually select Reset Kubernetes Cluster in your settings. So, if you click on this Reset Cluster, there will be automatically upgrade to your cluster. So, this is just a quick update, or how can you update your Kubernetes in your Docker desktop. Assigning pods to nodes is one of the most critical tasks of Kubernetes cluster management. While the default process can prove too generic, you can adjust it with advanced features like node affinity. The way the Kubernetes scheduler distributes pods across worker nodes impacts performance and resources, and therefore your cost. It's then essential to understand how the process works and how to keep it in check. This chapter outlines basic Kubernetes scheduling concept, including node selector, node affinity and anti-affinity, and the pod affinity and anti-affinity. It also includes some example of how can you run certain things. So, how Kubernetes scheduling work? Kubernetes scheduling is about selecting a suitable node to run pods. Kubescheduler is a part of the control plane, and it selects nodes for a new or not yet scheduler pods by defaulting trying to spread them evenly. Containers in pods can have different requirements, so the Kubernetes scheduler filters out any nodes that don't match the pod's specific needs. The Kubernetes scheduler identifies and scores all feasible nodes for your pod. It then picks the one with the highest score and notifies the API server about the decision. Several factors impact the scheduler decision, such as resource requirements, hardware and software constraints, etc. The Kubernetes scheduler is fast, thanks to automation. However, it can be expensive, as you may have to pay for resources that are insufficient for your different environments. And as there is no easy way to track your cost in Kubernetes, teams must find other way to keep their expenses in check. How to control the scheduler choices? In a nutshell, you can control where your pods go with Kubernetes labels. Labels are key value pairs you can manually attach to objects like pods and nodes. By using them, you can specify identifying attributes, organize or select subset of objects. The simplest way to constrain the Kubernetes scheduler is to use a node selector. How does a node selector works? Adding the node selector field to your pod specification with a key value pair lets you indicate the labels you wish to target node to have. Kubernetes will only schedule pods onto the nodes matching the labels you specified. The node selector is sufficient in small clusters, but is usually unsuitable for complex cases. For example, you may have an app that needs to run in separate availability zones, or you may want to keep the API and database separate when you want to don't have many replicas. That's where the concept of affinity comes in handy. Affinity and anti-affinity expand the types of constraints you can add and give you more control over the selection logic. Using them, you can create a preferred and soft rules for different conditions for Kubernetes to schedule the pod even if there are no perfectly matching nodes. They also let you match the labels of pods running on the same nodes and specify the location of new pods more precisely. It's essential to keep in mind that there are two types of affinity. Node affinity refers to impacting how pods get matched to nodes, and pod affinity specify how pods can be scheduled based on the labels of pod already running on the node. Node affinity is... So what is node affinity? How does it work? It's similar to node selector. Node affinity also lets you use labels To specify to which node kube scheduler should schedule your pods, you can specify it by adding the .spec.affinity.node affinity field in your pod. Remember that if you specify node selector and node affinity, both must be met for the pod to be scheduled. There are two types of node affinity: required during scheduling, ignored during execution. When using this one, the scheduler will only schedule the pod if the node meets the rule, and preferred during scheduling, ignored during execution. In this scenario, the scheduler will try to find a node matching the rule, but it will still schedule the pod even if it doesn't find anything suitable. The ladder lets you specify each instance weight by using a value between 1 and 100. When the scheduler finds nodes meeting all your unscheduled pods requirements, Kube Scheduler iterates through every preferred rule that the node matches and adds the value of the weight to a sum. The Kubernetes scheduler then adds this sum to the final score, impacting your pod final node decision. What is a pod affinity? Working along similar lines, this concept focuses on impacting the Kubernetes scheduler based on the labels on the pod already running on a given node. You can also specify it within the affinity section using pod affinity and pod anti-affinity field in the pod spec. Pod affinity assumes that a given pod can run in a specific location if there is already a pod meeting particular condition. Pod anti-affinity offers the opposite functionality, preventing pods from running on the same node as pods matching particular criteria. So, we will see an example of a Kubernetes YAML configuration for affinity node. This will ensure that a pod is scheduling on the nodes that match specific criteria. Finally, we will try to set a YAML configuration for node affinity. This will ensure that our pod is scheduled on node that match specific criteria. So I will open a new file in our Visual Studio Code, and this will be node affinity, for example, node affinity .yaml. I will copy my manifest, and in this affinity is everything that we talking in our theory section. So as you can see, we are trying to run a pod. This is the name of our pod. This is pod with node affinity, and in spec option we have affinity, node affinity, and this required during scheduling, ignore execution. As you can see, this is here, and this ensures that pod will only be scheduled on nodes that match the criteria. For example, kubernetes.io host model node 1. This is our value. And then we have other preferred during scheduling, ignore during execution. This is used to prefer nodes with additional characteristics such as disk type. For example, we're adding our SSD disk type, and it doesn't prevent scheduling on other nodes but gives a higher weight to the preferred nodes. Then we have pod. The pod runs an Nginx container, and this allows precise control over where your pod will be deployed within your cluster. As you can see, this is the name, and this is our complete manifest or YAML file. I will now go to our file, click on Save All to save this YAML file, and let me first clear my screen, and I will now run kubectl apply -f, and finally we need to add a name node of our YAML file, node affinity .yaml. I will hit on enter, and we created our pod. Let me just try to run kubectl get pod. We have our it's still pending, sorry, our pod with node, so we have to wait. But this is how can you use this special affinity and add some node selector terms. I hope this was helpful, but let's see if our pod is still pending. So after a minute or two our pod will be created, and we can check in our, let me run again. We don't have our pod is not created yet, but it will be soon. So I will try again after this pod get created. Our pod with node affinity is created, but still in pending state. So this was just a simple example. It really doesn't matter if it's running or not. Just wanted to show you how can you use this node selector, and what is node selector, and how to add this node affinity to your YAML file. Thank you for watching, and I hope this was helpful. Init containers are just like regular containers, but they run to completion and run before the main container starts. There are various use cases for init containers, such as init containers can contain certain utilities or custom code for the setup that is not persistent for the app container. It can also change the file system before starting the app container based on certain logic. It can also be used to limit the attack surface by keeping certain tools as a part of init containers. Init containers can also delay the start of the main containers by having some precondition check unless they are met if it keep trying to the init containers. Writing and using init containers in Kubernetes. To write the init containers, we have to specify that in the spec section. In the spec section of the pod, we have to define the init containers. There can be one or more init containers, which will be running sequentially. The first init container runs and then it completes. Then the second one runs, it completes, and the other containers will start. None of the pod lifecycle or probes can be used for init containers. That's pretty much it about the init containers. Let's try to create our init container. First, I will open a new file, and then I will add init container -YAML for this file, and I will copy my manifest file. As you can see, this is our init container, and this is what I've been talking about in the previous chapter. As you can see, this is the list of initialization container that belongs to this pod. The init container runs before main container. It writes a file index.html with a message to the shared volume at /data. This is our volume mounts and name, and as you can see, mount path, and we are using empty dir. As you can see, this is hello from the init container /data/index.html. Main container, this is our main container here in spec, runs the nginx web server, and it serves the index.html file written by init container from user-share-nginx-html, as you can see here. And then you have shared volume, and empty dir, as I told you, is used to share data between the init container and the main container. And this use case, our init containers are great for the task like preparing environment, pulling dependencies, or ensuring prerequisites are met before the main container start. So what will happen here is that our init container will run before that our main container. It will write a file, this echo hello message from hello from the init container, and then it will stop, and then our main container will be created, and our main container of course run nginx web server, and it serves this index.html file written by init container, and that's it. Let me first save my file, save all, and now I will be running once again kubectl apply -f and the name of our init container dot YAML. So it is created, as you can see, and if we try kubectl get pods, you can see that we have init container is running and main container will be here very soon. And also you can try to log in to your init container example. As you can see, it defaulted container main container, out of main container init container, so you can now run whatever you want, some command, and this is how can you create your init container and it runs before our main container. Thank you for watching. Now that we know what is init container, let's look at what is a sidecar container. Rather than running as a standalone container or service, sidecar containers are used to enhance or extend the functionality of the main container without changing its core behavior. Imagine you have a web server running in a container. A sidecar container could be added to handle logging, monitoring, or security. This pattern allows you to separate concerns, allowing each container to perform tasks while maintaining modularity. Why will we use side containers in Kubernetes, or why use side containers in Kubernetes? First reason is separation of concerns. Sidecar containers keep your architecture modular by separating application concerns. The main application container remains focused on its primary responsibility, while the sidecar container handles auxiliary tasks. This separation reduces complexity and improves maintainability. Then the second reason is reusability. Sidecar containers are highly reusable across different applications. Whether it's for monitoring, logging, or security, you can use the same sidecar container in multiple pods, saving time and effort when managing your microservices. Then the third reason is scalability. Because the sidecar containers run within the same pod as the main application, it can scale independently, offering flexibility in how resources are allocated. You can also ensure that sidecar containers will always be co-located with the application container, which simplifies networking and communication. And fourth reason is reliability. Sidecar containers are ideal for tasks like health checks, retries, and proxying traffic. This makes your application more reliable, as you can handle errors or failures without impacting the main container. In Kubernetes, the pod lifecycle governs how containers within a pod are managed. This is especially relevant when dealing with sidecar containers, as they often perform crucial functions alongside the main application container. Here, how sidecar containers work with the pod lifecycle. Key phases of the pod lifecycle. First is pending. At this stage, the pod has been created, but Kubernetes has not yet scheduled it to a node. During this phase, the pod containers, including the sidecar containers, are not running. Kubernetes will soon determine the approach node for the pod to be scheduled onto. Running. Once the pod has been scheduled to a node, it enters the running state and its containers, both the main application container and the sidecar containers, are actively running. At this point, sidecar containers work in tandem with the application container, providing their auxiliary functions like logging, monitoring, or proxying. Succeeded or failed. If a container inside the pod terminates successfully, like an init container completes its task, the pod enters the succeeded state. If the container fall, the pod enters the failed state. For sidecar containers, they must handle failures gracefully. For example, logging containers should ensure that logging continues even if the container crashes. Sidecar containers impact. Sidecar containers typically run throughout the pod lifecycle. If a sidecar container fails but the application container is still running, you may want to adjust the pod's restart policy or handle failures through probes. Terminating. When a pod is being terminated, Kubernetes will start stopping its containers. In this phase, the side container will also stop, but Kubernetes ensures it does so gracefully. Depending on your configuration, you can manage how the sidecar containers stop using termination grace period seconds option in your manifest file. Then, since sidecar containers, there is sidecar container impact. Since sidecar containers share the life cycle of the pod, they will also be terminated when the pod is deleted. Sidecar containers may need additional configuration to ensure they properly handle termination signals and perform cleanup tasks, sending final log data. And if we have an unknown state, if Kubernetes cannot determine the state of the pod, it enters the unknown state. This could happen if the pod's status cannot be retrieved for some reason. Sidecar containers impact. In this case, the sidecar containers may also be an intermediate state. It's important to use monitoring and readiness probe to ensure you detect this situation and act accordingly. So let's now go to our Visual Studio Code and try to configure our sidecar container. In this chapter we will run first we will create our new file, and this will be an example of Kubernetes configuration file using a sidecar container. I will create a new file. It will be sidecar-container.yaml, and I will paste my manifest. As you can see, this is a simple pod. We have our main container. As you can see, this is main app, and this is the primary application container running an Nginx server. As you can see, it also writes logs to -var-log-nginx, which is mounted on the shared volume, as you can see. And sidecar containers run log processor. This is our log processor, as you can see. This is our sidecar container, and this container process or monitors the logs created by the main application. In this case, it used the tail command to continuously output the logs to standard output. This is the tail command, and this is the log, as you can see. And we have our shared volume, empty-dir. Both containers share an empty-dir volume, enabling this sidecar container to access the logs generated by the main container. So now let's go to save our file, and in the terminal I will run kubectl apply or create, if you more like that command, and then we will run our sidecar container YAML file, and we created our container. I will now run kubectl get pods. As you can see, our sidecar example is running, and now I will type kubectl describe pod and name of our container, of our pod, sorry, example. And as you can see, we have type is empty-dir that we specified, and command is tail, and all logs will be added to this file. This is the complete file of complete this describes the whole system that we created, and this pattern is useful for implementing additional tasks like logging, monitoring, or data synchronization without modifying the primary application container. So this was sidecar containers, as you can see, and in this chapter I just wanted to show you how can we create our sidecar example. So as you can see, we have two containers that is running. One is a sidecar, and this container processes or monitors the log created by our main application, and our main application is our main app, which running container running an Nginx server. So all logs from this Nginx file will be stored in our sidecar containers in this /log/access.log file. Thank you for watching, and I hope this was helpful. In Kubernetes, a probe is a mechanism used to determine the health and readiness of a container or application running with a pod. Probes are defined in the pod specification and are performed periodically to ensure the proper functioning of the application. Kubernetes supports three types of probe: liveness probe, readiness probes, and startup probes. A liveness probe determines if a container is still running and functioning correctly. If the liveness probe fails, Kubernetes considers the container to be unhealthy and takes appropriate action, such as restarting the container. Liveness or liveness probes are essential for applications that can encounter runtime issues or deadlock situations. A readiness probe determines if a container is ready to receive incoming network traffic and serve requests. It ensures that the container has completed its initialization process and is prepared to handle a request. If the readiness probe fails, Kubernetes removes the container IP address from the service list of endpoints, directing traffic to other healthy containers. And the third one is startup probe. It is used to determine if a container application has started successfully. It is mainly useful for scenario where an application takes a longer time to start, but can eventually become healthy. Unlike liveness and readiness probe, the result of a startup probe does not affect the container's readiness or liveness status. Once the startup probe success, the liveness or liveness and readiness probes take over. For each probe, you can define various parameters such as probe type, HTTP, TCP, or exec, the probe's timeout, the interval between probe checks, the number of consecutive failures before considering the probe as failed, and the success criteria. Probes provides Kubernetes with the ability to manage container health and readiness automatically, allowing for better resilience, self-healing, and efficient routing of network traffic within the cluster. Here are a few problems that can arise with Kubernetes probes. Misconfigured probes. One of the most common problems is misconfiguring the probes, such as specifying incorrect endpoints, port, or paths. This can lead to false positive or false negative results, causing containers to be erroneously marked as unhealthy or ready. Insufficient timeout. If the timeout for a probe is set too low, it might result in false failures. If the container takes longer to respond due to a high load or complex initialization process, the probe might time out and mark the container as unhealthy, triggering unnecessary restarts. Unresponsive or slow applications. Probes rely on the responsiveness of the application or process within the container. If the application is unresponsive or slow due to bugs, performance issue, or resource constraints, it can lead to false negatives and misjudgment of container health. Resource constraints. In case where probes put additional load on containers, such as HTTP requests or executing commands, it can consume resources and affect the performance of the application itself. This can result in delays in application responsiveness or increased resource utilization. Timing issue. In certain scenarios, timing can be challenging. For example, if the initial delay for a readiness probe is too short, the probe may start the container before the container's application has finished initializing. This can lead to false negatives and prevent the container from receiving traffic prematurely. Interference with container startup. If a liveness or readiness probe is too aggressive, you can interrupt the startup process of a container. For example, if the probe starts too early and triggers a restart during the initialization phase, it can prevent the container from properly completing its setup. It is important to know that the probes are controlled by the kubelet. It's essential to carefully design and configure probes based on your specific application, characteristics and requirements. Regular monitoring, troubleshooting and tuning of probe settings can help address this issue and ensure that the accurate health and readiness detection of containers within a Kubernetes cluster. In the continuation of this chapter, I will try to create and work and show you how can we work with liveness probe, readiness probe, and then we will use startup probe. But first, as I promised, let's create our new file in our Visual Studio Code. I will create a new file and let's add a name, livenessprobe.yaml, and in this file I will copy this manifest, and just to explain this, we'll create a new pod and it checks if the application running in the container is healthy. If in this case it sends HTTP GET request to the root path, as you can see our path HTTP GET, our root path is this / symbol y port 80. If the container fails this check, Kubernetes restarts the container automatically. Initial delay seconds specifies how long Kubernetes should wait after the container start before performing the first probe. Here it's set to 5 seconds. And period seconds is 10. Specifies the interval between subsequent liveness check, and as I already mentioned, it set to 10 seconds. This setup is useful to ensure your application remains operational and any issue causing the container to hang or crash are resolved by restarting it. I will now go and save this file, and then we will run kubectl apply -f and let's add our name. So this pod or container is created, and if I now run kubectl get pods, we can see that our liveness probe example is running. Let's now type kubectl describe pod, and I will add the name for our pod. This is liveness probe example, and let's see what we're having here. As you can see, namespace is default. Node is Docker desktop. This is our IP address of our 10.1.0.24, and it's running. So as I already mentioned, in the liveness probe. And in this setup, we are ensuring that our application remain operational and any issue causing the container to hang or crash are resolved by restarting it. So, as you can see, we set our initial delay seconds to 5 seconds, and it specifies how long Kubernetes should wait after the container start before performing the first probe, and our period in seconds specify that interval between subsequent liveness check is 10 seconds. So this is how can you work with liveness probe. And now let's see how can we work with readiness probe. This probe checks whether the application in the container is ready to serve request. But first, let's create our new file, and I will add a name for this file. This will be readiness probe.yaml. Let me just copy my manifest and let's save our file. Let's save our file. And as you can see, kind this pod name is readiness probe example, exactly my name, nginx image, and in this case Kubernetes only send traffic to a pod that passes its readiness check. In this example, the probe performs an HTTP GET request on the root path. As you can see, this is HTTP GET and our root path is / on the container on port 80, listen on port 80. In the initial delay seconds is set to 5, so this specifies how long Kubernetes should wait until the container starts before performing the first readiness check. Here is 5 seconds, and period seconds. As you remember from previous chapter, we specify that in interval between subsequent readiness checks, here it checks for every 10 seconds. And by applying this application, this manifest or this YAML file, this ensures that application is fully initialized and ready before it starts receiving traffic. So let's now run. First I will clear my screen, and then let's run our command kubectl apply-f and the name of our YAML file readiness probe.yaml, and we created our pod. I will now run kubectl get pod. As you can see, our liveness probe example is running. Readiness probe is running. Let's try again, and finally we have our readiness probe. And now I will try to describe, for example, service. You can see some additional information, and then I will describe a pod. Our pod name is readiness probe example. As you can see, this is our this is where you can find all information about your pod. So this is how can you run this readiness probe. In this probe, just to remind you, we will be able, or we are able to check whether the application in the container is ready to serve request. As you can see, it is ready, and now Kubernetes only send traffic to that pod that passes its readiness check. In this example, the probe performs HTTP GET request on the root path of the container port that listen on port 80. And finally, the third probe is startup probe. I will now create a new file. Let me add a name for this file. This will be startup probe.yaml, and let me copy my example. And in this example, the startup probe checks if the application in the container has successfully started. It allows Kubernetes to perform these checks before other processes, like the first two, liveness or readiness. In this example, HTTP GET request is sent to dash, as you can see, this is our path, and on port 80. Initial delay seconds is 10, and Kubernetes wait for 10 seconds after the container start before performing first check, startup check. Period seconds to wait is 5, and it checks every 5 seconds, and we have a new command or new option. This is failure threshold is set to 10. It specifies the number of consecutive failures, 10 seconds, before Kubernetes concludes the container has not successfully started, and then it restarts automatically. Let me save this file. I will then clear my screen, and in our terminal, let's write exactly the same command, kubectl apply -f, and then we will add our YAML file, startup probe.yaml. It created our pod, and this probe is particularly useful for application with log initialization process to ensure they have enough time to start before being subject to other probes or traffic. Just to remind you, this startup probe checks if the application in the container has successfully started. It allows Kubernetes to perform these checks before any other probe, before two probes that we already saw. How can we work? Specifically in this example, HTTP GET, as you can see, request is sent to this /path on port 80. Let me now try command kubectl get pods. As you can see, we have our startup probe example ready, and let's describe our pod. Our pod name is startup dash probe dash example, and as you can see, you can see all the necessary information that you need to know about this pod. So this is how can you work with probes in Kubernetes. And finally, if you remember, we started with node selector and then continue with init containers. Then we work with sidecar containers, and now with probes. In this set of chapters, I just want you to show you that there is a complex and more complex way that you can work with your Kubernetes and find out everything. These complex settings and examples are good if you are trying to learn more about Kubernetes, and this will help you if you work on some other environment, for example in the cloud. So in the third part of our course there will be some examples, but this is just a crucial thing if you want to work with Kubernetes and learn what is init containers, what is probe, what is node selector, and how to check application that run into your container. Thank you for watching, and see you in the next lesson. When you're using a kubectl and type this command, almost every time when you want to run some command against your container, against your pod, against, I don't know, it really become annoying and boring to type this every time. There is an alias command which simplify use of kubelet. If you run this command, for example, alias k equal kubectl namespace, and you need to add the default, the name of your namespace. My namespace is default. You can set an alias, and every time that you type k, it will represent kubectl. So I have some pods that are already running, and I will now try to type kubectl, but now I will use this. First, let's try kubectl get pod. As you can see, we have our kubectl that is running, and I will now try to run just k and get pod. As you can see, we set this alias, and now you can simply run k. You don't have to type kubectl. This is a convenient when you work in the great environment and you have many containers or pods or clusters that running thousands of pods. Let's see, for example, some more. Let's delete some of the pods. Let's try, for example, k delete -f, and I will now run. Let me try, for example, let me just find node dot affinity dash YAML. It's not dot, is dash YAML. Let's try again. So as you can see, it works. And if I try, for example, k get pods, now we don't have our pod with node affinity. As you can see here, we don't have any pod. And now I will simply delete all of my pods. So you can run k delete -f, and I will simply run what we have here. We have sidecar dash container dash YAML. I have init dash container dash YAML, and as you can see, this is how can you delete multiple pods in your environment. And this alias is good example how can you save on some time or save your nerves if you don't like to type this kubectl every time. You can now just simply k, and this alias will work every time, or k will work every time when you use this. In this command line. Thank you for watching, and I hope this was helpful. As you can see, I deleted all of my pods that we created in this demo, and I just want to say something about Docker and Kubernetes. At the end of this second part of the course, in which we covered Kubernetes in great detail, I would like to point out that this is only part of what can be done with this excellent service or services. It doesn't matter at all if you are a developer or not, or administrator or architect. This introduction to the world of Kubernetes can be enough, or Docker, can be enough for you to master the basics and much more. My message is that if I have interested you, you can continue to study and maybe go for one of the certificates offered by this popular service. As you have seen for yourself, working in Docker and Kubernetes requires a certain knowledge of Linux. So it is always good to learn the concept of this operating system and the main commands at the same time. Congratulations on completing this course. I hope you enjoyed learning Docker and Kubernetes as much as I enjoyed creating this course for you. Remember, mastering these technologies doesn't happen overnight. The best way to improve is by practicing regularly. Experiment with containers, build your own applications, deploy them to Kubernetes, and don't be afraid to make mistakes. Every mistake is an opportunity to learn. If you found this course helpful, please consider liking the videos, subscribing to the channel, and sharing the course with others who might benefit from it. Your support helps me create more free educational content. Of course, on my channel you will find different type of courses. Thank you for choosing to learn with me. I wish you the very best in your DevOps and cloud computing journey. Good luck, and I will see you in the next course.